Hello everyone, once again welcome back to our channel Beat the Neat। और फाइनली क्लास 11th की आप देख सकते हो पूरी ऑडियो बुक आ गई है आपके लिए। और इसकी जो दूसरी वाली बुक है उसकी भी जल्दी ही मैं पूरी ऑडियो बुक आप लोगों को प्रोवाइड कर दूंगी। ये एक ऑडियो बुक है, नॉट द एक्सप्लेनेटरी वन बच्चा, सो वेन एवर यू आर लिसनिंग इट बी स्पेसिफिक विद दैट। ये वीडियो काफी लंबा है बट इसमें सारे चैप्टर्स मैंने आपके कवर कर दिए हैं। तो चलिए एंजॉय करिए और अपने दोस्तों के साथ में ज्यादा से ज्यादा शेयर करिए, क्योंकि उसे बनाने में मुझे बहुत मेहनत लगी और आप लोगों की रिक्वेस्ट और आप लोगों की तैयारी देखते हुए मैंने इसे तैयार किया है, क्योंकि मुझे पता है इन ऑडियो बुक से आपको रिवीजन में बहुत 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 हेल्प मिलती है। तो चलिए टाइम वेस्ट नहीं करते हैं और जल्दी से शुरू करते हैं।
Some basic concepts of chemistry. Chemistry is the science of molecules and their transformations. It is the science not so much of the 100 elements but of the infinite variety of molecules that may be built from them. Roald Hoffmann. Science can be viewed as a continuing human effort to systematize knowledge for describing and understanding nature. You have learned in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane, juice on keeping for prolonged time, and rusting of iron are some of the examples of changes which we come across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation, properties, structure, and reactions of material substances is called chemistry. Development of chemistry. Chemistry as we understood it today is not a very old discipline. Chemistry was not studied for its own sake. Rather, it came up as a result of search for two interesting things. Number one, philosopher's stone, Paris, which would convert all baser metals, example iron and copper, into gold. Number two, elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of the life. Chemistry developed mainly in the form of alchemy and iatrochemistry during 1300 to 1600 CE. Modern chemistry took shape in the 18th century Europe after a few centuries of alchemical traditions which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and the Indian, had their own alchemical traditions. These included much knowledge of chemical processes and techniques. In ancient India, chemistry was called Rasayan Shastra, Rasatantra, Raskriya or Rasavidya. It included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systematic excavation at Mohenjo-daro in Sindh and Harappa in Punjab proved that the story of development of chemistry in India is very old. Archaeological findings show that baked bricks were used in construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process, in which materials were mixed, molded, and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in the construction work. It contains lime, sand, traces of CaCO3. Harappans made faience, a sort of glass which was used in ornamental. They melted and forged a variety of objects from metals such as lead, silver, gold, and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Musky in South India in 1000 to 900 BC and Hastinapur and Taxila in North India, that is 1000 to 200 BC. Glass and glaze were colored by addition of coloring agents like metal oxides. Copper metallurgy in India dates back to the beginning of Chalcolithic cultures in the subcontinent. There are much archaeological evidences to support the view that technologies for extraction of copper and iron were developed indigenously. According to Rigveda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BC. The golden gloss of the black polished ware of northern India could not be replicated, and it is still a chemical mystery. These wares indicate the mastery with which kiln temperature could be controlled. Kautilya's Arthashastra describes the production of salt from sea. A vast number of statements and material described in the ancient Vedic literature can be shown to agree with modern scientific findings. Copper utensils, iron, gold, silver ornaments, and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Sushruta Samahita explains the importance of alkalis. The Charaka Samahita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc. The sulfates of copper, zinc, and iron are the carbonates of lead and iron. Rasopnishada describes the preparation of gunpowder mixture. Tamil texts also describe the preparation of fireworks using sulfur charcoal, saltpetre, that is potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was a reputed chemist, an alchemist, and a metallurgist. His work Ras Ratnakar deals with the formulation of mercury compounds. He has also discussed methods for the extraction of metals like gold, silver, tin, and copper. A book Rasarnavam appeared around 800 CE. It discusses the uses of various furnaces, ovens, and crucibles for different purposes. It describes the method by which metal could be identified by flame color. Chakrapani discovered mercury sulfide. The credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soap. Indians began making soap in the 18th century CE. Oil of Iranda and seeds of mahua plant and calcium carbonate were used for making soap. The paintings found on the walls of Ajanta and Ellora, which look fresh even after ages, testify to a high level of science achieved in ancient India. Varahamir in Brihat Samhita is a sort of encyclopedia which was composed in the 6th century CE. It informs about the preparation of glutinous material to be applied on walls and roof of houses and temples. It was prepared entirely from extracts of various plants, fruits, seeds, and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to test such material scientifically and assess them for use. A number of classical texts like Arthveda mention some dye stuff. The material used were turmeric, madar, sunflower, orpiment, cochineal, and lac. Some other substances having tinting property were Camplesia, Patanga, and Jatuka. Varahamihir Brihat Samhita gives references to perfumes and cosmetics. Recipes for hair drying were made from plants like indigo and minerals like iron tar, black iron or steel, and acidic extracts of sour rice gruel. Gandhayukli describes recipes for making scents, mouth perfumes, bath powders, incense, and talcum powder. Paper was known to India in the 17th century, as account of Chinese traveler I Tsin describes. Excavation at Takshila indicate that ink was used in India from the 4th century. Colors of ink were made from chalk, red lead, and minima. It seems that the process of fermentation was well known to Indians. Vedas and Kautilya's Arthashastra mention about many types of liquors. Charaka Samhita also mentions ingredients such as barks of plants, stem, flowers, leaves, wood, cereals, fruits, and sugarcane for making aswas. The concept that matter is ultimately made of indivisible building blocks appeared in India a few centuries BCE as a part of philosophical speculations. Acharya Kanda, born in 600 BCE, originally known by the name Kashyap, was the first proponent of the atomic theory. He formulated the theory of very small indivisible particles, which he named Parmanu, comparable to atoms. He authored the text Vaishika Sutras. According to him, all substances are aggregated form of smaller units called atoms, Parmanu, which are eternal, indestructible, spherical, suprasensible, and in motion in the original state. He explained that this individual entity cannot be sensed through any human organ. Kanda added that there are variety of atoms that are as different as the different classes of substances. He said these Parmanu could form pairs or triplets. Among other combinations and unseen forces causes interactions between them. He conceptualized this theory around 2500 years before John Dalton, 1766 to 1844. Charaka Samhita is the oldest Ayurvedic epic of India. It describes the treatment of diseases. The concept of reduction of particle size of metals is clearly discussed in Charaka Samhita. Extreme reduction of particle size is termed as nanotechnology. Charaka Samhita describes the use of bhasma of metals in the treatment of ailments. Nowadays, it has been proved that bhasmas have nanoparticles of metals. After the decline of alchemy, iatrochemistry reached a steady state, but it too declined due to the introduction and practice of Western medical system in the 20th century. During this period of stagnation, pharmaceutical industry based on Ayurveda continued to exist, but it too declined gradually. It took about 100 to 150 years for Indians to learn and adopt new techniques. During this time, foreign products poured in. As a result, indigenous traditional techniques gradually declined. Modern science appeared in Indian scene in the later part of the 19th century. By the mid-19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, you have learned that chemistry deals with the composition, structure, properties and interaction of matter and is of much use to human beings in daily life. These aspects can be best described and understood in terms of basic constituents of matter that are atoms and molecules. That is why chemistry is also called the science of atoms and molecules. Can we see, weigh and perceive these entities? Is it possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and the number of these particles? We will get the answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical values with suitable units. 1.1 Importance of Chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain and operation of computer, production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new material. Chemistry contributes in a big way to the national economy. It also plays an important role in meeting human needs for food, healthcare products, and other material aimed at improving the quality of life. This is exemplified by the large-scale production of a variety of fertilizers, improved variety of pesticides and insecticides. Chemistry provides methods for the isolation of life-saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug AZT, that is azithromycin, is used for helping its patient. Chemistry contributes to a large extent in the development and growth of nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new material having a specific magnetic, electrical and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymers, metals, etc. These industries contribute in a big way to the economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants like CFCs, chlorofluorocarbons, responsible for ozone depletion in the stratosphere, have been successfully synthesized. However, many big environmental problems continue to matters of grave concern to the chemist. One such problem is the management of the greenhouse gases like methane, carbon dioxide, etc. Understanding of biochemical processes, uses of enzymes for large-scale production of chemicals, and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2 Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies a space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of the states of matter which you learned in your previous classes. 1.2.1 States of matter. You are aware that matter can exist in three physical states, by solid, liquid and gas. The constituent particles of matter in these three states can be represented as shown in figure 1.1. Particles are held very close to each other in solids in an orderly fashion that there is not much freedom of movement. In liquids, the particles are close to each other but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid states, and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibits the following characteristics. Number 1. Solids have definite volume and definite shape. Number 2. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. Number 3. Gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. On heating, a solid usually changes to a liquid and the liquid on further heating changes to a gas. In the reverse process, a gas on cooling liquefies to the liquid and the liquid on further cooling freezes to the solid. 1.2.2 Classification of matter. In class 9th, chapter 2, you have learned that at the macroscopic or bulk level, matter can be classified as mixture or pure substance. These can be further subdivided as shown in figure 1.2. When all constituent particles of a substance are same in chemical nature, it is said to be a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substances which may be present in it any ratio. Hence, their composition is variable. Pure substances forming mixture are called its components. Many of the substances present around you are mixtures. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout the bulk of the mixture and its composition is uniform throughout. Sugar, solution and air are the example of homogeneous mixture. In contrast to this, in heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixtures of salt and sugars, grains and pulses along with some dirt, often stone pieces, are heterogeneous mixtures. You can think of many more examples of mixtures which you come across in the daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods such as simple handpicking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixtures. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water and glucose are some examples of pure substances. Glucose contains carbon, hydrogen and oxygen in a fixed ratio and its particles are of same composition. Hence, like all other pure substances, glucose has a fixed composition. Also, its constituents carbon, hydrogen and oxygen cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules from the previous classes. However, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. Their all atoms are one type. However, the atoms of different elements are different in nature. Some elements such as sodium or copper contains atoms as their constituent particles, whereas in some others the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen, oxygen Gases consist of molecules in which two atoms combine to give their respective molecules. This is illustrated in figure 1.3. When two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, the constituents of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Example of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in figure 1.4. Note that a water molecule comprises two hydrogen and one oxygen atom. Similarly, a molecule of carbon dioxide contains two oxygen atoms combined with one carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compound formed by either their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combustion, but water is used as a fire extinguisher. 1.3 Properties of matter and their measurement. 1.3.1 Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with acids and bases. Physical properties can be measured or observed without changing the identity or the composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The examples of chemical properties are characteristic reactions of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. 1.3.2 Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Any quantitative observation of measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 meter. Here 6 is the number and m denotes meter, the unit in which the length is measured. Earlier, two different systems of measurement, that is the English system and the metric system, were being used in different parts of the world. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Late need of common standard system was felt by the scientific community. Such a system was established in 1960 and is discussed in detail below. 1.3.3 The International System of Units, SI. The International System of Units was established by the 11th General Conference on Weights and Measures, CGPM, from Conference General des Poids et Mesures. The CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. The SI system has 7 base units and they are listed in table 1.1. These units pertain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. The definitions of the SI basic units are given in table 1.2. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. These prefixes are listed in table 1.3. Let us now quickly go through the some quantities which you will be often using in this book. 1.3.4 Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. You should be careful in using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. The SI unit of mass as given in table 1.1 is kilogram. However, its fraction named as gram, 1 kilogram is equals to 1000 gram, is used in laboratories due to the smaller amounts of chemical used in chemical reaction. 1.3.5 volume. Volume is the amount of space occupied by a substance. It has the units of length to the power cube. So in SI system, volume has units of meter cube, but again in chemistry laboratories, smaller volumes are used, hence volume is often denoted in centimeter cube or decimeter cube units. A common unit liter, which is not an SI unit, is used for measurement of volume of liquids. 1 liter is equals to 1000 ml, 1000 centimeter cube is equals to 1 dm cube. In the laboratory, the volume of liquids or solution can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of a solution. These measuring devices are shown in figure 1.7. 1.3.6 Density. The two properties mass and volume discussed above are related as follows. Density is equals to mass upon volume. Density of a substance is its amount of mass per unit volume. So SI unit of density can be obtained as follows. SI unit of density is equals to SI unit of mass upon SI unit of volume. Kilogram per meter cube or kilogram meter to the power minus 3. This unit is quite large and a chemist often expresses density in gram centimeter cube, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. Temperature. There are three common scales to measure temperature: degree Celsius, Fahrenheit and Kelvin. Here Kelvin is the SI unit. The thermometers based on these scales are shown in figure 1.8. Generally, the thermometer with Celsius scale are calibrated from 0 degree to 100 degree, where these two temperatures are the freezing point and the boiling point of water respectively. The Fahrenheit scale is represented between 32 degree to 212 degree Fahrenheit. The temperatures on two scales are related to each other by the following relationship. Fahrenheit is equals to 9 by 5 degrees Celsius plus 32. The Kelvin scale is related to Celsius scale as follows. Kelvin K is equals to degree Celsius plus 273.15. It is interesting to note that temperature below 0 degree Celsius are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. 1.4 Uncertainty in measurement. Many a time in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently and present the data realistically with certainty to the extent possible. These ideas are discussed below in detail. 1.4.1 Scientific notation. As chemistry is the study of atoms and molecules which have extremely low masses and are present in extremely large numbers, a chemist has to deal with the numbers as large as 602, 200, 6 times 000 for the molecules of 2 gram of hydrogen gas, or as small as 0.23 times 0166 gram mass of hydrogen atom. Similarly, other constants such as Planck's constant, speed of light, charges on particles, etc. involve numbers of the above magnitude. It may look funny for a moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication or division with such numbers. You can write any two numbers of the above type and try any one of the operations you like to accept as challenge, and then you will really appreciate the difficulty in handling such numbers. This problem is solved by using scientific notation for such number, that is exponential notation, in which any number can be represented in the form n into 10 to the power n, where n is the exponent having positive or negative values and capital N is a number which varies between 1 to 9.999. Thus, we can write 232.508 as 2.32508 into 10 to the power 2 in scientific notation. Note that while writing it, the decimal had to be moved to the left by 2 places, and same is the exponent of 10 in the scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 to the power minus 4. Here the decimal has to be moved 4 places to the right and -4 is the exponent in the scientific notation. While performing mathematical operations on numbers expressed in the scientific notation, the following points are to be kept in mind: multiplication and division, addition and subtraction. 1.4.2 Significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitations of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using a platform balance and it comes out to be 9.4 gram. On measuring the mass of this object and an analytical balance, the mass obtained is 9.4213 gram. The mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. Therefore, digit 4 placed after decimal in the measurement by platform balance is uncertain. The uncertainty in the experimental or the calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus 1 which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Thus, if we write a result as 11.2 ml, we say that 11 is certain and 2 is uncertain, and thus uncertainty would be plus minus 1 in the last digit. Unless otherwise stated, an uncertainty of plus minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. Number 1. All non-zero digits are significant. For example, in 285 cm there are 3 significant figures and in 0.25 ml there are 2 significant figures. Number 2. Zeros preceding to first non-zero digit are non-significant. Such zero indicates the position of decimal point. The 0.03 has 1 significant figure and 0.0052 has 2 significant figures. Number 3. Zeros between the two non-zero digits are significant. Thus 2.005 has 4 significant figures. Number 4. Zeros at the end or right of a number are significant provided they are on the right side of the decimal point. Number 5. Counting the numbers of objects, for example 2 balls or 20 eggs, have infinite significant figures as these are exact numbers and can be represented by writing infinite number of 0 after placing a decimal. In numbers written in scientific notation, all digits are significant. However, one would always like the results to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurements for the same quantity. However, accuracy is the agreement of a particular value to the true value of the result. For example, if the true value for a result is 2 gram and student A takes 2 measurements and reports the result as 1.95 gram and 1.93 gram, these values are precise as they are close to each other but are not accurate. Another student B repeats the experiments and obtains 1.94 and 2.05 gram as the result for 2 measurements. These observations are neither precise nor accurate. Multiplication and division of significant figures. In these operations, the result must be reported with no more significant figures in the measurement with this few significant figures, while limiting the result to the required number of significant figures as done in the above mathematical operations. One has to keep in mind the following points for rounding off all the numbers. Number 1. If the rightmost digits to be removed is more than 5, the preceding number is increased by 1. If the rightmost digit to be removed is less than 5, the preceding number is not changed. If the rightmost digit is to be removed as 5, then the preceding number is not changed. If it is an even number but it is increased by 1 of its an odd number. 1.4.3 Dimensional analysis. Often while calculating there is a need to convert units from one system to the other. The method used to accomplish this is called factor labeled method or unit factor method or dimensional analysis. This is illustrated below. 1.5 Laws of chemical combinations. The combination of elements to form compounds is governed by the following 5 basic laws. Number 1. Law of conservation of mass. This law was put forth by Antoine Lavoisier in 1789. He performed careful experimental studies for combustion reactions and reached to the conclusion that in all physical and chemical changes there is no net change in mass during the process. Hence he reached to the conclusion that matter can neither be created nor destroyed. This is called law of conservation of mass. This law formed the basis for several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactants and products and carefully planned experiments performed by Lavoisier. 1.5.2 Law of Definite Proportion. This law was given by French chemist Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. Proust worked with two samples of cupric carbonate, one of which was of natural origin and the other was synthetic. He found that the composition of elements present in it was same for both the samples as shown below. Thus he concluded that irrespective of the source, a given compound always contains same elements combined together in the same proportion by mass. The validity of this law has been confirmed by various experiments. It is sometimes also referred to as law of definite composition. Third law, law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if two elements can combine to form more than one compound, the masses of one element that combine with the fixed mass of the other element are in the ratio of small whole numbers. For example, hydrogen combines with oxygen to form two compounds, namely water and hydrogen peroxide. Number 4. Gay-Lussac's law of gaseous volume. This law was given by Gay-Lussac in 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Thus 100 ml of hydrogen combined with 50 ml of oxygen to give 100 ml of water vapor. Thus the volumes of hydrogen and oxygen which combine bear a simple ratio of 2:1. Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportions by volume. The law of definite proportions stated earlier was with respect to mass. The Gay-Lussac law was explained properly by the work of Avogadro in 1811. 1.5.5 Law, Avogadro's law. Fifth law, Avogadro's law. In 1811, Avogadro proposed that equal volumes of all gases at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules, which is quite understandable in present times. If we consider again the reaction of hydrogen and oxygen to produce water, we see that two volumes of hydrogen combine with one volume of oxygen to give two volumes of water without leaving any unreacted oxygen. Note that in the figure 1.9, page 16, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic. If hydrogen and oxygen were considered as diatomic as recognized now, then the above results are easily understandable. However, Dalton and others believed that atoms of the same kind cannot combine and molecules of the oxygen or hydrogen containing two atoms did not exist. Avogadro's proposal was published in the French journal De Physique. In spite of being correct, it did not gain much support. After about 50 years, in 1860, the first international conference on chemistry was held in Karlsruhe, Germany, to resolve various ideas. At the meeting, Stanislaw Cannizzaro presented a sketch of course of chemical philosophy, which emphasized on the importance of Avogadro's work. 1.6 Dalton's atomic theory. Although the origin of the idea that matters is composed of small indivisible particles called atomio dates back to the time of Democritus, a Greek philosopher, it again started emerging as a result of several experimental studies which led to the laws mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. Number 1. Matter consists of indivisible atoms. Number 2. All atoms of given element have identical properties including identical mass. Atoms of different elements differ in mass. Number 3. Compounds are formed when atoms of different elements combine in a fixed ratio. Number 4. Chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. Dalton's theory could explain the laws of chemical combination. However, it could not explain the laws of gaseous volumes. It could not provide the reason for combining of atoms, which was answered later by other scientists. 1.7 Atomic and molecular masses. After having some idea about the terms atoms and molecules, it is appropriate here to understand what do we mean by atomic and molecular masses. 1.7.1 Atomic mass. The atomic mass or the mass of an atom is actually very small because atoms are extremely small. Today we have sophisticated techniques, example mass spectrometry, for determining the atomic masses fairly accurately. But in the 19th century, scientists could determine the mass of one atom relative to another by experimental means, as has been mentioned earlier. Hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1, and other elements were assigned masses related to it. However, the present system of atomic masses is based on carbon-12 as the standard and has been agreed upon in 1961. Here, carbon-12 is one of the isotope of carbon and can be represented as 12 carbon in the system. 12 carbon is assigned as mass of exactly 12 atomic mass unit EMU, and masses of all other atoms are given relative to this standard. One atomic mass unit is defined as a mass exactly equal to 1/12 of the mass of one carbon-12 atom. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculations, we actually use average atomic masses of elements, which are explained below. 1.7.2 Average atomic mass. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, the average atomic mass of that element can be computed. For example, carbon has the following 3 isotopes with relative abundances and masses as shown against. Similarly, average atomic masses for other elements can be calculated in the periodic table of elements. The atomic masses mentioned for different elements actually represent their average atomic masses. 1.7.3 Molecular mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. For example, molecular mass of methane, which contains 1 carbon atom and 4 hydrogen atoms, can be obtained as follows. Molecular mass of methane is equals to 16.043 U. 1.7.4 Formula mass. Some substances such as sodium chloride do not contain discrete molecules as their constituent units. In such compounds, positive and negative entities are arranged in a 3-dimensional structure as shown in figure 1.10. It may be noted that in sodium chloride, one Na ion is surrounded by 6 chloride ion and vice versa. The formula such as NaCl is used to calculate the formula mass instead of molecular mass, as in the solid state sodium chloride does not exist as single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine, that is 58.5 U. 1.8 Mole concept and molar mass. Atoms and molecules are extremely small in size, and their numbers in even a small amount of any substance is really very large. To handle such large numbers, a unit of convenient magnitude is required. Just as we denote 1 dozen for 12 items, a score for 20 items, gross for 144 items, we use the idea of mole to count entities at the microscopic level. In a SI system, mole was introduced as 7th base quantity for the amount of a substance. The mole symbol mol is the SI unit of amount of substance. One mole contains exactly 6.022140076 into 10 to the power 23 elementary entities. This number is the fixed numerical value of the Avogadro constant Na, when expressed in the unit mole to the power -1, and is called the Avogadro number. The amount of substance symbol N of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, any other particle, or a specified group of particles. It may be emphasized that the mole of a substance always contains the same number of entities, no matter what the substance may be. In order to determine this number precisely, the mass of carbon-12 atom was determined by a mass spectrometer and found to be equal to 1.992648 into 10 to the power -23 gram. Knowing that 1 mole of carbon weighs 12 gram, the number of 12 atoms in it is equal to 12 gram per mole. This number of entities in 1 mole is so important that it is given a separate name and symbol. It is called Avogadro constant. or Avogadro number denoted by Na in honor of Amedeo Avogadro. To appreciate the largeness of this number, let us write it with all zeros without using any powers of 10. Having defined the mole, it is easier to know the mass of 1 mole of a substance or the other constituent entities. The mass of 1 mole of substance in grams is called its molar mass. The molar mass in grams is numerically equal to atomic molecular formula mass in U. Molar mass of water 18.02 gram per mole. Molar mass of sodium chloride 58.5 gram per mole. 1.9% composition. So far we were dealing with the number of entities present in a given sample, but many a time information regarding the percentage of a particular element present in a compound is required. Suppose an unknown or new compound is given to you. The first question you would ask, what is its formula, or what are its constituents and what ratio are they present in the given compound? For known compounds also, such information provides a check whether the given sample contains the same percentage of elements as present in a pure sample. In other words, one can check the purity of given sample by analyzing this data. Let us understand it by taking the example of water. Since water contains hydrogen and oxygen, the percentage composition of both these elements can be calculated as follows. Mass percentage of an element is equals to mass of that element in the compound into 100 upon molar mass of the compound. 1.9.1 Empirical formula for molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of a compound. If the mass percent of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can further be obtained if the molar mass is known. The following example illustrates this sequence. 1.10 Stoichiometric and Stoichiometry Calculations. The word stoichiometry is derived from two Greek words, stoichion and metron. Stoichiometry thus deals with the calculation of masses of the reactants and the products involved in a chemical reaction. Before understanding how to calculate the amounts of reactants required or the products produced in a chemical reaction, let us study what information is available from the balanced chemical equation of a given reaction. Let us consider the combustion of methane. A balanced equation for this reaction is as given below. CH4 plus 2O2 gives out CO2 plus 2H2O. Here methane and dioxygen are called reactants and carbon dioxide and water are called products. Note that all the reactants and the products are gases in the above reaction, and this has been indicated by letter in the brackets next to its formula. Similarly, in case of solids and liquids and are written S and L respectively. Thus, according to the above chemical reaction, 1 mole of CH4 reacts with 2 moles of O2 to give 1 mole of CO2 and 2 moles of H2O. 1 molecule of CH4 reacts with 2 molecules of O2 to give 1 molecule of CO2 and 2 molecules of H2O. Calculations you have to check from your book. 1.10 Limiting reagent. Many a time reactions are carried out with the amounts of reactants that are different than the amounts as required by a balanced chemical reaction. In such situations, one reactant is in more amount than the amount required by a balanced chemical reaction. The reactant which is present in the least amount gets consumed after some time, and after that further reaction does not take place, whatever be the amount of the other reactant. Hence the reactant which gets consumed first limits the amount of products formed and is therefore called limiting reagent. In performing stoichiometric calculation, this aspect is also to be kept in mind. 1.10.2 Reactions in solutions. A majority of reactions in the laboratories are carried out in solution. Therefore, it is important to understand as how the amount of substance is expressed when it is present in the solution. The concentration of solution or the amount of substance present in its given volume can be expressed in any of the following ways. Number 1. Mass percent or weight percent, mole fraction, molarity, molality. Let us now study each one of them in detail. Balancing a chemical equation you have to check from your book. All the examples you have to check from your book. Number 1. Mass percent. It is obtained by using the following reaction. Mass percent is equals to mass of solute upon mass of solution into 100. Number 2. Mole fraction. It is the ratio of number of moles of a particular component to the total number of moles of the solution. If a substance A dissolves in a substance B and their number of moles are Na and Nb respectively, then the mole fractions of A and B are given as mole fraction of A is equals to number of moles of A, number of moles upon number of moles of solution. Mole fraction of B is equals to number of moles of B upon number of moles of solutions. Number third, molarity. It is the most widely used unit and is denoted by capital M. It is defined as the number of moles of the solute in 1 liter of the solution. Thus, molarity is equals to number of moles of solute upon volume of solutions in liter. Number 4, molality. It is defined as the number of moles of solute present in 1 kg of solvent. It is denoted by small m. Thus, molality is equals to number of moles of solute upon mass of solvent in kg. Summary. Chemistry as we understand it today that it is not a very old discipline. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied the knowledge in various walks of life. The study of chemistry is very important as its domain encompasses every sphere of life. Chemists study the properties and structure of substances and the changes undergone by them. All substances contain matter which can exist in 3 states, solid, liquid or gas. The constituent particles are held in different ways in these states of matter and they exhibit their characteristic properties. Matter can also be classified into elements, compounds or mixtures. An element contains particles of only one type, which may be atoms or molecules. The compounds are formed where atoms of 2 or more elements combine in a fixed ratio to each other. Mixtures occur widely, and many of the substances present around us are mixtures. When the properties of a substance are studied, this measurement is inherent. The quantification of properties requires a system of measurement and units in which the quantities are to be expressed. Many systems of measurement exist, of which the English and the metric systems are widely used. The scientific community, however, has agreed to have a uniform common system throughout the world, which is abbreviated as SI unit, International System of Units. Since measurements involve recording of data, which are always associated with a certain amount of uncertainty, the proper handling of data obtained by measuring the quantities is very important. The measurements of quantities in chemistry are spread over a wide range of 10 to the power minus 31 to 10 to the power plus 23. Hence, a convenient system of expressing the numbers in scientific notation is used. The uncertainty is taken care by specifying the number of significant figures in which the observations are reported. The dimensional analysis helps to express the measured quantities in different systems of units. Hence, it is possible to interconvert the results from one system of units to another. The combination of different atoms is governed by basic laws of chemical combination, these being the law of conservation of mass, law of definite proportion. The combination of different atoms is governed by basic laws of chemical combination, these being the law of conservation of mass, law of definite proportions, law of multiple proportions, Galois laws of gaseous volumes and Avogadro law. All these laws led to the Dalton's atomic theory, which states that atoms are building blocks of matter. The atomic mass of an element is expressed relative to 12 carbon isotope of carbon, which has an extinct value of 12U. Usually, the atomic mass used for an element is the average atomic mass obtained by taking into account the natural abundance of different isotopes of that element. The molecular mass of a molecule is obtained by taking sum of the atomic masses of different atoms present in a molecule. The molecular formula can be calculated by determining the mass percent of different elements present in a compound and its molecular mass. The numbers of atoms, molecules or any other particles present in a given system are expressed in the terms of Avogadro constant 6.022 into 10 to the power 23. This is known as 1 mole, the respective particles or entities. Chemical reactions represent the chemical changes undergone by different elements and compounds. A balanced chemical equation provides a lots of information. The coefficient indicate the molar ratios and the respective number of particles taking part in a particular reaction. The quantitative study of the reactants required or the products formed is called stoichiometry. Using stoichiometric calculations, the amount of one or more reactant required to produce a particular amount of product can be determined and vice versa. The amount of substance present in a given volume of a solution is expressed in number of ways. Example, mass percent, mole fraction, molarity and molality. Chapter completed. Thank you so much.
Structure of atom. The existence of atoms has been proposed since the time of early Indian and Greek philosophers 400 BC, who were of the view that atoms are the fundamental building blocks of matter. According to them, the continuous subdivisions of matter would ultimately yield atoms which would not be further divisible. The word atom has been derived from the Greek word atomio, which means uncuttable or non-divisible. These earlier ideas were mere speculations and there was no way to test them experimentally. These ideas remained dormant for a very long time and were revived again by the scientists in 19th century. The atomic theory of matter was first proposed on firm scientific basis by John Dalton, a British school teacher, in 1808. His theory, called Dalton's atomic theory, regarded the atom as ultimate particle of matter. In this unit, we start with the experimental observations made by scientists towards the end of 19th and beginning of 20th century. These established that atoms can be further divided into subatomic particles, i.e. electrons, protons and neutrons, a concept very different from that of Dalton. The major problems before the scientists at that time were to account for the stability of atom after the discovery of subatomic particles, to compare the behavior of one element from other in terms of both physical and chemical properties, to explain the formation of different kinds of molecules by the combination of different atoms, and to understand the origin and nature of the characteristics of electromagnetic radiations absorbed or emitted by atoms. Dalton's atomic theory was able to explain the law of conservation of mass, law of constant composition, and law of multiple proportion very successfully. However, it failed to explain the results of many experiments. For example, it was known that substances like glass or ebonite, when rubbed with silk or fur, generate electricity. Many different kinds of subatomic particles were discovered in the 20th century. However, in this section, we will talk about only two particles, namely electron and proton. Discovery of electron. In 1830, Michael Faraday showed that if electricity is passed through a solution of an electrolyte, chemical reactions occurred at the electrodes, which resulted in the liberation and deposition of matter at the electrodes. He formulated certain laws which you will study in class 12. These results suggested the particular nature of electricity and insights into the structure of atom obtained from the experiments on electrical discharge through gases. Before we discuss these results, we need to keep in mind a basic rule regarding the behavior of charged particles. Like charges repel each other and unlike charges attract each other. In mid-1850s, many scientists, mainly Faraday, began to study electrical discharge in partially evacuated tubes known as cathode ray discharge tubes. It is depicted in figure 2.1. A cathode ray tube is made of glass containing two thin pieces of metals called electrodes sealed in it. The electrical discharge through the gases could be observed only at very low pressures and at very high voltages. The pressure of different gases could be adjusted by evacuation. When sufficiently high voltage is applied across the electrodes, current starts flowing through a stream of particles moving in the tube from the negative electrode to the positive electrode anode. These were called cathode ray or cathode ray particles. The flow of current from cathode to anode was further checked by making a hole in the anode and coating the tube behind the anode with phosphorescent material, zinc sulfide. When these rays, after passing through anode, strike the zinc sulfide coating, a bright spot on the coating is developed. Same things happens in a television set. The results of these experiments are summarized below. The cathode ray starts from cathode and moves towards the anode. Second, these rays themselves are not visible, but their behavior can be observed with the help of a certain kind of materials. fluorescent or phosphorescent, which glow when hit by them. Television picture tubes are cathode ray tubes, and television pictures result due to fluorescence on the television screen coated with certain fluorescent or phosphorescent materials. Third, in the absence of electrical or magnetic field, these rays travel in straight lines. Figure 2.2. Fourth, in the presence of electrical or magnetic field, the behavior of cathode rays are similar to that expected from negatively charged particles, suggesting that the cathode rays consist of negatively charged particles called electrons. Fifth, the characteristics of cathode rays, electrons, do not depend upon the material of electrodes and the nature of the gas present in the cathode ray tube. Thus, we can conclude that electrons are basic constituent of all atoms. Charge to mass ratio of electron. In 1897, British physicist J. Thomson measured the ratio of electrical charge E to the mass of electron Me by using cathode ray tube and applying electrical and magnetic field perpendicular to each other as well as to the path of electrons. Thomson argued that amount of deviation of the particles from their path in the presence of electrical or magnetic field depends upon 1. The magnitude of the negative charge on the particle. Greater the magnitude of the charge on the particle, greater is the interaction with the electric or magnetic field, and thus greater is the deflection. 2. The mass of the particle. Lighter the particle, greater the deflection. Third, the strength of the electrical or magnetic field. The deflection of electrons from its original path increases with the increase in voltage across electrodes, or the strength of the magnetic field. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. Similarly, when only magnetic field is applied, electrons strike the cathode ray tube point C. By carefully balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path followed as in the absence of electric or magnetic. By carefully balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path followed as in the absence of electric or magnetic field, and they hit the screen at point B. By carrying out accurate measurements on the amount of deflections observed by the electrons on the electric field strength or magnetic field strength, Thomson was able to determine the value of E by Me equals 1.75 into 10 raised to the power 11 C per kg, where Me is the mass of the electron in kg and E is the magnitude of the charge on the electron in coulomb. Since the electrons are negatively charged, the charge on electron is minus E. Charge on the electron. R.A. Millikan devised a method known as oil drop experiment to determine the charge on electrons. He found that the charge on the electron to be minus 1.6 raised to the power 10 minus 19 coulomb. The present accepted value of the electrical charge is minus 1.6022 into 10 raised to the power minus 19 coulomb. The mass of the electron Me was determined by combining these results with Thomson's value, which give 9 into 10 raised to the power minus 31 kg. Discovery of protons and neutrons. Electrical discharge carried out in the modified cathode ray tube led to the discovery of particles carrying positive charge, also known as canal rays. The characteristics of these positively charged particles are listed below. Unlike cathode rays, positively charged particles depend upon the nature of gas present in the cathode ray tube. These are simply the positively charged gaseous ions. Second, the charge to mass ratio of the particles is found to depend on the gas from which they originate. Some of the positively charged particles carry a multiple of the fundamental of electric charge. The behavior of these particles in the magnetic or electric field is opposite to that observed for electron or cathode rays. The smallest and lightest positive ion was obtained from hydrogen and was called proton. This positively charged particle was characterized in 1919. Later, a need was felt for the presence of electrically neutral particle as one of the constituent of atoms. These particles were discovered by Chadwick by bombarding a thin sheet of beryllium by alpha particles. When electrically neutral particles having a mass slightly greater than that of protons was emitted, he named these particles as neutrons. The important properties of these fundamental particles are given in Table 2.1. Atomic models. Observations obtained from the experiments mentioned in the previous sections have suggested that Dalton's indivisible atom is composed of subatomic particles carrying positive and negative charges. Different atomic models were proposed to explain the distribution of these charged particles in an atom. Although some of these models were not able to explain the stability of atoms, two of these models, proposed by J.J. Thomson and Ernst Rutherford, are discussed below. Thomson model of atom. J.J. Thomson in 1898 proposed that an atom possesses a spherical shape, radius approximately 10 raised to the power minus 10 meter, in which the positive charge is uniformly distributed. The electrons are embedded into it in such a manner as to give the most stable electrostatic arrangement. Many different names are given to this model, for example, plum pudding, raisin pudding, or watermelon. This model can be visualized as a pudding or watermelon of positive charge with plums or seeds embedded into it. An important feature of this model is that the mass of the atom is assumed to be uniformly distributed over the atom. Although this model was able to explain the overall neutrality of the atom but was not consistent with the results of later experiments. Thomson was awarded Nobel Prize for Physics in 1906 for his theoretical and experimental investigations on the conduction of electricity by gases. Rutherford's nuclear model of atom. Rutherford and his students Hans Geiger and Ernst Marsden bombarded very thin gold foil with alpha particles. Rutherford's famous alpha particle scattering experiment is represented in figure 2.15. A stream of high-energy alpha particles from a radioactive source was directed at a thin foil of gold metal. The thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever alpha particles struck that screen, a tiny flash of light was produced at that point. The results of scattering experiment were quite unexpected. According to Thomson model of atom, the mass of each gold atom in the foil should have been spread evenly. Alpha particles had enough energy to pass directly through such a uniform distribution of mass. It was expected that the particles would slow down and change direction only by small angles as they pass through the foil. It was observed that 1. Most of the alpha particles passed through the gold foil undeflected. Second, a small fraction of the alpha particles was deflected by small angles. Third, a very few alpha particles, almost 1 into 20,000, bounced back, that is, were deflected nearly 180 degrees. On the basis of the observations, Rutherford drew the following conclusions regarding the structure of atom. 1. Most of the space in atom is empty, as most of the alpha particles pass through the foil undeflected. Second, a few positively charged alpha particles were deflected. The deflection must be due to enormous repulsive force, showing that the positive charge of the atom is not spread throughout the atom as Thomson had presumed. The positive charge has to be concentrated in a very small volume that repelled and deflected the positively charged alpha particles. Calculations by Rutherford showed that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The radius of the atom is about 10 raised to the power minus 10 meter, while the nucleus is about 10 raised to the power minus 15 meter. One can appreciate this difference in size by realizing that if a cricket ball represents a nucleus, then the radius of atom would be about 5 kilometers. On the basis of above observations and conclusions, Rutherford proposed the nuclear model of atom after discovery of protons. According to this model, 1. The positive charge in most of the mass of the atom was densely concentrated in extremely small region. This very small region of the atom was called nucleus by Rutherford. The nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular paths called orbits. Thus, Rutherford's model of atom resembles the solar system, in which the nucleus plays the role of sun and the electrons that of revolving planets. Electrons and the nucleus are held together by electrostatic forces of attraction. Atomic number and mass number. The presence of positive charge on the nucleus is due to the protons in the nucleus. As established earlier, the charge on the proton is equal but opposite to that of electron. The number of protons present in the nucleus is equal to the atomic number Z. For example, the number of protons in hydrogen nucleus is 1, in sodium atom 11. Therefore, their atomic numbers are 1 and 11 respectively. In order to keep the electrical neutrality, the number of electrons in an atom is equal to the number of protons, atomic number Z. For example, number of electrons in hydrogen atom and sodium atom is 1 and 11 respectively. Z equals to number of protons in the nucleus of an atom equals to number of electrons in a neutral atom. While the positive charge of the nucleus is due to protons, the mass of the nucleus due to protons and neutrons. As discussed earlier, protons and neutrons present in the nucleus are collectively known as nucleons. The total number of the nucleons is termed as mass number of the atom. Mass number equals to number of protons plus number of neutrons. Isobars and isotopes. The composition of any atom can be represented by using the normal element symbol X, with superscript on the left hand side of the atomic number A and subscript Z on the left hand side of the atomic number. Isobars are the atoms with same mass number but different atomic number, for example C14 and N14. On the other hand, atoms with identical atomic number but different atomic mass are called isotopes. In other words, it is evident that difference between the isotopes is due to the presence of different number of neutrons present in the nucleus. For example, considering of hydrogen atom again, 99.985% of hydrogen atoms contain this isotope is called protium. Rest of the percentage of hydrogen atom contains two other isotopes. The one containing one proton and one neutron is called deuterium, and the other one possessing one proton and two neutrons is called tritium. The latter isotope is found in trace amounts on Earth. Other examples of commonly occurring isotopes are carbon atoms containing 6, 7, 8 neutrons besides 6 protons, chlorine atoms containing 18, 20 neutrons besides 17 protons. Lastly, an important point to mention regarding isotopes is that chemical properties of atoms are controlled by the number of electrons, which are determined by the number of protons in the nucleus. Number of neutrons present in the nucleus have very little effect on the chemical properties of an element. Therefore, all the isotopes of a given element show same chemical behavior. Drawbacks of Rutherford model. Rutherford nuclear model of an atom is like a small-scale solar system, with the nucleus playing the role of massive sun and the electrons being similar to the lighter particles. Further, the Coulomb force kq1 q2 upon r square, where q1 and q2 are the charges, r is the distance of separation of the charges, and k is the proportionality constant between electron nucleus is mathematically similar to gravitational force g m1 m2 upon r square, where m1 and m2 are the masses, r is the distance of separation of the masses, and g is the gravitational constant. When classical mechanics is applied to the solar system, it shows that planets describe well-defined orbits around the sun. The theory can also calculate precisely the planetary orbits, and these are in agreement with the experimental measurements. The similarity between the solar system and the nuclear model suggests that electrons should move around the nucleus in well-defined orbits. However, when a body is moving in an orbit, it undergoes acceleration. Even if the body is moving with a constant speed in an orbit, it must accelerate because of changing direction. So an electron in the nuclear model describing planet-like orbits is under acceleration. According to the electromagnetic theory of Maxwell, charged particles, when accelerated, should emit electromagnetic radiations. This feature does not exist for planets since they are uncharged. Therefore, an electron in orbit will emit radiation. The energy carried by radiation comes from the electronic motion. The orbit will thus continue to shrink. Calculations show that it should take an electron only 10 raised to the power minus 8 seconds to spiral into the nucleus. But this does not happen. Thus, the Rutherford model cannot explain the stability of an atom. If the motion of an electron is described on the basis of the classical mechanics and electromagnetic theory, you may ask that since the motion of electrons in orbits is leading to the instability of atoms, then why not consider electrons as stationary around the nucleus? If the electrons were stationary, electrostatic attraction between the dense nucleus and the electrons would pull the electrons towards the nucleus to form a miniature version of Thomson's model of atom. Another serious drawback of Rutherford model is that it says nothing about the electronic structure of atom, i.e., how the electrons are distributed around the nucleus and what are the energies of these electrons. Developments leading to the Bohr's model of atom. Historically, results observed from the studies of interactions of radiations with matter have proved immense information regarding the structure of atoms and molecules. Niels Bohr utilized these results to improve upon the model proposed by Rutherford. Two developments played a major role in the formulation of Bohr's model of atom. These were 1. Dual character of these electromagnetic radiation, which means that radiations possess both wave-like and particle-like properties, and 2. Experimental results regarding atomic spectra, which can be explained only by assuming quantized electronic energy levels in atoms. Wave nature of electromagnetic radiation. James Maxwell, 1870, was the first to give a comprehensive explanation about the interaction between the charged bodies and the behavior of electrical and magnetic fields on macroscopic level. He suggested that when electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the forms of waves called electromagnetic waves or electromagnetic radiation. Light is the form of radiation known from early days, and speculation about its nature dates back to remote ancient times. In earlier days, Newton light was supposed to be made of particles, corpuscles. It was the only in the 19th century when wave nature of light was established. Maxwell was again the first to reveal that light waves are associated with oscillating electric and magnetic character. Although electromagnetic wave motion is complex in nature, we will consider here only a few simple properties. 1. The oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other and both are perpendicular to the direction of propagation of the wave. Simplified picture of electromagnetic wave is shown in 2.6. 2. Unlike sound waves or water waves, electromagnetic waves do not require medium and can move in vacuum. It is now well established that there are many types of electromagnetic radiations which differ from one another in wavelength or frequency. These constitute what is called an electromagnetic spectrum. Different regions of the spectrum are identified by different names. Some examples are radio frequency regions, example 10.10 raised to the power 6 Hz, used for broadcasting. Microwave region around 10 raised to the power 10 Hz, used for radar. Infrared region around 10 raised to the power 13 Hz, used for heating. Ultraviolet region around 10 raised to the power 16 Hz, a component of sun's radiation. The small portion around 10 raised to the power 15 Hz is what is ordinarily called visible light. It is only this part which our eyes can see or detect. Special instruments are required to detect non-visible radiation. Different kinds of units are used to represent electromagnetic radiation. These radiations are characterized by the properties namely frequency and wavelength. The SI unit of frequency is Hertz. After Hendrik Hertz, it is defined as the number of waves that pass a given point in 1 second. Wavelength should have the units of length, and as you know, the SI unit of length is meter. Since electromagnetic radiation consists of different kinds of waves of much smaller wavelength, smaller units are used. Figure 2.7 shows various types of electromagnetic radiations which differ from one another in wavelengths and frequencies. In vacuum, all types of electromagnetic radiations, regardless of wavelength, travel at the same speed, i.e. 3 into 10 raised to the power 8 meter per second. This is called speed of light and is given the symbol c. The frequency, wavelength, and velocity of light c are related by the equation c equals to frequency into wavelength. The other commonly used quantity, especially in spectroscopy, is the wave number. It is defined as the number of wavelengths per unit length. Its units are reciprocal of wavelength unit, i.e. per meter. However, commonly used unit is per centimeter, which is not a SI unit. Particle nature of electromagnetic radiation, Planck's quantum theory. Some of the experimental phenomena, such as diffraction and interference, can be explained by the wave nature of the electromagnetic radiation. However, following are some of the observations which could not be explained with the help of even the electromagnetic theory of 19th century, known as classical physics. 1. The nature of emission of radiations from hot bodies, black body radiation, ejection of electrons from metal surface when radiation strikes it, photoelectric effect, variation of heat capacity of solids as function of temperature, line spectra of atoms with special reference to hydrogen. It is noteworthy that the first concrete explanation for the phenomena of black body radiation was given by Max Planck in 1900. This phenomena is given below. When solids are heated, they emit radiation over a wide range of wavelengths. For example, when an iron rod is heated in furnace, it first turns to dull red and then progressively becomes more and more red as the temperature increases. As this is heated further, the radiation emitted becomes white and then becomes blue as the temperature becomes very high. In terms of frequency, it means that the frequency of emitted radiation goes from a lower frequency to a higher frequency as the temperature increases. The red color lies in the lower frequency region, while blue color belongs to the higher frequency region of the electromagnetic spectrum. The ideal body which emits and absorbs radiations of all frequencies is called a black body, and the radiation emitted by such a body is called black body radiation. The exact frequency distribution of the emitted radiation, i.e. intensity versus frequency curve of the radiation from a black body, depends only on its temperature. At a given temperature, intensity of radiation emitted increases with decrease of wavelength, reaches a maximum value at a given wavelength, and then starts decreasing with further decrease of wavelength as shown in figure 2.8. The above experimental result cannot be explained satisfactorily on the basis of wave theory of light. Planck suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner. A belief popular at the time. Planck gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy E of a quantum radiation is proportional to its frequency and is expressed by equation E equals to h nu. The proportionality constant h is known as Planck's constant and has the value of 6.626 into 10 raised to the power minus 34 joules second. With this theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency or wavelength at different temperatures. Photoelectric effect. In 1887, H. Hertz performed a very interesting experiment in which electrons or electric current were ejected when certain metals, for example potassium, rubidium, cesium, etc., were exposed to a beam of light. The phenomena is called photoelectric effect. The results observed in this experiment were: 1. The electrons are ejected from the metal surface as soon as the beam of light strikes the surface, i.e., there is no time lag between the striking of light beam and the ejection of electrons from its metal surface. 2. The number of electrons ejected is proportional to the intensity or brightness of light. 3. For each metal, there is a characteristic minimum frequency, also known as threshold frequency, below which photoelectric effect is not observed. At frequency which is greater than threshold frequency, the ejected electrons come out with certain kinetic energy. The kinetic energies of these electrons increase with the increase of frequency of light used. All the above results could not be explained on the basis of laws of classical physics. According to latter, the energy content of the beam of light depends upon the brightness of the light. In other words, number of electrons ejected and kinetic energy associated with them should depend on the brightness of light. It has been observed that though the number of electrons ejected does depend upon the brightness of the light, the kinetic energy of the ejected electrons does not. For example, red light of any brightness may shine on a piece of potassium metal for hours, but no photoelectrons are ejected. But as soon as even a very weak yellow light shines on the potassium metal, the photoelectric effect is observed. The threshold frequency for potassium metal is 5 into 10 raised to power 14 Hz. Einstein was able to explain the photoelectric effect using Planck's quantum theory of electromagnetic radiation as a starting point. Shining a beam of light onto a metal surface can, therefore, be viewed as shooting a beam of particles, the photons. When a photon of sufficient energy strikes an electron in the atom of the metal, it transfers its energy instantaneously to the electron during the collision, and the electron is ejected without any time lag or delay. Greater the energy possessed by the photon, greater will be the transfer of energy to the electron, and greater the kinetic energy of the ejected electron. In other words, kinetic energy of the ejected electron is proportional to the frequency of the electromagnetic radiation. Since the striking photon has energy equals to h nu, and the minimum energy required to eject the electron is h nu naught, also called work function, then the difference in energy h nu minus h nu naught is transferred as the kinetic energy of the photoelectron. Following the conservation of energy principle, the kinetic energy of the ejected electron is given by equation 2.7, which equals h nu naught plus half mev square, where me is the mass of electron and v is the velocity with the ejected electron. Lastly, a more intense beam of light consists of larger number of photons. Consequently, the number of electrons ejected is also larger as compared to that in an experiment in which a beam of weaker intensity of light is employed. Dual behavior of electromagnetic radiation. The particle nature of light posed a dilemma for scientists. On the one hand, it could explain the black body radiation and photoelectric effect satisfactorily, but on the other hand, it was not consistent with the known wave behavior of light, which could account for the phenomena of interference and diffraction. The only way to resolve this dilemma was to accept the idea that light possesses both particle and wave-like properties, i.e., light has dual behavior. Depending on the experiment, we find that light behaves either as a wave or as a stream of particles. Whenever radiation interacts with matter, it displays particle-like properties in contrast to the wave-like properties, interference and diffraction, which it exhibits when it propagates. This concept was totally alien to the way the scientists thought about matter and radiation, and it took them a long time to become convinced of its validity. It turns out, as you shall see later, that some microscopic particles like electrons also exhibit this wave-particle duality. Evidence for the quantized electronic energy level atomic spectra. The speed of light depends upon the nature of the medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. It is observed that when a ray of white light is passed through a prism, the wave with shorter wavelength bends more than one with longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visible range, a ray of white light is spread out in a series of colored bands called spectrum. The light of red color, which has longest wavelength, is deviated the least, while the violet light, which has shortest wavelength, is deviated the most. The spectrum of white light that we can see ranges from violet at 7.50 into 10 raised to the power 14 Hz to red at 4 into 10 raised to the power 14 Hz. Such a spectrum is called continuous spectrum. Continuous because violet merges into blue, blue into green, and so on. A similar spectrum is produced when a rainbow forms in the sky. Remember that visible light is just a small portion of the electromagnetic radiation. When electromagnetic radiation interacts with matter, atoms, and molecules, may absorb energy and reach to a higher energy state. With higher energy, these are in an unstable state. For returning to the normal, more stable lower energy states, the atoms and molecules emit radiations in various regions of the electromagnetic spectrum. Emissions and absorption spectra. The spectrum of radiation emitted by substance that has absorbed energy is called an emission spectrum. Atoms, molecules, or ions that have absorbed radiation are said to be excited. To produce an emission spectrum, energy is supplied to a sample by heating it or irradiating it, and the wavelength or frequency of the radiation emitted as the sample gives up the absorbed energy is recorded. An absorption spectrum is like the photographic negative of an emission spectrum. A continuum of radiation is passed through a sample which absorbs radiation of certain wavelength. The missing wavelength, which corresponds to the radiation absorbed by the matter, leaves dark spaces in the bright continuous spectrum. The study of emission or absorption spectra is referred to as spectroscopy. The spectrum of the visible light, as discussed above, was continuous, as all wavelengths of the visible light are represented in the spectra. The emission of spectra of atoms in the gas phase, on the other hand, do not show a continuous spread of wavelength from red to violet. Rather, they emit light only at specific wavelengths with dark spaces between them. Such spectra are called line spectra or atomic spectra because the emitted radiation is identified by the appearance of bright lines in the spectra. Line emission spectra are of great interest in the study of electronic structure. Each element has a unique line emission spectrum. The characteristic lines in atomic spectra can be used in chemical analysis to identify unknown atoms in the same way as fingerprints are used to identify people. The exact matching of lines of the emission spectrum of the atoms of a known element with the lines from an unknown sample quickly establishes the identity of the latter. German chemist Robert Bunsen was one of the first investigators to use line spectra to identify elements. Elements like rubidium, cesium, thallium, indium, gallium, and scandium were discovered when the minerals were analyzed by spectroscopic methods. The element helium was discovered in the sun by spectroscopic method. Line spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the H2 molecules dissociate and the energetically excited hydrogen atom produced emit electromagnetic radiation of discrete frequency. The hydrogen spectrum consists of several series of lines named after the discoverers. Balmer showed in 1885 on the basis of experimental observation that if spectral lines are expressed in terms of wave number, then the visible lines of hydrogen spectrum obey the following formula. Wave number equals 109.677 1 upon 2 square minus 1 upon n square per centimeter, where n is an integer equal to or greater than 3. The series of lines described by this formula are called the Balmer series. The Balmer series of lines are the only lines in the hydrogen spectrum which appear in the visible region of the electromagnetic spectrum. The Swedish spectroscopist Johannes Rydberg noted that all series of lines in the hydrogen spectrum could be described by the following expressions. Wave number equals 109.677 1 upon n1 square minus 1 upon n2 square per centimeter, where n1 can be 1, 2 and so on, and n2 is n1 plus 1, n1 plus 2 and so on. The value 109.677 centimeter per is called Rydberg constant for hydrogen. The first 5 series of lines that correspond to n1 equals 1, 2, 3, 4, 5 are known as Lyman, Balmer, Paschen, Brackett and P1 series respectively. Table 2.3 shows the series of transitions in the hydrogen spectrum. Figure 2.11 shows the Lyman, Balmer, Paschen series of transitions for. Of all elements, hydrogen atom has the simplest line spectrum. Line spectrum becomes more and more complex for heavier atom. There are, however, certain features which are common to all line spectra, i.e. 1. Line spectrum of element is unique, and 2. There is regularity in the line spectrum of each element. The questions which arise are: what are the reasons for these similarities? Is it something to do with the electronic structure of atoms? These are the questions need to be answered. We shall find later that the answers to these questions provide the key in understanding electronic structure of these elements. Bohr's model for hydrogen atom. Niels Bohr was the first to explain quantitatively the general features of hydrogen atom structure and its spectrum. Though the theory is not the modern quantum mechanics, it can still be used to rationalize many points in the atomic structure and spectra. Bohr's model for hydrogen atom is based on the following postulates. 1. The electron in hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbits, stationary states or allowed energy states. These orbits are arranged concentrically around the nucleus. Second, the energy of an electron in the orbit does not change with time. However, the electron will move from a lower stationary state to a higher stationary state when required amount of energy is absorbed by the electron, or energy is emitted when electron moves from higher stationary state to lower stationary state. The energy change does not take place in a continuous manner. 3. The frequency of radiation absorbed or emitted when transition occurs between two stationary states that differ in energy by delta E is given by frequency equals delta E upon H equals E2 minus E1 upon H, where E1 and E2 are the energies of the lower and higher allowed energy states respectively. This expression is commonly known as Bohr's frequency rule. Fourth, the angular momentum of an electron in a given stationary state can be expressed as MEVR equals n h by 2 pi, where n is integer. Thus, an electron can move only in those orbits for which its angular momentum is integral multiple of h by 2 pi, that is, why only certain fixed of orbits are allowed. The details regarding the derivation of energies of the stationary states used by Bohr are quite complicated and will be discussed in higher classes. However, according to Bohr's theory of hydrogen atom, A. The stationary states of electrons are numbered 1, 2, 3. These integral numbers are known as principal quantum numbers. The radii of the stationary states are expressed as Rn equals n square A naught, where A naught is 52.9 picometer. Thus, the radius of the first stationary state, called Bohr's orbit, is 52.9 picometer. Normally, the electron in the hydrogen atom is found in the orbit that is n equals 1. As n increases, the value of R will increase. In other words, the electron will be present away from the nucleus. The most important property associated with the electron is the energy of the stationary state. It is given by expression En equals minus RH 1 upon n square, where RH is called Rydberg constant and its value is 2.18 into 10 raised to the power minus 18 joule. The energy of lowest state, also called as ground state, is E1 equals minus 2.18 into 10 raised to the power minus 18, 1 upon 1 square, which equals minus 2.18 into 10 raised to the power minus 18 joule. The energy of the stationary state for n equals 2 will be minus 0.545 into 10 raised to the power minus 18 joule. Figure 2.11 depicts the energy of different stationary states or energy levels of hydrogen atom. This representation is called an energy level diagram. When the electron is free from the influence of nucleus, the energy is taken as 0. The electron in this situation is associated with the stationary state of principal quantum number equals n equals infinity and is called as ionized hydrogen atom. When the electron is attracted by the nucleus and is present in orbit n, the energy is emitted and its energy is lowered. That is the reason for the presence of negative sign in equation 2.13 and depicts the stability relative to the reference state of zero energy and n equals infinity. Bohr's theory can also be applied to the ions containing only one electron, similar to that present in hydrogen atom. For example, He plus, Li2 plus, Be3 plus, and so on. The energies of the stationary states associated with these kinds of ion, also known as hydrogen-like species, are given by the expression En equals minus 2.18 into 10 raised to the power 18 Z square upon n square joules, and the radii by the expression Rn equals 52.9 n square upon Z picometer, where Z is the atomic number and has values 2, 3 for the helium and lithium atoms respectively. From the above equations, it is evident that the value of energy becomes more negative and that of radius becomes smaller with increase of Z. This means that electron will be tightly bound to the nucleus. E. It is also possible to calculate the velocities of electrons moving in these orbits, although the precise equation is not given here. Qualitatively, the magnitude of velocity of electrons increase with increase of positive charge in the nucleus and decrease with increase of principal quantum number. Explanation of line spectrum of hydrogen. Line spectrum observed in case of hydrogen atom, as mentioned in section 2.3.3, can be explained quantitatively using Bohr's model. According to assumption 2, radiation energy is observed if electron moves from the orbit of smaller principal quantum number to the orbit of higher principal quantum number, whereas the radiation energy is emitted if the electron moves from higher orbit to lower orbit. The energy gap between two orbits is given by equation 2.16. Delta E equals to EF minus EI. Combining, we get delta E upon minus RH upon NF square minus RH upon NI square, stand for initial orbits. We get the final equation as 2.18 into 10 raised to the power minus 18 joules, 1 upon n square I minus 1 upon n square F. The frequency associated with the absorption and emission of photon can be evaluated by using equations. Frequency equals delta E upon h equals RH upon h, 1 minus Ni square minus 1 upon Nf square, which equals 3.29 into 10 raised to the power 15, 1 upon Ni square minus 1 upon Nf square hertz. And in terms of wave number, it equals to 1.09677 into 10 raised to the power 7 upon bracket 1 upon Ni square minus 1 upon Nf square per meter. In case of absorption spectrum, Nf is greater than Ni and the term in the parenthesis is positive and energy is absorbed. On the other hand, in case of emission spectrum, Ni is greater than Nf, delta E is negative and energy is released. The expression is similar to the used by Rydberg, derived empirically using the experimental data available at that time. Further, each spectral line, whether in absorption or emission spectrum, can be associated with particular transition in hydrogen atom. In case of large number of hydrogen atoms, different possible transitions can be observed and thus leading to large number of spectral lines. The brightness or intensity of spectral lines depend upon the number of photons of same wavelength of frequency absorbed or emitted. Limitations of Bohr's model. Bohr's model of hydrogen atom was no doubt an improvement over Rutherford's nuclear model, as it could account for the stability and line spectra of hydrogen atom and hydrogen-like ions. However, Bohr's model was too simple to account for the following points. 1. It fails to account for the finer details, doublet, that is two closely spaced lines, of the hydrogen atom spectrum, observed by using sophisticated spectroscopic techniques. This model is also unable to explain the spectrum of atoms other than hydrogen. For example, helium atom, which possesses only 2 electrons. Further, Bohr's theory was also unable to explain the spreading of spectral lines in the presence of magnetic field, which is called Zeeman effect, or splitting of spectral lines in electric field, which is known as Stark effect. 2. It could not explain the ability of atoms to form molecules by chemical bonds. In other words, taking into account of points mentioned above, one needs a better theory which can explain the salient features of the structure of complex atoms towards quantum mechanical model of the atom. In view of the shortcoming of the Bohr's model, attempts were made to develop a more suitable and general model for atoms. 2 important developments which contributed significantly to the formulation of such model were dual behavior of matter and Heisenberg uncertainty principle. Dual behavior of matter. The French physicist de Broglie in 1924 proposed that matter, like radiation, should also exhibit dual behavior, i.e. both particle and wave-like properties. This means that just as the photon has momentum as well as wavelength, electrons should also have momentum as well as wavelength. De Broglie from this analogy gave the following relation between wavelength and momentum of a material particle. Lambda equals to h by mv equals h by p, where m is the mass of particle, v is velocity, and p its momentum. De Broglie's prediction was confirmed experimentally when it was found that an electron beam undergoes diffraction, a phenomenon characteristic of waves. This fact has been put to use in making an electron microscope, which is based on the wave-like behavior of electrons, just as an ordinary microscope utilizes the wave nature of light. An electron microscope is a powerful tool in modern scientific research because it achieves magnification of about 15 million times. It needs to be noted that according to de Broglie, every object in motion has a wave character. The wavelengths associated with ordinary objects are so short because of their large masses that their wave properties cannot be detected. The wavelengths associated with electrons and other subatomic particles can, however, be detected experimentally. Results obtained from these following problems prove the points quantitatively. Heisenberg's uncertainty principle. Werner Heisenberg, a German physicist, in 1927 stated uncertainty principle, which is the consequence of dual behavior of matter and radiation. It states that it is impossible to determine simultaneously the exact position and exact momentum or velocity of an electron. Mathematically, it can be given by delta x equals delta px, which is greater than h by 4 pi, or delta x into delta v x greater than or equal to h by 4 pi m, where delta x is the uncertainty in position and delta px or delta vx is the uncertainty in momentum or velocity of the particle. If the position of the electron is known with the high degree of accuracy, then the velocity of the electron will be also uncertain. On the other hand, if the velocity of the electron is known precisely, then the position of the electron will be uncertain. Thus, if we carry out some physical measurements on the electron's position or velocity, the outcome will always depict a fuzzy or blurred picture. The uncertainty principle can be best understood with the help of an example. Suppose you are asked to measure the thickness of a sheet of paper with an unmarked meter stick. Obviously, the results obtained would be extremely inaccurate and meaningless. In order to obtain any accuracy, you should use an instrument graduated in units smaller than the thickness of a sheet of paper. Analogously, in order to determine the position of an electron, we must use a meter stick calibrated in units of smaller than the dimensions of an electron. To observe an electron, we can illuminate it with light or electromagnetic radiation. The light used must have a wavelength smaller than the dimensions of an electron. The high momentum photons of such light would change the energy of electrons by collisions. In this process, we no doubt would be able to calculate the positions of the electron, but we would know very little about the velocity of the electron after the collision. Significance of uncertainty principle. One of the important implications of the Heisenberg uncertainty principle is that it rules out existence of definite paths or trajectories of electrons and other similar particles. The trajectory of an object is determined by its location and velocity at various moments. If we know where a body is at a particular instant, and if we know its velocity and the forces acting on it at the instant, we can tell where the body would be sometime later. We therefore conclude that the position of an object and its velocity fix its trajectory. Since for a subatomic object such as an electron, it is not possible simultaneously to determine the position and velocity at any given instant to an arbitrary degree of precision, it is not possible to talk of the trajectory of an electron. The effect of Heisenberg uncertainty principle is significant only for motion of microscopic objects and is negligible for that of macroscopic objects. This can be seen from the following examples. If uncertainty principle is applied to an object of a mass, say about a milligram, then delta V into delta X equals approx 10 raised to power minus 28 meters squared per second. The value of delta V delta X obtained is extremely small and insignificant. Therefore, one may say that in dealing with milligram-sized or heavier objects, the associated uncertainties are hardly of any real consequence. In the case of a microscopic object like an electron, on the other hand, delta V dot delta X obtained is much larger, and such uncertainties are a real consequence. For example, for an electron whose mass is 9 raised to power into 10 raised to power minus 31 kg, according to Heisenberg's certainty principle, delta V dot delta X equals to 10 minus 4 meters squared per second. It therefore means that if one tries to find the exact location of an electron, say to an uncertainty of only 10 raised to power minus 8 meter, then uncertainty delta V in velocity would be approximately 10 raised to power 4 meter per second, which is so large that the classical picture of electrons moving in Bohr's orbits cannot hold good. It therefore means that the precise statements of the position and momentum of electrons have to be replaced by the statements of probability that the electron has at a given position and momentum. This is what happens in the quantum mechanical model of atom. Reasons for the failure of the Bohr model. One can now understand the reasons for the failure of the Bohr model. In Bohr model, an electron is regarded as a charged particle moving in well-defined circular orbits about the nucleus. The wave character of the electron is not considered in Bohr model. Further, an orbit is a clearly defined path, and this path can completely be defined only if both the position and the velocity of the electron are known exactly at the same time. This is not possible according to Heisenberg uncertainty principle. Bohr model of the hydrogen atom, therefore, not only ignores dual behavior of matter but also contradicts Heisenberg uncertainty principle. In view of these inherent weaknesses in the Bohr model, there was no point in extending Bohr model to other atoms. In fact, an insight into the structure of the atom was needed, which could account for wave-particle duality of matter and be consistent with Heisenberg uncertainty principle. This came with the advent of quantum mechanics. Quantum mechanical model of atom. Classical mechanics, based on Newton's laws of motion, successfully describes the motion of all macroscopic objects such as falling stone, orbiting planets, etc., which have essentially a particle-like behavior as shown in the previous section. However, it fails when applied to microscopic objects like electrons, atoms, molecules, etc. This is mainly because of the fact that classical mechanics ignores the concept of dual behavior of matter, especially for subatomic particles and the uncertainty principle. The branch of science that takes into account this dual behavior of matter is called quantum mechanics. Quantum mechanics is a theoretical science that deals with the study of motion of the microscopic objects that have both observable wave-like and particle-like properties. It specifies the laws of motion that these objects obey. When quantum mechanics is applied to macroscopic objects, the results are the same as those from the classical mechanics. Quantum mechanics was developed independently in 1926 by Werner Heisenberg and Erwin Schrodinger. Here, however, we shall be discussing the quantum mechanics, which is based on the ideas of wave motion. The fundamental equation of quantum mechanics was developed by Schrodinger, and it won him the Nobel Prize in Physics in 1933. This equation, which incorporates wave-particle duality of matter as proposed by de Broglie, is quite complex, and knowledge of higher mathematics is needed to solve it. You will learn its solutions for different systems in higher classes. For a system such as an atom or a molecule whose energy does not change with time, the Schrodinger equation is written as H sigma equals E sigma, where H is a mathematical operator called Hamiltonian. Schrodinger gave a recipe of constructing this operator from the expression for the total energy of the system. The total energy of the system takes into account the total kinetic energies of all the subatomic particles, electrons, nuclei, attractive potential between the electrons and nuclei, and repulsive potential among the electrons and nuclei individually. Solution of this equation gives E and sigma, hydrogen atoms, and the Schrodinger equation. When Schrodinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave functions of the electron associated with each energy level. These quantized energy states and corresponding wave functions, which are characterized by a set of three quantum numbers, principal quantum number n, azimuthal quantum number L, and magnetic quantum number m, L, arise as a natural consequence in the solution of the Schrodinger equation. When an electron is in any energy state, the wave function corresponds to the energy state, contains all information about the electron. The wave function is a mathematical function whose value depends upon the coordinates of the electrons in the atom and does not carry any physical meaning. Such wave functions of the hydrogen or hydrogen-like species with one electron are called atomic orbitals. Such wave functions pertaining to one electron species are called one-electron systems. The probability of finding an electron at a point within an atom is proportional to square at that point. The quantum mechanical results of the hydrogen atom successfully predict all aspects of the hydrogen atom spectrum, including some phenomena that could not be explained by the Bohr model. Application of Schrodinger Equation to multi-electron atoms presents a difficulty. The Schrodinger equation cannot be solved exactly for a multi-electron atom. This difficulty can be overcome by using approximate methods. Such calculations with the aid of modern computers show orbitals in atoms other than hydrogen do not differ in any radical way from the hydrogen orbital discussed above. The principal difference lies in the consequence of increased nuclear charge. Because of this all, the orbitals are somewhat contracted. Further, as we shall see later, unlike orbitals of hydrogen or hydrogen-like species whose energy depends only on the quantum number n, the energies of the orbitals in multi-electron atoms depend on quantum number n and l. Orbitals and quantum numbers. A large number of orbitals are possible in an atom. Qualitatively, these orbitals can be distinguished by their size, shape, and orientation. An orbital of smaller size means there is no more chance of finding the electron near the nucleus. Similarly, shape and orientation mean there is more probability of finding the electron along certain directions than along others. Atomic orbitals are precisely distinguished by what are known as quantum numbers. Each orbital is designated by three quantum numbers labeled as n, l, and ml. The principal quantum number n is positive integer with the value of n equals 1, 2, 3. The principal quantum number determines the size and to large extent the energy of the orbital. For hydrogen atom and hydrogen-like species, energy and size of the orbital depends only on n. The principal quantum number also identifies the shell. With the increase in the value of n, the number of allowed orbital increases and are given by n square. All the orbitals of a given value of n constitute a single shell of atom and are represented by the following letters. Size of an orbital increases with the increase of principal quantum number n. In other words, the electron will be located away from the nucleus. Since energy is required in shifting away the negatively charged electrons from the positively charged nucleus, the energy of the orbital will increase with increase of n. Azimuthal quantum number L is also known as orbital angular momentum or subsidiary quantum number. It defines the three-dimensional shape of the orbital. For a given value of n, L can have n values ranging from 0 to n minus 1. That is, for a given value of n, the possible values of L are 0, 1, 2, so forth, and n minus 1. For example, when n equals to 1, value of L is only 0. For n equals to 2, the possible values can be 0 and 1. For n3, the possible values of L are 0 and 1 and 2. Each shell consists of one or more subshells or sublevels. The number of subshells in a principal shell is equal to the value of n. For example, in the first shell, there is only one subshell which corresponds to L equals to 0. There are two subshells in the second shell, there are three in the third shell, and so on. Each subshell is assigned azimuthal quantum number. Subshells corresponding to different values of L are represented by the following symbols. Table 2.4 shows the permissible values of L for a given principal quantum number and the corresponding subshell notation. Magnetic orbital quantum numbers ML give information about the spatial orientation of the orbital with respect to standard set of coordinate axes. For any subshell, 2l plus 1 values or ml are possible, and these values are given by ml equals minus l minus 1 minus l minus 2 0 1 l minus 2 l minus 1 l. Thus for L equals to 0, the only permitted value of ML0 is 1s orbital. For L1, M1 can be minus 1, 0 and plus 1 can be equal to 3p orbitals. For L equals to 2, ML equals to minus 2, minus 1, 0, plus 1 and plus 2. 5d orbitals. It should be noted that the values of ml are derived from L and the value of L are derived from N. Each orbital in an atom therefore is defined by a set of values for NL and ML. An orbital described by the quantum numbers is an orbital in the p subshell of the second shell. The following chart gives the relation between the subshells and the given number of orbitals associated with it. Electron spin S. The three quantum numbers labeling an atomic orbital can be used equally well to define its energy, shape, and orientation. But all these quantum numbers are not enough to explain the line spectra observed in the case of multi-electron atoms. That is, some of the lines actually occur in doublets, triplets. This suggests the presence of a few more energy levels than predicted by three quantum numbers. In 1925, George Heisenberg and Samuel Goldschmidt proposed the presence of the fourth quantum number known as electron spin quantum number ms. An electron spins around its own axis much in a similar way as Earth spins around its own axis while revolving around the Sun. In other words, an electron has, besides charge and mass, intrinsic spin angular quantum number. Spin angular momentum of the electron, a vector quantity, can have two orientations relative to the chosen axis. These two orientations are distinguished by the spin quantum numbers ms, which can take the value of plus half or minus half. These are called the two spin states of the electron and are normally represented by two arrows, spin up and spin down. Two electrons that have different ms values are said to have opposite spin. An orbital can not hold more than two electrons, and these two electrons should have opposite spins. To sum up, the four quantum numbers provide the following information. N defines the shell, determines the size of the orbital, and also to a large extent the energy of the orbital. There are n subshells in the nth shell. L identifies the subshell and determines the shape of the orbital. There are 2l plus 1 orbitals of each type in subshell, that is 1s orbital, 3p orbitals, and 5d orbitals per subshell. To some extent, L also determines the energy of the orbital in multi-electron atom. ML designates the orientation of the orbital. For a given value of L, ML has 2l plus 1 values, the same as the number of orbitals per subshell. It means that the number of orbitals is equal to the number of ways in which they are oriented. MS refers to the orientation of the spin of the electron. Shapes of atomic orbitals. The orbital wave function for an electron in an atom has no physical meaning. It is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of corresponding wave functions as a function of r are different, which gives plots for 1s and 2s orbital. According to the German physicist Max Born, the square of the wave function at a point given give the probability of density of the electron at the point. The variation as a function of r for 1s and 2s orbitals is given in figure 2.12b. Here again you may note that the curves for 1s and 2s orbitals are different. It may be noted that for 1s orbital, the probability density is maximum at the nucleus and it decreases sharply as you move away from it. On the other hand, for 2s orbital, the probability density first decreases sharply to the 0 and again starts increasing. After reaching a small maxima, it decreases again and approaches 0 as the value of r increases further. The region where this probability density function reduces to 0 is called nodal surfaces or simply nodes. In general, it has been found that ns orbital has n-1 nodes, that is, number of nodes increases with increase of principal quantum numbers n. In other words, the number of nodes of 2s is 1, 2 for 3s, and so on. These probability density variations can be visualized in terms of charge cloud diagrams. In these diagrams, the density of the dots in a region represent electron probability density in that region. Boundary surface diagrams of constant probability density for different orbitals can give a fairly good representation of the shapes of the orbitals. In this representation, a boundary surface or contour surface is drawn in space for an orbital on which the value of probability density is constant. In principle, many such boundary surfaces may be possible. However, for a given orbital, only that boundary surface diagram of a constant probability density is taken to be good representation of the shape of the orbital, which encloses a region or volume in which the probability of finding the electron is very high, say 90%. The boundary surface diagram for 1s and 2s orbitals are given in figure 2.13b. One may ask a question, why do we not draw a boundary surface diagram which bounds a region in which the probability of finding the electron is 100%? The answer to this question is that the probability density has always some value, howsoever small it may be at any finite distance from the nucleus. It is therefore not possible to draw a boundary surface diagram of a rigid size in which the probability of finding the electron is 100%. Boundary surface diagram for s orbital is actually a sphere centered on the nucleus. In 2 dimensions, this sphere looks like a circle. It encloses a region in which probability of finding the electron is about 90%. Thus, we see that 1s and 2s orbitals are spherical in shape. In reality, all the s orbitals are spherical symmetric. That is, the probability of finding the electron at a given distance is equal in all the directions. It is also observed that the size of the s orbital increases with increase in n, that is 4s greater than 3s greater than 2s greater than 1s, and the electron is located further away from the nucleus as the principal quantum number increases. Boundary surface diagrams for 3p orbitals L equals to 1 are shown in figure 2.14. In these diagrams, the nucleus is at the origin. Here, unlike s orbitals, the boundary surface diagrams are not spherical. Instead, each p orbital consists of 2 sections called lobes that are on either side of the plane that passes through the nucleus. The probability density of function is 0 on the plane where the two lobes touch each other. The size, shape, and energy of the 3 orbitals are identical. They differ, however, in the way the lobes are oriented. Since the lobes may be considered to lie along x, y, z axis, they are given the designations 2px, 2py, and 2pz. It should be understood, however, that there is no simple relation between the values of ml -1, 0, and +1 and the x, y, z directions. For our purpose, it is sufficient to remember that because there are 3 possible values of ml, there are therefore 3 p orbitals whose axes are mutually perpendicular. Like s orbitals, p orbitals increase in size and energy with increase in the principal quantum number, and hence the order of the energy and size of various p orbitals is 4p greater than 3p greater than 2p. Further, like s orbitals, the probability density functions of p orbital also pass through value 0. Besides, at 0 and infinite distance, as the distance from the nucleus increases, the number of nodes are given by n-2. That is, number of radial nodes is 1 for 3p orbital, 2 for 4p orbital, and so on. For L equals to 2, the orbital is known as d orbital, and the minimum value of principal quantum number n has to be 3. As for the value of L cannot be greater than n-1, there are 5 ml values, -2, -1, 0, +1, and +2 for L2, and thus there are 5 d orbitals. The boundary surface diagram of d orbital is shown in figure 2.15. The 5d orbitals are designated as dxy, dyz, dxz, dx square minus y square, and dz square. The shapes of the first 4d orbitals are similar to each other, whereas that of the fifth one, dz square, is different from others, but all 5 3d orbitals are equivalent in energy. The d orbitals for which n is greater than 3 also have shapes similar to 3d orbital but differ in energy and size. Besides the radial nodes, probability density function is 0. The probability density functions for the np and nd orbitals are 0 at the plane passing through the nucleus. For example, in case of pz orbital, xy plane is a nodal plane. In case of dxy orbital, there are two nodal planes passing through the origin and bisecting the xy plane containing z-axis. These are called angular nodes, and number of angular nodes are given by L, i.e. one angular node for p orbitals, two angular nodes for d orbitals, and so on. The total number of nodes are given by n-1, i.e. sum of L angular nodes and n-L-1 radial nodes. Energies of orbitals. The energy of an electron in a hydrogen atom is determined solely by the principal quantum number. Thus, the energy of the orbitals increases as follows, and is depicted in figure 2.16. Although the shapes of 2s and 2p orbitals are different, an electron has the same energy when it is in the 2s orbital as when it is present in 2p orbital. The orbitals having the same energy are called degenerate. The 1s orbital in a hydrogen atom, as said earlier, corresponds to the most stable condition and is called ground state, and an electron residing in this orbital is more strongly held by the nucleus. An electron in the 2s, 2p or higher orbitals in a hydrogen atom is an excited state. The energy of an electron in a multi-electron atom, unlike that of the hydrogen atom, depends not only on its principal quantum number but also on its azimuthal quantum number, that is, for a given principal quantum number S, PDF, all have different energies. The main reason for having different energies of the subshells is the mutual repulsion among the electrons in a multi-electron atoms. The only electrical interaction present in hydrogen atom is the attraction between negatively charged electron and the positively charged nucleus. In multi-electron atoms, besides the presence of attraction between the electron and nucleus, there are repulsion terms between every electron and other electrons present in the atom. Thus, the stability of an electron in multi-electron atom is because of the total attraction. Attractive interactions are more than the repulsive interactions. In general, the repulsive interactions of the electrons in the outer shell with the electrons in the inner shell are more important. On the other hand, the attractive interactions of an electron increases with increase of positive charge on the nucleus. Due to the presence of electrons in the inner shells, the electrons in the outer shell will not experience the full positive charge of the nucleus Ze. The effect will be lower due to the partial screening of positive charge on the nucleus by the inner shell electrons. This is known as the shielding of the outer shell electrons from the nucleus by the inner shell electrons, and the net positive charge experienced by the outer electrons is known as the effective nuclear charge, Z effective E. Despite the shielding of the outer electrons from the nucleus by the inner shell electrons, the attractive force experienced by outer shell electrons increases with increase of nuclear charge. In other words, the energy of interaction between the nucleus and the electron decreases with the increase of atomic number Z. Both the attractive and repulsive interactions depend upon the shell and shape of the orbital in which the electron is present. For example, electrons present in spherical shaped s orbital shields the outer electron from the nucleus more effectively as compared to electrons present in p orbital. Similarly, electrons present in p orbitals shield the outer electrons from the nucleus more than the electrons present in d orbitals, even though all these orbitals are present in the same shell. Further, within a shell, due to spherical shape of s orbital, the s orbital electron spends more time close to the nucleus in comparison to p orbital electron, which spends more time in the vicinity of nucleus in comparison to d orbital electron. In other words, for a given shell, the Z effective experienced by the electron decreases with increase in azimuthal quantum number, that is, the s orbital electron will be more tightly bound to the nucleus than p orbital electron, which in turn will be better tightly bound than the d orbital electron. The energy of electrons in s orbital will be lower, i.e. more negative than that of p orbital electron, which will have less energy than that of d orbital electron, and so on. Since the extent of shielding from the nucleus is different for electrons in different orbitals, it leads to splitting of energy levels within the same shell. That is, energy of electron in an orbital, as mentioned earlier, depends upon the values of n and l. Mathematically, the dependence of energies of orbitals on n and l are quite complicated, but one simple rule is that the lower the value of n plus l for an orbital, the lower is its energy. If two orbitals have the same value of n plus l, the orbital with lower value of n will have the lower energy. The table 2.5 illustrates that n plus L rule depicts the energy levels of multi-electron atoms. It may be noted that different subshells of a particular shell have different energy in case of multi-electron atoms. However, in a hydrogen atom, they have the same energy. Lastly, it may be mentioned here that energies of the orbitals in the same subshell decrease with increase in atomic number Z effective. For example, energy of 2s orbital of hydrogen atom is greater than the 2s orbital of lithium, and that of lithium is greater than that of sodium, and so on. Filling of orbitals in atoms. The filling of electrons into the orbitals of different atoms takes place according to Bohr principle, which is based on Pauli's exclusion principle, the Hunt rule of maximum multiplicity, and the relative energies of the orbital. Bohr principle. The word Bohr in German means building up. The building up of orbitals mean that filling up of orbitals with electrons. The principle states in the ground state of the atoms, the orbitals are filled in order of their increasing energies. In other words, electrons first occupy the lowest energy orbital available to them and enter into higher energy orbitals only after the lower energy orbitals are filled. The order in which the energies of the orbital increase, and hence the order in which the orbitals are filled, are as follows. The order may be remembered by using the method given in figure 2.17. Starting from the top, the direction of the arrows give the order of filling of orbitals, that is starting from right top to bottom left. Pauli's exclusion principle. The number of electrons to be filled in various orbitals is restricted by the exclusion principle given by the Austrian scientist Wolfgang Pauli. According to this principle, no two electrons in an atom can have the same set of 4 quantum numbers. Pauli exclusion principle can also be stated as only two electrons may exist in the same orbital, and these electrons must have opposite spin. This means that the two electrons can have the same value of 3 quantum numbers n, l, ml, but must have the opposite spin quantum number. The restriction imposed by Pauli's exclusion principle on the number of electrons in an orbital helps in calculating the capacity of electrons to be present in any subshell. For example, subshell 1s comprises of one orbital, and thus the maximum number of electrons present in 1s subshell can be 2 in PD subshells. The maximum number of electrons can be 6 and 10 and so on. This can be summed up as the maximum number of electrons in the shell with principal quantum number n is equal to 2n squared. Hund's rule of maximum multiplicity. This rule deals with the filling of electrons into the orbitals belonging to the same subshell, called degenerate orbitals. It states pairing of electrons in the orbitals belonging to the same subshell P, D, or F does not take place until each orbital belonging to that subshell has got one electron each, i.e. it is singly occupied. Since there are 3p, 5d, and 7f orbitals, therefore the pairing of electrons will start in the p, d, and f orbitals with the entry of 4th, 6th, and 8th electron respectively. It has been observed that half-filled and fully filled degenerate set of orbitals acquire extra stability due to the symmetry. Electronic configuration of atoms. The distribution of electrons into orbitals of an atom is called its electronic configuration. If one keeps in mind the basic rules which govern the filling of different atomic orbitals, the electronic configurations of different atoms can be written very easily. The electronic configuration of different atoms can be represented in two ways: SAPBDC notation or orbital diagrams. In the first notation, the subshell is represented by the respective letter symbol, and the number of electrons present in the subshell is depicted as the superscript. The similar subshell represented for different shells is differentiated by writing the principal quantum number before the respective subshell. In the second notation, each orbital of the subshell is represented by a box, and the electron is represented by an arrow, a positive spin, or a down arrow, a negative spin. The advantage of second notation over the first is that it represents all the four quantum numbers. The hydrogen atom has only one electron, which goes in the orbital with the lowest energy, namely 1s. The electronic configuration of the hydrogen atom is 1s1, meaning that it only has one electron in the 1s orbital. The second electron in helium can also occupy the 1s orbital. Its configuration is therefore 1s2. As mentioned above, the two electrons differ from each other with opposite spin, as can be seen from the orbital diagram below. The third electron of lithium is not allowed in the first 1s orbital because of Pauli's exclusion principle. It therefore takes the next available choice, namely the 2s orbital. The electronic configuration of Li of lithium is 1s square 2s1. The 2s orbital can accommodate one more electron. The configuration of beryllium atom is therefore 1s square 2s square. In the next six elements, boron, carbon, nitrogen, oxygen, and neon, 2p orbital gets progressively filled. This process is completed with the neon atom. The orbital picture of these elements can be represented as follows. The electronic configuration of the elements sodium to argon follow exactly the same pattern as the elements from lithium to neon, with the difference that the 3s and 3p orbitals are getting filled now. This process can be simplified if we represent the total number of electrons in the first two shells by the name of element neon. The electronic configuration of the elements from sodium to argon can be written as Na Ne3s1 or argon Ne3s square 3p6. The electrons in the completely filled shells are known as core electrons, and the electrons that are added to the electronic shell with the highest principal quantum numbers are called valence electrons. For example, the electrons in neon are the core electrons, and the electrons from sodium to argon are the valence electrons. In potassium and calcium, the 4s orbital, being lower in energy than 3d orbitals, is occupied by 1 and 2 electrons respectively. In potassium and calcium, the 4s orbitals, being lower in energy than the 3d orbitals, is occupied by 1 and 2 electrons respectively. A new pattern is followed, beginning with scandium. The 3d orbitals, being lower in energy than the 4p orbitals, is filled first. Consequently, in the next 10 elements, scandium, titanium, vanadium, chromium, magnesium, iron, cobalt, nickel, copper, and zinc, the 5 3d orbitals are progressively occupied. We may be puzzled by the fact that chromium and copper have 5 and 10 electrons in 3d orbitals rather than 4 and 9, as their positions would have indicated, with 2 electrons in the 4s orbital. The reason is that fully filled orbitals and half-filled orbitals have extra stability, that is lower energy. Thus P3p, 6p5, D10, F7, F14, etc. configurations are either half-filled or fully filled, are more stable. Chromium and copper therefore adopt the D5 and D10 configurations. With the saturation of the 3d orbitals, the filling of the 4p orbital starts at gallium and is completed at krypton. In the next 18 elements, from rubidium to xenon, the pattern of filling 5s, 4d and 3p orbitals are similar to that of 4s, 3d, 4p orbitals discussed above. Then comes the turn of 6s orbitals. In cesium and the barium, this orbital contains 1 and 2 electrons respectively. Then from the lanthanum to Mercury, the filling of electrons takes place in 4f 5d orbitals. After this, filling of 6p, then 7s, and finally 5f and 6d orbitals takes place. The element after uranium are all short-lived and all of them are produced artificially. The electronic configurations of known elements are tabulated in table 2.6. One may ask, what is the utility of knowing the electron configuration? The modern approach to the chemistry in fact depends almost entirely on electronic distribution to understand and explain chemical behavior. For example, questions like why two or more atoms combine to form molecules, why some elements are metals while others are non-metals, why elements like helium and argon are not reactive but elements like halogens are reactive, find simple explanation from the electronic configurations. These questions have no answer in Daltonian model of atom. A detailed understanding of the electronic structure of atom is therefore very essential for getting an insight into the various aspects of modern chemical knowledge. Stability of completely filled and half-filled subshells. The ground state electronic configuration of the atom of an element always corresponds to the state of the lowest total electronic energy. The electronic configurations of most of the atoms follow the basic rules. However, in certain elements such as copper or Ca, where the two subshells 4s and 3d differ slightly in their energies, an electron shifts from a subshell of lower energy to a subshell of higher energy, provided such a shift results in all orbitals of the subshell of higher energy getting either completely filled or half filled. The valence electron configuration of Cr and Cu therefore are 3d 5 4s1, 3d 10 4s1 respectively, and not 3d 4 4s2. It has been found that there is extra stability associated with these electronic configurations.
तो आज का चैप्टर है हमारा यूनिट 3 क्लासिफिकेशन ऑफ एलिमेंट्स एंड periodicity in properties. So बच्चों, this is only an audio book, so be specific, right? So चलिए टाइम बिना वेस्ट किए स्टार्ट करते हैं. The periodic table is arguably the most important concept in chemistry, both in principle and in practice. It is the everyday support for students. It suggests new avenues of research to professionals and it provides a succinct organization of the whole of chemistry. It is a remarkable demonstration of the fact that the chemical elements are not a random cluster of entities, but instead display trends and lie together in families. An awareness of the periodic table is essential to anyone who wishes to disentangle the world and see how it is built up from the fundamental building blocks of the chemistry, the chemical elements. These words are given by Glenn T. Seaborg. In this unit, we will study the historical development of the periodic table as it stands today and the modern periodic law. We will also learn how the periodic classification follows as a logical consequence of the electronic configuration of atoms. Finally, we shall examine some of the periodic trends in the physical and chemical properties of the elements. 3.1. Why do we need to classify elements? We know by now that the elements are the basic units of all types of matter. In 1800, only 31 elements were known. By 1865, the number of identified elements had more than doubled to 63. At present, 114 elements are known. Of them, the recently discovered elements are man-made. Efforts to synthesize new elements are continuing. With such a large number of elements, it is very difficult to study individually the chemistry of all these elements and their innumerable compounds individually. To ease out this problem, scientists searched for a systematic way to organize their knowledge by classifying the elements. Not only that, it would rationalize known chemical facts about elements, but even predict new ones for undertaking further study. 3.2. Genesis of periodic classification. Classification of elements into group and development of periodic law and periodic table are the consequences of systematizing the knowledge gained by a number of scientists through their observation and experiment. The German chemist Johann Dobereiner in early 1800 was the first to consider the idea of trends among properties of elements. By 1829, he noted a similarity among the physical and chemical properties of several groups of 3 elements, that is triads. In each case, he noticed that the middle element of each of the triads had an atomic weight about halfway between the atomic weight of the other two. Also, properties of the middle element were in between those of the two members, since Dobereiner relationship, referred to as the law of triads, seemed to work only for a few elements. It was dismissed as coincidence. The next reported attempt to classify element was made by French geologist A.E.B. de Cancortois in 1862. I hope कि मैंने इस name सही pronounce किया है. He arranged the then known elements in order of increasing atomic weights and made a cylindrical table of elements to display the periodic recurrence of properties. This also did not attract much attention. The English chemist John Alexander Newlands in 1865 propounded the law of octaves. He arranged the elements in increasing order of their atomic weights and noted that every eighth element had properties similar to the first element. The relationship was just like every eighth note that resembles the first in octaves of music. Newland's law of octaves seemed to be true only for elements up to calcium. Although his idea was not widely accepted at that time, he for his work was later awarded Davy Medal in 1887 by the Royal Society of London. The periodic law as we know it today owes its development to the Russian chemist Dmitry Mendeleev 1834 to 1907 and the German chemist Lothar Meyer 1830 to 1895. Working independently, both the chemists in 1869 proposed that on arranging elements in the increasing order of their atomic weights, similarities appear in physical and chemical properties at regular intervals. Lothar Meyer plotted the physical properties such as atomic volume, melting point, boiling point against atomic weight and obtained a periodically repeated pattern. Unlike Newland's, Lothar Meyer observed a change in length of that repeating pattern. By 1868, Lothar Meyer had developed a table of the elements that closely resembles the modern periodic table. However, his work was not published until after the work of Dmitry Mendeleev, the scientist who is generally credited with the development of the modern periodic table. While Dobereiner initiated the study of periodic relationship, it was Mendeleev who was responsible for publishing the periodic law of the first time. It states as follows: the properties of the elements are a periodic function of their atomic weights. Let me show you the both above tables. This is the table 3.1, Dobereiner's triads, and here three elements are mentioned: lithium, sodium and potassium. Table 3.2, that is Newland's octaves. Here you can see the elements and their atomic weight. Mendeleev arranged elements in horizontal rows and vertical columns of a table in order of their increasing atomic weights in such a way that the elements with similar properties occupied the same vertical column or group. Mendeleev's system of classifying elements was more elaborate than that of Lothar Meyer's. He fully recognized the significance of periodicity and used broader range of physical and chemical properties to classify the elements. In particular, Mendeleev relied on the similarities in the empirical formulas and properties of the compounds formed by the elements. He realized that some of elements did not fit in with his scheme of classification in the order of atomic weight was strictly followed. He ignored the order of atomic weights, thinking that the atomic measurements might be incorrect, and placed the element with similar properties together. For example, iodine with lower atomic weight than that of tellurium, that is of group 6, was placed in group 7th along with fluorine, chlorine, bromine because of similarities in properties. At the same time, keeping his primary aim of arranging the elements of similar properties in the same group, he proposed that some of elements were still undiscovered and therefore left several gaps in the table. For example, both gallium and germanium were unknown at the time. Mendeleev published his periodic table. He left the gap under aluminium and a gap under silicon and called these elements eka aluminium and eka silicon. Mendeleev predicted not only the existence of gallium and germanium but also described some of their general physical properties. These elements were discovered later. Some of the properties predicted by Mendeleev for these elements and those found experimentally are listed in Table 3.t. The boldness of Mendeleev's quantitative predictions and their eventual success made him and his periodic table famous. Mendeleev's periodic table, published in 1905, is shown in figure 3.1. Here you can see the table 3.3, Mendeleev's prediction for the elements Eka aluminium, that is gallium, and Eka silicon, that is germanium. Here you can see, and this is figure 3.1, that is Mendeleev's periodic table published earlier. Here you can see all the elements. 3.3 Modern periodic law and the present form of the periodic table. We must bear in mind that when Mendeleev developed his periodic table, chemists knew nothing about the internal structure of atom. However, the beginning of the 20th century witnessed profound developments in theories about subatomic particles. In 1913, the English physicist Henry Moseley observed regularities in the characteristic X-ray spectra of the elements. A plot of under root nu, where nu frequency of X-rays emitted, against atomic number, that is Z, gave a straight line and not plot of nu versus atomic mass. He thereby showed that the atomic number is a more fundamental property of an element than its atomic mass. Mendeleev's periodic law was therefore accordingly modified, and this is known as the modern periodic law. The physical and chemical properties of the elements are periodic functions of their atomic numbers. The periodic law revealed important analogies among the 94 naturally occurring elements, that is neptunium and plutonium, like actinium and protoactinium are also found in pitch blende and ore of uranium. It has stimulated renewed interest in inorganic chemistry and has carried into the present with the creation of artificially produced short-lived elements. You may recall that the atomic number is equal to the nuclear charge, that is number of protons or the number of electrons in neutral atom. It is then easy to visualize the significance of quantum number and electronic configuration in periodicity of elements. In fact, it is now recognized that the periodic law is essentially the consequence of periodic variation in electronic configuration, which indeed determine the physical and chemical properties of elements and their compounds. Numerous forms of periodic table have been devised from time to time. Some forms emphasize chemical reactions and valence, whereas others stress the electronic configuration of elements. A modern version, the so-called long form of the periodic table of the elements, that is in figure 3.2, I will show you, is the most convenient and widely used. The horizontal rows, which Mendeleev called series, are called periods, and the vertical columns groups. Elements having similar outer electronic configuration in their atoms are arranged in vertical columns, referred to as groups or families. According to the recommendation of International Union of Pure and Applied Chemistry, that is IUPAC, the groups are numbered from 1 to 18, replacing the older notation of group 1st A, 7th A, like this, up to the 7th B. And there are altogether 7 periods. The period number corresponds to the highest principal quantum number n of the elements in the period. The first period contains 2 elements. The subsequent period consists of 8, 8, 18, 18 and 32 elements respectively. The 7th period is incomplete and, like the 6th period, would have theoretical maximum on the basis of quantum numbers of 32 elements. In this form of periodic table, 14 elements of both 6th and 7th periods, that is lanthanoids and actinoids respectively, are placed in separate panels at the bottom. 3.4 Nomenclature of Elements with atomic numbers greater than 100. The naming of the new elements had been traditionally the privilege of the discoverer, and the suggested name was ratified by the IUPAC. In recent years, this has led to some controversy. The new elements with very high atomic numbers are so unstable that only minute quantities, sometimes only a few atoms of them, are obtained. Their synthesis and characterization therefore requires highly sophisticated, costly equipment and laboratory. Such work is carried out with competitive spirit only in some laboratories in the world. Scientists, before collecting the reliable data on the new element, at times get tempted to claim for its discovery. For example, both American and Soviet scientists claimed credit for discovering element 104. The Americans named it Rutherfordium, whereas Soviets named it Kurchatovium. To avoid such problems, the IUPAC has made the recommendation that until a new element discovered is proved and its name is officially recognized, a systematic nomenclature be derived directly from the atomic number of the elements using the numeral roots for 0 and number 1 to 9. These are shown in table 3.4. This is the table. The roots are put together in order of digits, which make the atomic number, and EM is added at the end. The IUPAC names for elements with Z above 100 are shown in table 3.5. This is the table 3.5. Let me show you the figure 3.2 also. Here you can see the periodic table. Affinite transition elements, that is lanthanide and actinoid series. Now this is the table 3.4 and this is table 3.5, nomenclature of elements with atomic number above 100. Thus the new element first gets a temporary name with symbol consisting of 3 letters. Later permanent name and symbol are given by a vote of IUPAC representatives from each country. The permanent name might reflect the country or the state of the country in which the element was discovered, or pay tribute to a notable scientist. As of now, elements with atomic numbers up to 118 have been discovered. Official names of all elements have been announced by IUPAC. 3.5 Electronic configuration of elements and the periodic table. In the preceding unit, we have learned that an electron in an atom is characterized by a set of 4 quantum numbers, and the principal quantum number n defines the main energy level known as shell. We have also studied about the filling of electrons into different subshells, also referred to as orbitals, SPDF, in an atom. The distribution of electrons into orbitals of an atom is called its electronic configuration. An element's location in the periodic table reflects the quantum numbers of the last orbital filled. In this section, we will observe a direct connection between the electronic configuration of the elements and the long form of the periodic table. A. Electronic configuration in periods. The period indicates the value of n for the outermost or valence shell. In other words, successive period in periodic table is associated with the filling of the next higher principal energy level, that is n is equals to 1, n is equals to 2, etc. It can be readily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. The first period, n is equals to 1, starts with the filling of the lowest level 1s and therefore has 2 elements, hydrogen 1s1 and helium 1s2. When the first shell K is completed, the second period n is equals to 2 starts with lithium and the third electron enters to the 2s orbital. The next element, beryllium, has 4 electrons and has the electronic configuration 1s2, 2s2. Starting from the next element, boron, the 2p orbitals are filled with electrons when the L shell is completed at neon, 2s2, 2p6. Thus, there are 8 elements in the second period. The third period, n is equals to 3, begins at sodium and the added electron enters a 3s orbital. Successive filling of 3s and 3p orbitals give rise to the third period of 8 elements from sodium to argon. The fourth period, n is equals to 4, starts at potassium and the added electrons fill up the 4s orbital. Now you may note that before the 4p orbital is filled, filling up to 3d orbitals becomes energetically favorable and we come across the so-called 3d transition series of elements. This starts from scandium, Z is equals to 21, and which has the electronic configuration 3d1, 4s2. The 3d orbitals are filled at zinc, that is Z30, with electronic configuration 3d10 4s2. The fourth period ends at krypton with the filling up to the 4p orbitals. Altogether, we have 18 elements in the fourth period. The fifth period and 5 beginning with rubidium. Rubidium is similar to the fourth period and contains the 4d transition series starting at yttrium Z39. This period ends at xenon with the filling up the 5p orbitals. The sixth period N6 contains 32 elements and successive electrons enter 6s, 4f, 5d and 6p orbitals in the order filling up of the 4f orbitals begins with cerium Z58 and ends at lutetium Z71 to give the 4f in a transition series which is called the lanthanoid series. The seventh period N7 is similar to the sixth period with the successive filling up the 7s, 5f, 6d and 7p orbitals and includes most of the man-made radioactive elements. This period will end at the element with atomic number 118, which would belong to the noble gas family. Filling up the 5f orbitals after actinium, that is Z89, gives the 5f inner transition series known as the actinoid series. The 4f and 5f inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. B. Group-wise electronic configuration. Elements in the same vertical column or group have similar valence shell electronic configuration. The same number of electrons in the outer orbitals and similar properties, for example, the group 1 elements, alkali metals, all have an s1 valence shell electronic configuration as shown below. Thus, it can be seen that the properties of an element have periodic dependence upon its atomic number and not on relative atomic mass. 3.6 Electronic configuration and types of elements SPDEF blocks. The Aufbau principle and the electronic configuration of atoms provide a theoretical foundation for the periodic classification. The elements in a vertical column of the periodic table constitute a group or family and exhibit similar chemical behavior. This similarity arises because these elements have the same number and same distribution of electrons in the outermost orbital. We can classify the elements into 4 blocks: S block, P block, D block and F block, depending on the type of atomic orbitals that are being filled with electrons. This is illustrated in figure 3.3. We notice 2 exceptions to this categorization. Strictly, helium belongs to the S block, but its positioning in the P block along with other group 18 elements is justified because it has a completely filled valence shell 1s2 and as a result exhibits properties characteristic of other noble gases. The other exception in hydrogen, it has only one s electron and hence can be placed in group 1 alkali metals. It can also gain an electron to achieve a noble gas arrangement and hence it can behave similar to a group 17, that is halogen family elements. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown in figure 3.2 and figure 3.3. We will briefly discuss the salient features of the 4 types of elements marked in the periodic table. More about these elements will be discussed later. During the description of their features, certain terminology has been used which has been classified in section 3.7. 3.6.1 The S block elements. The elements of group 1 and group 2, that is alkali metals and alkaline earth metals, which have NS1 and NS2 outermost electronic configuration, belong to the S block elements. They are all reactive metals with low ionization enthalpies. They lose the outermost electron readily to form 1 positive ion in the case of alkali metals or 2 positive ion in the case of alkaline earth metals. The metallic character and the reactivity increase as we go down the group. Because of high reactivity, they are never found pure in nature. The compounds of the S block elements, with the exception of those of lithium and beryllium, are predominantly ionic. 3.6.2 The P block elements. The P block elements comprise those belonging in group 13 to 18. And these together with the S block elements are called the representative elements or main group elements. The outermost electronic configuration varies from ns2np1 to ns2np6 in each period. At the end of each period is a noble gas element with a closed valence shell ns2np6 configuration. All the orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter this stable arrangement by the addition or removal of electron. The noble gases thus exhibit very low chemical reactivity. Preceding the noble gases family are two chemically important groups of nonmetals. They are the halogen group 17 and the chalcogens group 16. These two groups of elements have highly negative electron gain enthalpies and readily add 1 or 2 electrons respectively to attain the stable noble gas configuration. The non-metallic character increases as we move from left to right across a period, and metallic character increases as we go down the group. 3.6.3 The D block elements, transition elements. These are the elements of group 3 to 12 in the center of the periodic table. These are characterized by the filling of inner d orbitals by electrons and are therefore referred to as d block elements. These elements have the general outer electronic configuration, that is n-1 d 1 to 10 ns 0 to 2. They are all metals. They mostly formed colored ions, exhibit variable valence, that is oxidation states, paramagnetism, and oftenly used as catalyst. However, zinc, cadmium, Mhg, which have the electronic configuration n-1 d10 ns2, do not show most of the properties of transition elements. In a way, transition metals form a bridge between the chemically active metals of S block elements and the less active metal of group 13 and 14, and does take their familiar name transition elements. 3.6.4 The F block element, that is the inner transition elements. The two rows of elements at the bottom of the periodic table called the lanthanoids, that is CeZ58 to LuZ71, and the actinoids, that is ThZ90 to Lr, that is Z103, are characterized by the outer electronic configuration n-2 F1 to 14, n-1 D0 to 1, and ns2. The last electron added to each element is filled in f orbital. These two series of elements are hence called the inner transition elements, F block elements. They are all metals. Within each series, the properties of the elements are quite similar. The chemistry of the early actinoid is more complicated than the corresponding lanthanoids due to the large number of oxidation states possible for these actinoid elements. Actinoid elements are radioactive. Many of the actinoid elements have been made only in nanogram quantities or even less by nuclear reactions, and their chemistry is not fully studied. The elements after uranium are called transuranium elements. 3.6.5 Metals, nonmetals, and metalloids. In addition to displaying the classification of elements into S, P, D, and F blocks, figure 3.3 shows another broad classification of elements based on their properties. The elements can be divided into metals and nonmetals. Metal comprises more than 78% of all known elements and appear on the left side of periodic table. Metals are usually solid at room temperature. Mercury is an exception. Gallium and cesium also have very low melting points, that is 303 Kelvin and 302 Kelvin respectively. Metals usually have high melting and boiling points. They are good conductors of heat and electricity. They are malleable, can be flattened into thin sheets by hammering, and ductile, can be drawn into the wires. In contrast, nonmetals are located at the top right-hand side of the periodic table. In fact, in horizontal row, the property of elements change from metallic on the left to non-metallic on the right. Nonmetals are usually solids or gases at room temperature with low melting and boiling points. That is, boron and carbon are exception. They are poor conductors of heat and electricity. Most nonmetallic solids are brittle and are neither malleable nor ductile. The elements become more metallic as we go down a group. The non-metallic character increases as one goes from left to right across the periodic table. The change from metallic to non-metallic character is not abrupt as shown by the thick zigzag line in figure 3.3. The elements example silicon, germanium, arsenic, antimony, tellurium bordering this line and running diagonally across the periodic table shows properties that are characteristic of both metals and nonmetals. These elements are called semimetals or metalloids. 3.7 Periodic trends in properties of elements. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or move across a period in the periodic table. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in elements towards the middle of the table, and increases to a maximum in the group 17 non-metals. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group. Whereas within a group of non-metals, say halogens, reactivity decreases down the group. But why do the properties of elements follow these trends? And how can we explain periodicity? To answer these questions, we must look into the theories of atomic structure and properties of the atom. In the section, we shall discuss the periodic trends in certain physical and chemical properties and try to explain them in terms of number of electrons and energy levels. 3.7.1 Trends in Physical Properties. There are numerous physical properties of elements such as melting points, boiling points, heat of fusion, vaporization, energy of atomization, etc., which show periodic variation. However, we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and electronegativity. A. Atomic radius. You can very well imagine that finding the size of an atom is a lot more complicated than the measuring the radius of a ball. Do you know why? Firstly, because the size of an atom, that is 1.2 angstrom, that is 1.2 into 10 to the power minus 10 meter in radius, is very small. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary, the determination of the atomic size cannot be precise. In other words, there is no practical way by which the size of an individual atom can be measured. However, an estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. One practical approach to estimate the size of an atom of a non-metallic element is to measure the distance between the two atoms when they are bound together by a single bond in covalent molecule, and from this value, the covalent radius of the element can be calculated. For example, the bond distance in the chlorine molecule, that is Cl2, is 198 pm, and half the distance, 99 pm, that is picometer, is taken as the atomic radius of chlorine. For metals, we define the term metallic radius, which is taken as half the internuclear distance separating the metal cores in the metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 pm. Hence, the metallic radius of copper is assigned a value of 128 pm. For simplicity in this book, we use the term atomic radius to refer for both covalent or metallic radius depending on whether the element is a non-metal or a metal. Atomic radii can be measured by X-ray or other spectroscopic methods. The atomic radii of few elements are listed in table 3.6. Two trends are obvious. We can see the table atomic radii 3.6a and 3.6b. One is atomic radii pm down a family and one is atomic radii pm across the periods. We can explain these trends in terms of nuclear charge and energy level. The atomic size generally decreases across a period as illustrated in figure 3.4a for the elements of the second period. It is because within the period, the outer electrons are in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Within a family or vertical column of periodic table, the atomic radius increases regularly with atomic number as illustrated in figure 3.4b. For alkali metals and halogens, as we descend the groups, the principal quantum number increases and the valence electron are farther from the nucleus. This happens because the inner energy levels are filled with electrons which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. Note that the atomic radii of noble gases are not considered here. Being monoatomic, their non-bonded radii values are very large. In fact, radii of noble gas should be compared not with the covalent radii but with the van der Waals radii of other elements. See figure 3.4a and figure 3.4b. Both are variation of atomic radius with atomic number across the second period and variation of atomic radius with atomic number for alkali metals and halogens. B. Ionic radius. The removal of an electron from an atom results in the formation of cation, whereas the gain of an electron leads to an anion. The ionic radii can be estimated by measuring the distances between cations and anions in ionic crystals. In general, the ionic radii of element exhibit the same trend as the atomic radii. A cation is smaller than its parent's atom because it has fewer electrons, while its nuclear charge remains the same. The size of an anion will be larger than that of the parent atom because the addition of one or more electrons would result in increased repulsion among the electrons and a decrease in effective nuclear charge. For example, the ionic radius of fluoride ion is 136 pm, whereas the atomic radius of fluorine is only 64 pm. On the other hand, the atomic radius of sodium is 186 pm compared to the ionic radius of 95 pm for Na ion. When we find some atoms and ions which contain the same number of electrons, we call them isoelectronic species. For example, O2 negative, F negative, Na positive and Mg2 positive have the same number of electrons, that is 10. Their radii would be different because of their different nuclear charges. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. An ion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. C. Ionization enthalpy. A quantitative measure of the tendency of an element to lose electron is given by its ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom in its ground state. In other words, the first ionization enthalpy for an element X is the enthalpy change, that is delta H, for the reaction depicted in equation 3.1. Here you can see the equation. X gives out X positive plus E negative. The ionization enthalpy is expressed in unit of kilojoule per mole. We can define the second ionization enthalpy as the energy required to remove the second most loosely bound electron. It is the energy required to carry out the reaction shown in equation 3.2. It is X positive gives out X2 positive plus electron. Energy is always required to remove electron from an atom and hence ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from a positive charged ion than from a neutral atom. In the same way, the third ionization enthalpy will be higher than the second and so on. The term ionization enthalpy, if not qualified, is taken at the first ionization enthalpy. The first ionization enthalpies of elements having atomic numbers up to 60 are plotted in figure 3.5. Here is the figure. The periodicity of the graph is quite striking. You will find maxima at the noble gases which have closed electron shells and very stable electronic configurations. On the other hand, minima occur at the alkali metals and their low ionization enthalpies can be correlated with their high reactivity. In addition, you will notice two trends. The first ionization enthalpy generally increases as we go across a period and decreases as we descend in group. These trends are illustrated in figures 3.6a and 3.6b. I will show the diagram respectively for the elements of the second period and the first group of the periodic table. You will appreciate that the ionization enthalpy and atomic radius are closely related properties. To understand these trends, we have to consider two factors, that is the attraction of electrons towards the nucleus and second, the repulsion of electrons from each other. The effective nuclear charge experienced by the valence electron in an atom will be less than, first see the diagram, 3.6a and 3.6b. The actual charge in the nucleus because of shielding or screening of the valence electron from the nucleus by the intervening core electrons. For example, the 2s electron in lithium is shielded from the nucleus by the inner core of 1s electrons. As a result, the valence electron experiences a net positive charge which is less than the actual charge plus 3. In general, shielding is effective when the orbitals in the inner shells are completely filled. This situation occurs in the case of alkali metals, which have single outermost ns electron preceded by a noble gas electronic configuration. When we move from lithium to fluorine across the second period, successive electrons are added to orbitals in the same principal quantum level, and the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electrons to the nucleus. Thus, across a period, increasing nuclear charge outweighs the shielding. Consequently, the outermost electrons are held more and more tightly and the ionization enthalpy increases across a period. As we go down a group, the outermost electrons being increasingly farther from the nucleus. There is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, increase in shielding outweighs the increasing nuclear charge and the removal of the outermost electron requires less energy down a group. From figure 3.6a, you will also notice that the first ionization enthalpy of boron is slightly less than that of beryllium. Even though the former has a greater nuclear charge, when we consider the same principal quantum level, an s electron is attracted to the nucleus more than a p electron. In beryllium, the electron removed during the ionization is an s electron, whereas the electron removed during the ionization of boron is a p electron. The penetration of a 2s electron to the nucleus is more than that of a 2p electron. Hence, the 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. Therefore, it is easier to remove the 2p electron from boron compared to removal of a 2s electron from beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Another anomaly is the smallest first ionization enthalpy of oxygen compared to nitrogen. This arises because in the nitrogen atom, their 2p electrons resides in different atomic orbitals, that is Hund's rule, whereas in the oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbital, resulting in an increased electron-electron repulsion. Consequently, it is easier to remove the fourth 2p electron from oxygen than it is to remove one of the 3 2p electrons from the nitrogen. D. Electron gain enthalpy. When an electron is added to a natural gaseous atom X to convert it into a negative ion, the enthalpy change accompanying the process is defined as the electron gain enthalpy. Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form an ion as represented by equation 3.3. X gives a plus, electron gives out X negative. Depending on the element, the process of adding an electron to the atom can be either endothermic or exothermic. For many elements, energy is released when an electron is added to the atom and the electron gain enthalpy is negative. For example, group 17 elements have very high negative electron gain enthalpies because they can attain a stable noble gas electronic configuration by picking up an electron. On the other hand, noble gases have large positive electron gain enthalpies because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. It may be noted that electron gain enthalpies have large negative values towards the upper right of the periodic table preceding the noble gases. The variation in electron gain enthalpies of elements is less systematic than the ionization enthalpies. As a general rule, electron gain enthalpy become more negative with increase in the atomic number across a period. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom since the added electron on an average would be closer to the positively charged nucleus. We should also expect electron gain enthalpy to become less negative as we go down a group because the size of the atom increases and the added electron would be farther from the nucleus. This is generally the case. Table 3.7 you can see. I will show you. However, electron gain enthalpy of oxygen or fluorine is less negative than that of the succeeding element. This is because when an electron is added to oxygen or fluorine, the added electron goes to the smaller n is equals to 2 quantum level and suffers significant repulsion from the other electrons present in this level. For the n is equals to 3 quantum level, sulfur or chlorine, the added electron occupies a larger region of space and the electron-electron repulsion is much less. This is table 3.7, electron gain enthalpies of some main group elements. E. Electronegativity. A qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself is called electronegativity. Unlike ionization enthalpy and electron gain enthalpy, it is not a measurable quantity. However, a number of numerical scales of the electronegativity of elements via Pauling scale, Mulliken-Zaff scale, Allred-Rockow scale have been developed. The one which is the most widely used is the Pauling scale by Linus Pauling, an American scientist in 1922 assigned arbitrarily a value of 4 to fluorine, the element considered to have the greatest ability to attract electrons. Approximate values for the electronegativity of a few elements are given in table 3.8a. I will show you. The electronegativity of any given element is not constant. It varies depending on the element to which it is bound. Though it is not a measurable quantity, it does provide a means of predicting the nature of force that holds a pair of atoms together, a relationship that you will explore later. Electronegativity generally increases across a period from left to right, say from lithium to fluorine, and decreases down a group, say from fluorine to astatine. In the periodic table, how can these trends be explained? Can the electronegativity be related to atomic radii, which tend to decrease across each period from left to right but increase down each group? The attraction between the outer or valence electrons and the nucleus increases as the atomic radius decreases in a period. The electronegativity also increases on the same account. Electronegativity values decreases with the increase in atomic radii down a group. The trend is similar to that of ionization enthalpy. Knowing the relationship between the electronegativity and atomic radius, can you now visualize the relationship between the electronegativity and non-metallic properties? See this 3.7, the periodic trends of elements in the periodic table. Then 3.8a, electronegative value across the periods. Table 3.b, electronegativity values on Pauling scale down a family. Non-metallic elements have a strong tendency to gain electrons. Therefore, electronegativity is directly related to that non-metallic properties of elements. It can be further extended to say that electronegativity is inversely related to a metallic properties of elements. Thus, the increase in electronegativities across a period is accompanied by an increase in non-metallic properties or decrease in metallic properties of elements. Similarly, the decrease in electronegativity down a group is accompanied by a decrease in non-metallic properties of elements. All these periodic trends are summarized in figure 3.7. That is the figure 3.7. Now, 3.7.2 periodic trends in chemical properties. Most of the trends in chemical properties of elements such as diagonal relationships, inert pair effect, effect of lanthanoid contraction, etc. will be dealt with along the discussion of each group in later units. In this section, we shall study the periodicity of the valence state shown by elements and the anomalous properties of the second period elements from lithium to fluorine. A. Periodicity of valence or oxidation states. The valence is the most characteristic property of the elements and can be understood in terms of their electronic configuration. The valence of representative elements is usually, though not necessarily, equal to the number of electrons in the outermost orbitals and or equal to 8 minus the number of outermost electron as shown below. Nowadays, the term oxidation state is frequently used for valence. Consider the two oxygen-containing compounds OF2 and Na2O. The order of electronegativity of the three elements involved in these compounds is fluorine is greater than oxygen is greater than sodium. Each of the atoms of fluorine with outer electronic configuration 2s2 2p5 shares one electron with oxygen in the OF2 molecule. Being highest electronegative element, fluorine is given oxidation state -1. Since there are two fluorine atoms in this molecule, oxygen with outer electronic configuration 2s2 2p4 shares 2 electrons with fluorine atoms and nearby exhibits oxidation state +2. In Na2O, oxygen being more electronegative accepts 2 electrons, one more each of the two sodium atoms, and thus shows oxidation state -2. On the other hand, sodium with electronic configuration 3s1 loses 1 electron to oxygen and is given oxidation state +1. Thus, the oxidation state of an element in a particular compound can be defined as the charge acquired by atom on the basis of electronegative consideration from other atoms in the molecules. Some periodic trends observed in the valence of elements, hydrides and oxides, are shown in table 3.9. Other such periodic trends which occur in the chemical behavior of the elements are discussed elsewhere in this book. See the table 3.9. Periodic trends in valence of elements as shown by the formulas of their compounds. There are many elements which exhibit variable valence. This is particularly characteristic of transition elements and actinoids, which we shall study later. We analyze properties of second period elements. The first element of each of the group 1 and 2 and group 13 to 17 boron to fluorine it is, differs in many respects from the other members of their respective group. For example, lithium, unlike other alkali metals, and beryllium, unlike other alkaline earth metals, from compounds with pronounced covalent character. The other members of these groups predominantly form ionic compounds. In fact, the behavior of lithium and beryllium is more similar with the second element of the following group, that is magnesium and aluminium respectively. This sort of similarity is commonly referred to as diagonal relationship in the periodic properties. What are the reasons for the different chemical behavior of the first member of a group of elements in the S and P blocks compared to that of the subsequent members in the same group? The anomalous behavior is attributed to their small size, large charge, radius ratio, and high electronegativity of the elements. In addition, the first member of group has only 4 valence orbitals 2s and 2p available for bonding, whereas the second member of the groups have 9 valence orbitals 3s, 3p, 3d. As a consequence of this, the maximum covalency of the first member of each group is 4. Example, boron can only be formed Bf4 whole negative, whereas the other members of the groups can expand their valence shell to accommodate more than 4 pairs of electrons. Example, aluminium AlF6 whole 3 negative. Furthermore, the first member of p block elements displays greater ability to form p-pi multiple bonds to itself. Example, C-pi double bond C-pi, C triple bond C, N double bond N, and triple bond N. And to the other second period elements, example, C double bond O, C double bond N, C triple bond N, and double bond O, compared to subsequent members of the same group. 3.7.3 Periodic Trends and Chemical Reactivity. We have observed the periodic trends in certain fundamental properties such as atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and valence. We know by now that the periodicity is related to electronic configuration. That is, all chemical and physical properties are manifestation of the electronic configuration of elements. We shall now try to explore relationships between these fundamental properties of elements with their chemical reactivity. The atomic and ionic radii, as we know, generally decrease in a period from left to right. As a consequence, the ionization enthalpies generally increase, with some exceptions as outlined in section 3.7.1a, and electron gain enthalpies become more negative across a period. In other words, the ionization enthalpy of the extreme left element in a period is the least, and the electron gain enthalpy of the element on the extreme right is the highest negative. Note: noble gases having completely filled shells have rather positive electron gain enthalpy values. This results into high chemical reactivity at the two extremes and the lowest in the center. Thus, the maximum chemical reactivity at the extreme left among alkali metals is exhibited by the loss of an electron, leading to the formation of a cation, and at the extreme right among halogens shown by the gain of an electron forming an anion. This property can be related with reducing and oxidizing behavior of the elements, which you will learn later. However, here it can be directly related to the metallic and non-metallic character of elements. Thus, the metallic character of an element which is highest at the extremely left decreases, and the non-metallic character increases while moving from left to right across the period. The chemical reactivity of an element can be best shown by its reaction with oxygen and halogen. Here we shall consider the reaction of the elements with oxygen only. Elements on two extremes of a period easily combine with oxygen to form oxides. The normal oxide formed by the element on extreme left is the most basic, example Na2O, whereas that formed by the element on extreme right is the most acidic, example Cl2O7. Oxides of element in the center are amphoteric, example Al2O3, As2O3, or neutral, example are CO, NO, N2O, etc. Amphoteric oxides behave as acidic with bases and as basic with acids, whereas the neutral oxides have no acidic or basic properties. Among transition metals, that is 3D series, the change in atomic radii is much smaller as compared to those of representative elements across the period. The change in atomic radii is still smaller among inner transition metals, that is 4F series. The ionization enthalpies are intermediate between those of S and P blocks. As a consequence, they are less electropositive than group 1 and 2 metals. In a group, the increase in atomic and ionic radii with increase in atomic number generally results in a gradual decrease in ionization enthalpies and a regular decrease, that is with the exception in some third period elements as shown in section 3.71d. In electron gain enthalpies in the case of main group elements, thus the metallic character increases down the group and non-metallic character decreases. This trend can be related with their reducing and oxidizing property, which you will learn later. In the case of transition elements, however, a reverse trend is observed. This can be explained in terms of atomic size and ionization enthalpy. Summary: in this unit, you have studied the development of periodic law and periodic table. Mendeleev periodic table was based on atomic masses. Modern periodic table arranges the elements in the order of their atomic numbers in 7 horizontal rows, that is periods, and 18 vertical columns, that is groups of families. Atomic numbers in a period are consecutive, whereas in the group they can increase in a pattern. Elements of the same group have similar valence shell, electronic configuration, and therefore exhibit similar chemical properties. However, the elements of the same period have incrementally increasing number of electrons from left to right and therefore have different valencies. 4 types of elements can be recognized in the periodic table on the basis of their electronic configuration. These are S, P, D and F block elements. Hydrogen with 1 electron in the first S orbital occupies a unique position in the periodic table. Metals comprise more than 78% of known elements. Non-metals which are located at the top of the periodic table are less than 20 in number. Elements which lie at the border line between metals and non-metals, example silicon, germanium, arsenic, are called metalloids or semi-metals. Metallic character increases with increasing atomic number in a group, whereas decreases from left to right in a period. The physical and chemical properties of elements vary periodically with their atomic numbers. Periodic trends are observed in atomic sizes, ionization enthalpies, electron gain enthalpies, electronegativity, and valence. The atomic radii decrease while going from left to right in a period and increase with atomic number in a group. Ionization enthalpies generally increases across a period and decrease down a group. Electronegativity also shows a similar trend. Electron gain enthalpies in general become more negative across a period and less negative down a group. There is some periodicity in valence. For example, among representative elements, the valence is either equal to the number of electrons in the outermost orbitals or 8 minus this number. Chemical reactivity is the highest at two the extremes of a period and is lowest in the center. The reactivity on the left extreme of a period is because of the ease of electron loss or low ionization enthalpy. High reactive elements do not occur in nature in free states. They usually occur in the combined form. Oxides formed of the elements on the left are basic and the elements on the right are acidic in nature. Oxides of elements in the center are atmospheric or neutral. Chapter done. See you in the next chapter. So बच्चों आज मैं करने जा रही हूँ Unit 4 as per your request, Chemical Bonding and Molecular Structure. सो आज मैं ये ऑडियो बुक कंप्लीट करूंगी. कोशिश है कि एक ही वीडियो में आपकी मैं इस ऑडियो बुक को कंप्लीट कर दूं. सो आई विल ट्राई माय बेस्ट. आपसे एक रिक्वेस्ट है बच्चों, इस वीडियो को ज़्यादा से ज़्यादा शेयर करिए अपने फ्रेंड्स के साथ में ताकि उनको भी एग्जाम से पहले इसका बेनिफिट मिल सके. थैंक यू सो मच. तो चलिए टाइम बिना वेस्ट किए स्टार्ट करते हैं. यूनिट 4 केमिकल बॉन्डिंग एंड मॉलिक्यूलर स्ट्रक्चर. Scientists are constantly discovering new compounds, orderly arranging the facts about them, trying to explain with the existing knowledge, organizing to modify the earlier views, or evolve theories for explaining the newly observed facts. Matter is made up of one or different types of elements. Under normal conditions, no other element exists as an independent atom in nature except noble gases. However, a group of atoms is found to exist together as one species having characteristic properties. Such a group of atoms is called a molecule. Obviously, there must be some force which holds these constituent atoms together in the molecules. The attractive force which holds various constituents, atoms, ions, etc. together in different chemical species is called a chemical bond. Since the formation of chemical compounds takes place as a result of combination of atoms of various elements in different ways, it raises many questions. Why do atoms combine? Why are only certain combinations possible? Why do some atoms combine while certain others do not? Why do molecules possess definite shapes? To answer such questions, different theories and concepts have been put forward from time to time. These are Clausius approach, valence shell electron pair repulsion VSEPR theory, valence bond theory, and molecular orbital theory. The evolution of various theories of valence and the interpretation of the nature of chemical bonds have closely been related to the developments in the understanding of the structure of atom, the electronic configuration of elements, and the periodic table. Every system tends to be more stable, and bonding is nature's way of lowering the energy of the system to attain stability. 4.1 Clausius approach to chemical bonding. In order to explain the formation of chemical bond in terms of electrons, a number of attempts were made, but it was only in 1960 when Clausius and Lewis succeeded independently in giving a satisfactory explanation. They were the first to provide some logical explanation of valence, which was based on the inertness of noble gases. Lewis pictured the atom in terms of positively charged kernel, the nucleus plus and the inner electrons, and the outer shell that could accommodate a maximum of 8 electrons. He further assumed that these 8 electrons occupy the corners of a cube which surround the kernel. Thus, the single outer shell electron of sodium would occupy one corner of the cube, while in the case of the noble gases of all the 8 corners would be occupied. This octet of electrons represents a particularly stable electronic arrangement. Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. In the case of sodium and chlorine, this can happen by the transfer of an electron from sodium to chlorine, thereby giving the sodium ion and chloride ions. In the case of other molecules like Cl2, H2, F2, etc., the bond is formed by the sharing of a pair of electrons between the atoms. In the process, each atom attains a stable outer octet of electrons. Lewis symbols. In the formation of a molecule, only the outer shell electrons takes part in chemical combination and they are known as valence electrons. The inner shell electrons are well protected and are generally not involved in the combination process. G. N. Lewis, an American chemist, introduced simple notation to represent valence electron in an atom. The notation are called Lewis symbols. For example, the Lewis symbols for the elements of second period are as under. Here you can see the symbols. Significance of Lewis symbols. The number of dots around the symbol represents the number of valence electron. This number of valence electron helps to calculate the common or group valence of the element. The group valence of the elements is generally either equal to the number of dots in Lewis symbol or 8 minus the number of dots or valence electrons. Kozel, in relation to chemical bonding, drew attention to the following facts. In the periodic table, the highly electronegative halogens and the highly electropositive alkali metals are separated by the noble gases. The formation of a negative ion from a halogen atom and a positive ion from an alkali metal atom is associated with the gain and loss of electron by the respective atoms. The negative and positive ions thus formed attain stable noble gas electronic configuration. The noble gases, with the exception of helium, which has duplet of electrons, have a particularly stable outer shell configuration of 8 electrons, Ns2, Np6. The negative and positive ions are stabilized by electrostatic attraction. For example, the formation of NaCl from sodium and chlorine according to the above scheme can be explained. Here you can see sodium gives out sodium ion plus 1 electron. Na positive plus chloride negative gives out NaCl. Similarly, the formation of CaF2 may be shown as, here you can see this reaction. The bond formed as a result of the electrostatic attraction between the positive and negative ions was termed as the electrovalent bond. The electrovalence is thus equal to the number of unit charges on the ion. Thus, calcium is assigned a positive electrovalence of 2 while chlorine a negative electrovalence of 1. Kozel's postulations provide the basis for the modern concepts regarding ion formation by electron transfer and the formation of ionic crystalline compounds. His views have proved to be a great value in the understanding and systemization of the ionic compounds. At the same time, he did recognize the fact that a large number of compounds did not fit into these concepts. 4.11 Octet Rule. Kozel and Lewis in 1916 developed an important theory of chemical combination between atoms known as electronic theory of chemical bonding. According to this, atoms can combine either by transfer of valence electron from one atom to another or by sharing of valence electrons in order to have an octet in their valence shell. This is known as octet rule. 4.1.2 Covalent Bond. Langmuir in 1919 refined the Lewis postulations by abandoning the idea of the stationary cubical arrangement of the octet and by introducing the term covalent bond. The Lewis-Langmuir theory can be understood by considering the formation of chlorine molecule Cl2, the chloride atom with electronic configuration. Neon 3s2 3p5 is one of electron short of the argon configuration. The formation of the Cl2 molecule can be understood in terms of sharing of a pair of electrons between the two chlorine atoms, each chlorine atom contributing 1 electron to the shared pair in the process both. Here you can see the covalent bond between two chlorine atoms. Chlorine atoms attain the outer shell octet of the nearest noble gas, that is argon. The dot represents electrons. Such structures are referred to as Lewis dot structure. The Lewis dot structure can be written for the molecule also, in which the combining atoms may be identical or different. The important conditions being that Each bond is formed as a result of an electron pair between the atoms. Each bond is formed as a result of sharing of an electron pair between the atoms. Each combining atoms contributes at least one electron to the shared pair. The combining atoms attain the outer shell noble gas configuration as a result of the sharing of electrons. Thus, in water and carbon tetrachloride molecules, formation of covalent bonds can be represented as. Here you can see the structure. Thus, when two atoms share one electron pair, they are said to be joined by a single covalent bond. In many compounds, we have multiple bonds between atoms. The formation of multiple bonds envisages sharing of more than one electron pair between two atoms. If two atoms share two pairs of electrons, the covalent bond between them is called a double bond. For example, in the carbon dioxide molecule, we have two double bonds between the carbon and oxygen atoms. Similarly, in ethene molecule, the two carbon atoms are joined by a double bond. Here you can see the double bonds in CO2 molecule. When combining atoms share three electron pairs, as in the case of two nitrogen atoms in the N2 molecule and the two carbon atoms in the ethene molecule, a triple bond is formed. See the structure. 4.1.3 Lewis representation of simple molecules, the Lewis structure. The Lewis dot structures provide a picture of bonding in molecules and ions in terms of the shared pairs of electrons and the octet rule. While such a picture may not explain the bonding and behavior of a molecule completely, it does help in understanding the formation and properties of a molecule to a large extent. Writing a Lewis dot structures of molecule is therefore very useful. The Lewis dot structures can be written by adopting the following steps. The total number of electrons required for writing the structures are obtained by adding the valence electron of combining atoms. For example, in the CH4 molecule, there are 8 valence electrons available for bonding, 4 from carbon and 4 from the 4 hydrogen atoms. For anions, each negative charge would mean addition of 1 electron. For cations, each positive charge would result in subtraction of 1 electron from the total number of valence electrons. For example, for the CO3 2 negative ion, the 2 negative charges indicate that there are 2 additional electrons than those provided by the neutral atoms. For NH4 positive ion, 1 positive charge indicates the loss of 1 electron from the group of neutral atoms. Knowing the chemical symbols of the combining atoms and having knowledge of the skeletal structure of the compound known or guessed intelligently, it is easy to distribute the total number of electrons as bonding shared pairs between the atoms in proportion to the total bonds. In general, the least electronegative atom occupies the central position in the molecule or ion. For example, in the NF3 and CO3 2 negative, nitrogen and carbon are the central atoms, whereas fluorine and oxygen occupy the terminal positions. After accounting for the shared pairs of electrons for single bonds, the remaining electron pairs are either utilized for multiple bonding or remain as the lone pairs. The basic requirement being that each bonded atom gets an octet of electrons. Lewis representation of few molecules ions are given in Table 4.1. Table 4.1, the Lewis representation of some molecules. Here each hydrogen atom attains the configuration of helium, that is a duplet of electron. See the structures. 4.1.4 Formal charge. Lewis dot structures in general do not represent the actual shape of the molecules. In case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. The formal charge of an atom in an polyatomic molecule or ion may be defined as the difference between the number of valence electron of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. It is expressed as formal charge on an atom in a Lewis structure is equals to total number of valence electron in the free atom minus total number of non-bonding, that is lone pair electrons, minus 1 upon 2 total number of bonding, that is shared electrons. The counting is based on the assumption that the atom in the molecule owns 1 electron of each shared pair and both the electrons of a lone pair. Let us consider the ozone molecule. The Lewis structure of the O3 may be drawn as the atoms have been numbered as 1, 2, 3. The formal charge on here you can see the structure. And now see the calculation. Hence we represent O3 along with the formal charges as below. Here you can see the structure. We must understand that formal charges do not indicate real charge separation within the molecule. Indicating the charges on the atoms in the Lewis structure only helps in keeping track of the valence electron in the molecule. Formal charges help in the selection of the lowest energy structure from a number of possible Lewis structures for a given species. Generally, the lowest energy structure is the one with the smallest formal charges on the atoms. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. 4.1.5 Limitations of the octet rule. The octet rule, though useful, is not universal. It is quite useful for understanding the structures of the most of the organic compounds, and it applies mainly to the second period elements of the periodic table. There are three types of exceptions to the octet rule. The incomplete octet of the central atom. In some compounds, the number of electrons surrounding the central atom is less than 8. This is especially the case with elements having less than 4 valence electron. Examples are LiCl, BeH2 and BCl3. See the structures. Li, Be and boron have 1, 2 and 3 valence electrons only. Some other such compounds are AlCl3 and Bf3. Odd electron molecules. In molecules with an odd number of electrons like nitric oxide, NO, and nitrogen dioxide, that is NO2, the octet rule is not satisfied for all the atoms. See the structures. The expanded octet. Elements in beyond the third period of the periodic table have, apart from 3s and 3p orbitals, 3d orbitals also available for bonding. In a number of compounds of these elements, there are more than 8 valence electrons around the central atom. This is termed as the expanded octet. Obviously, the octet rule does not apply in such cases. Some of the examples of such compounds are PF5, SF6, H2SO4, and a number of coordination compounds. See the structures. Interestingly, sulfur also forms so many compounds in which the octet rule is obeyed. In sulfur dichloride, the S atom has an octet of electron around it. See the structure. Other drawbacks of the octet theory. It is clear that octet rule is based upon the chemical inertness of noble gases. However, some noble gases, for the example xenon and krypton, also combine with oxygen and fluorine to form a number of compounds like XeF2, KrF2, XeOF2, etc. This theory does not account for the shape of molecules. It does not explain the relative stability of the molecules, being totally silent about the energy of a molecule. 4.2 Ionic or electrovalent bond. From the Coastal and Lewis treatment of the formation of an ionic bond, it follows that the formation of the ionic bond would primarily depend upon the ease of formation of the positive and negative ions from the respective neutral atoms, the arrangement of the positive and negative ions in the solid, that is the lattice of crystalline compound. The formation of a positive ion involves ionization, that is removal of electrons from the neutral atom, and that of the negative ion involves the addition of electrons to the neutral atom. Here you can see all three reactions. The electron gain enthalpy, that is delta H, is the enthalpy change when a gas phase atom in its ground state gains an electron. The electron gain process may be exothermic or endothermic. The ionization, on the other hand, is always endothermic. Electron affinity is the negative of the energy change accompanying electron gain. Obviously, ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. Most ionic compounds have cations derived from metallic elements and anions from non-metallic elements. The ammonium ion NH4 ion, made up of two non-metallic elements, is an exception. It forms the cation of a number of ionic compounds. Ionic compounds in the crystalline state consist of orderly three-dimensional arrangements of cations and anions held together by Coulombic interaction energies. These compounds crystallize in different crystal structures determined by the size of the ions, their packing, arrangements, and other factors. The crystal structure of a sodium chloride NaCl, that is rock salt, for example, is shown below. Here you can see the rock salt structure. In ionic solid, the sum of the electron gain enthalpy and the ionization enthalpy may be positive, but still the crystal structures get stabilized due to the energy released in the formation of the crystal lattice. For example, the ionization enthalpy for sodium ion formation from sodium is 495.8 kJ per mole, while the electron gain enthalpy for the change chlorine plus 1 electron gives out chlorine negative is minus 348.7 kJ per mole only. The sum of two 147.1 kJ per mole is more than compensated for by the enthalpy of lattice formation of NaCl, that is minus 788 kJ per mole. Therefore, the energy released in the processes is more than the energy absorbed. Thus, this qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species in gaseous state. Since lattice enthalpy plays a key role in the formation of ionic compounds, it is important that we learn more about it. 4.2.1 Lattice enthalpy. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituents ions. For example, the lattice enthalpy of NaCl is 788 kJ per mole. This means that 788 kJ of energy is required to separate 1 mole of solid NaCl into 1 mole of sodium ion and 1 mole of chloride ion to an infinite distance. This process involves both the attractive forces between ions of opposite charges and the repulsive forces between ions of like charges. The solid crystal being three-dimensional, it is not possible to calculate lattice enthalpy directly from the interaction of forces of attraction and repulsion only. Factors associated with the crystal geometry have to be included. 4.3 Bond parameters. 4.3.1 Bond length. Bond length is defined as the equilibrium distance between the two nuclei of two bonded atoms in a molecule. Bond lengths are measured by spectroscopic X-ray diffraction and electron diffraction techniques, about which you will learn in higher classes. Each atom of the bonded pair contributes to the bond length. Figure 4.1, I will show you later. In the case of a covalent bond, the contribution from each atom is called the covalent radius of that atom. The covalent radius is measured approximately as the radius of an atom's core, which is in contact with the core of an adjacent atom in a bonded situation. The covalent radius is half of the distance between two similar atoms joined by covalent bond in the same molecule. See the figure 4.1, the bond length in a covalent molecule AB. Capital R is equals to RA plus RB. R is the bond length and RA and RB are the covalent radii of atoms A and B respectively. The van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded situation. Further, the van der Waals radius is half of the distance between two similar atoms in separate molecules in a solid. Covalent and van der Waals radii of chlorine are depicted in figure 4.2. See the diagram. Covalent and van der Waals radii in a chlorine molecule, the inner circles correspond to the size of a chlorine atom. Some typical average bond lengths for single, double and triple bonds are shown in table 4.2. Bond lengths for some common molecules are given in table 4.3. The covalent radii of some common elements are listed in table 4.4. 4.3.2 Bond angle. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. Bond angle is expressed in degree, which can be experimentally determined by spectroscopic method. It gives some idea regarding the distribution of orbitals around the central atom in a molecule that is complex or complex ion, and hence it helps in determining its shape. For example, HOH bond angle in water can be represented as under. Here you can see this is 104.5 degree. 4.3.3 bond enthalpy. But before that, I am showing you table 4.2, that is average bond lengths for some single, double and triple bond. Table 4.3 bond lengths in some common molecules. and table 4.4, that is the covalent radii. Now 4.3.3 bond enthalpy. It is defined as the amount of energy required to break 1 mole of bonds of a particular type of two atoms in a gaseous state. The unit of bond enthalpy is kilojoule per mole. For example, the HH bond enthalpy in hydrogen molecule is 435.8 kilojoule per mole. H2 gives out H plus H and delta H is equals to 435.8 kilojoule per mole. Similarly, the bond enthalpy for molecules containing multiple bonds, for example, O2 and N2 will be under O2. Here you can see the delta H for it, 498 kilojoule per mole, and for nitrogen N2, here you can see the delta H is 946.0 kilojoule per mole. It is important that larger the bond dissociation enthalpy, stronger will be the bond in the molecule. For a heteronuclear diatomic molecules like HCl, we have HCl gives out H plus Cl and delta H is here 431.0 kilojoule per mole. In case of polyatomic molecules, the measurement of bond strength is more complicated. For example, in case of H2O molecule, the enthalpy needed to break the two OH bonds is not the same. For H2O, delta H is 502 kilojoule per mole. For OH, delta H is equals to 427 kilojoule per mole. The difference in the delta H value shows that the second OH bond undergoes some change because of changed chemical environments. You can see these reactions here. This is the reason for some difference in energy of the same OH bond in different molecules like C2H5OH, that is ethanol, and water. Therefore, in polyatomic molecules, the term mean or average bond enthalpy is used. It is obtained by dividing total bond dissociation enthalpy by the number of bonds broken as explained below in case of water molecule. Average bond enthalpy is equals to 502 plus 427 upon 2, that is 464.5 kilojoule per mole. 4.3.4 bond order. In the Lewis description of covalent bond, the bond order is given by the number of bonds between the two atoms in a molecule. The bond order, for example, in H2 with a single shared electron pair, in O2 with two shared electron pairs, and in N2 with three shared electron pairs is 1, 2, 3 respectively. Similarly, in CO, three shared electron pairs between C and O, the bond order is 3. For N2, bond order is 3 and its delta H is 946 kilojoule per mole, being one of the highest for a diatomic molecule. Isoelectronic molecules and ions have identical bond orders. For example, F2 and O2 negative have bond order 1. N2, CO and NO positive have bond order 3. A general correlation useful for understanding the stabilities of molecules is that with increase in bond order, bond enthalpy increases and bond length decreases. 4.3.5 Resonance structure. It is often observed that a single Lewis structure is inadequate for the representation of molecule in conformity with its experimentally determined parameters. For example, the ozone O3 molecule can be equally represented by the structure first and second shown below. Here you can see the resonance in the O3 molecule. Structure 1 and second represent the two canonical forms, while the structure third is the resonance hybrid. In both structures, we have a OO single bond and a O double bond. The normal OO, that is single bond, and the double bond lengths are 148 picometer and 121 picometer respectively. Experimentally determined oxygen-oxygen bond lengths in the O3 molecule are the same, that is 128 picometer, and thus the oxygen-oxygen bonds in the O3 molecule are intermediate between a double and a single bond. Obviously, this cannot be represented by either of two Lewis structures shown above. The concept of resonance was introduced to deal with the type of difficulty experienced in the depiction of accurate structures of molecules like O3. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid which describes the molecules accurately. Thus, for O3, the two structures shown above constitute the canonical structures or resonance structure, and their hybrid, that is the third structure, represent the structure of O3 more accurately. This is also called resonance hybrid. Resonance is represented by a double-headed arrow. Some of other examples of resonance structure are provided by the carbonate ion and the carbon dioxide molecule. In general, it may be stated that resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure, and resonance averages the bond characteristics as a whole. Thus, the energy of the O3 resonance hybrid is lower than either of the two canonical forms, first and second, and figure 4.3. Many misconceptions are associated with resonance and the same need to be dispelled. You should remember that the canonical forms have no real existence. The molecule does not exist for a certain fraction of time in one canonical form and for other fraction of time in other canonical forms. There is no such equilibrium between the canonical forms as we have between tautomeric forms, keto and enol in tautomerism. The molecule as such as single structure, which is the resonance hybrid of the canonical forms and which cannot as such be depicted by a single Lewis structure. 4.3.6 Polarity of bonds. The existence of 100% ionic or covalent bond represents an ideal situation. In reality, no bond or compound is either completely covalent or ionic. Even in case of covalent bond between two hydrogen atoms, there is some ionic character. When covalent bond is formed between two similar atoms, for example in H2, O2, Cl2, N2 or F2, the shared pair of electron is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei. The bond so formed is called non-polar covalent bond. Contrary to this, in case of heteronuclear molecule like HF, the shared electron pair between the two atoms gets displaced more towards fluorine since the electronegativity of fluorine is far greater than that of hydrogen. The resultant covalent bond is a polar covalent bond. As a result of polarization, the molecule possesses the dipole moment, depicted below, which can be defined as the product of the magnitude of the charge and the distance between the centers of positive and negative charge. It is usually designated by a Greek letter mu. Mathematically, it is expressed as followed. Dipole moment mu is equals to charge q into distance of separation, that is r. Dipole moment is usually expressed in dBi units, that is d. The conversion factor is 1d is equals to 3.33564 into 10 to the power minus 30 cm, where c is coulomb and m is meter. Further, dipole moment is a vector quantity and by convention it is depicted by a small arrow with tail on the negative center and head pointing towards the positive center. But in chemistry, presence of dipole moment is represented by the crossed arrow put on Lewis structure of the molecule. The cross is on positive and arrowhead is on negative end. For example, the dipole moment of HF may be represented as, here you can see, this arrow symbolizes the direction of the shift of electron density in the molecule. Note that the direction of crossed arrow is opposite to the conventional direction of dipole moment vector. Peter Debye, the Dutch chemist, received Nobel Prize in 1936 for his work on X-ray diffraction and dipole moments. The magnitude of the dipole moment is given in Debye units in order to honor him. In case of polyatomic molecules, the dipole moment not only depend upon the individual dipole moments of bonds known as bond dipoles, but also on the spatial arrangement of various bonds in the molecule. In such case, the dipole moment of molecule is the vector sum of the dipole moments of various bonds. For example, in H2O molecule, which has a bent structure, the two OH bonds are oriented at an angle of 104.5 degree. Net dipole moment of 6.17 into 10 to the power minus 30 cm. 1d is equals to 3.33564 into 10 to the power minus 30 cm is the resultant of the dipole moments of two OH bonds. See the structure. Net dipole moment mu is equals to 1.85d is equals to 1.85 into 3.33564 into 10 to the power minus 30 cm is equals to 6.17 into 10 to the power minus 30 cm. The dipole moment in case of BeF2 is 0. This is because the two equal bond dipoles point in opposite direction and cancel the effect of each other. See the structures. In tetraatomic molecule, for example, in BF3, the dipole moment is 0, although the BF bonds are oriented at an angle of 120 degree to one another. The three bond moments give a net sum of 0 as the resultant of any two is equal and opposite to the third. See the structure. Let us study an interesting case of NH3 and NF3 molecule. Both the molecules have pyramidal shape with a lone pair of electrons on nitrogen atoms. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of NH3, that is 4.90 into 10 to the power minus 30 cm, is greater than that of NF3, that is 0.8 into 10 to the power minus 30 cm. This is because in case of NH3, the orbital dipole to lone pair is in the same direction as the resultant dipole moment of NH bonds, whereas in NF3 the orbital dipole is in the direction opposite to the resultant dipole moment of the three NF bonds. The orbital dipole, because of lone pair, decreases the effect of the resultant NF bond moments, which results in the low dipole moment of NF3 as represented below. See the structures. Dipole moments of some molecules are shown in table 4.5. Just as all the covalent bonds have some partial ionic character, the ionic bonds also have partial covalent character. The partial covalent character of ionic bonds was discussed by Fazans in terms of the following rules. See the table 4.5, dipole moment of selected molecules. Now, the number 1 is the smaller the size of the cation and the larger the size of the anion, the greater the covalent character of an ionic bond. The greater the charge on the cation, the greater the covalent character of the ionic bond. For cations of the same size and charge, the one with electronic configuration n-1 d to the power n ns0, typical of transition metal, is more polarizing than the one with a noble gas configuration, that is ns2 np6, typical of alkali and alkaline earth metal cations. The cation polarizes the anion, pulling the electron charge towards itself and thereby increasing the electronic charge between the two. This is precisely what happens in a covalent bond, that is, buildup of electron charge density between the nuclei, the polarizing power of the cation, the polarizability of the anion, and the extent of distortion, that is, polarization of an anion, are the factors which determine the percent covalent characters of the ionic bond. 4.4, the valence shell electron pair repulsion, that is VSEPR theory. As already explained, Lewis' concept is unable to explain the shapes of molecules. This theory provides a simple procedure to predict the shapes of covalent molecules. Sidgwick and Powell in 1940 proposed a simple theory based on the repulsive interactions of the electron pairs in the valence shell of the atoms. It was further developed and redefined by Niolom and Gillespie. I hope that I pronounced their name correctly. In 1957, they actually redefined. The main postulates of VSEPR theory are as follows. The shape of molecule depends upon the number of valence shell electron pairs, that is bonded or non-bonded, around the central atom. Pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. These pairs of electrons tend to occupy such positions in a space that minimize repulsion and thus maximize distance between them. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. A multiple bond is treated as if it is a single electron pair, and the 2 or 3 electron pairs of a multiple bond are treated as a single super pair. Where 2 or more resonance structures can represent a molecule, the VSEPR model is applicable to any such substructure. The repulsive interaction of electron pairs decrease in the order, that is lone pair is greater than lone pair, that is bond pair is greater than bond pair minus bond pair. Niolm and Gillespie in 1957 refined the VSEPR model by explaining the important difference between the lone pairs and bonding pairs of electrons. While the lone pairs are localized on the central atom, each bonded pair is shared between two atoms. As a result, the lone pair electrons in a molecule occupy more space as compared to bonding pairs of electron. This results in greater repulsion between two lone pairs of electron as compared to the lone pair, bond pair and bond pair repulsion. These repulsion effects result in deviation from idealized shapes and alteration in bond angles in molecules. For the prediction of geometrical shapes of molecules with the help of VSEPR theory, it is convenient to divide molecules into two categories. Number 1, molecules in which the central atom has no lone pair, and number 2, molecules in which the central atom has one or more lone pair. Table 4.6, page 114 shows the arrangement of electron pairs about a central atom A without any lone pairs and geometries of some molecules or ions of the type AB. Table 4.7, page 115 shows shapes of some simple molecules and ions in which the central atom has one or more lone pairs. Table 4.8, page 116 explains the reasons for the distortion in the geometry of the molecule. As depicted in table 4.6, in the compounds of AB2, AB3, AB4, AB5 and AB6, the arrangement of electron pairs and the B atoms around the central atom A are linear, trigonal, planar, tetrahedral, trigonal, bipyramidal and octahedral respectively. Such arrangement can be seen in the molecules like BF3, that is AB3, CH4, that is AB4 and PCl5, that is AB5 as depicted below by their ball and stick models. You can see the structure in figure 4.6, the shapes of molecules in which central atom has no lone pair. The VSEPR theory is able to predict geometry of a large number of molecules, especially the compounds of p-block elements accurately. It is also quite successful in determining the geometry quite accurately even when the energy difference between possible structures is very small. The theoretical basis of the VSEPR theory regarding the effects of electron pair repulsions on molecular shape is not clear and continues to be a subject of doubt and discussion. Table 4.c, geometry of molecules in which the central atom has no lone pair of electron. See the structures. Table 4.7, shape of some simple molecules or ions with central ions having one or more lone pairs of electrons. Table 4.8, shapes of molecules containing bond pair and lone pair. Here I will explain the reason also. Molecule type, that is AB2E, and the reason for the shape acquired. Theoretically, the shape should have been triangular planar, but actually it is found to be bent or V-shaped. The reason being the lone pair bond pair repulsion is much more as compared to the bond pair repulsion. So the angle is reduced 119.5 from 120 degree. In case of molecule type AB3E, the shape is trigonal pyramidal. This had 3 been a base bond pair in place of lone pair, the shape would have been tetrahedral, but one lone pair is present, and due to the repulsion between the lone pair bond pair, which is more than the bond pair repulsion, the angle between bond pairs is reduced to 107 degree from 109.5 degree. In the case of molecule type AB2E2, shape is bent. The shape should have been tetrahedral if there were all bond pair, but 2 lone pair are present, so the shape is distorted, tetrahedral or angular. The reason is lone pair repulsion is more than lone pair bond pair repulsion, which is more than bond pair repulsion. Thus, the angle is reduced to 104.5 from 109.5 degree. AB4E, the shape is seesaw. In A, the lone pair is present at axial position, so there are 3 lone pair bond pair repulsions at 90 degree. In B, the lone pair is in an equatorial position and there are 2 lone pair bond pair repulsions. Hence, arrangement is more stable. The shape shown in B is described as a distorted tetrahedron, a folded square or a seesaw. Here you can see. In the molecule type AB3F2, the shape is T-shape. And reason is, in A, the lone pair are at equatorial position, so there are less lone pair bond pair repulsions as compared to others in which the lone pair are at axial positions. So structure is most stable, that is T-shaped. You can see that all three structures A, B and C. Now 4.5 Valence bond theory. As we know that Lewis approach helps in writing the structure of molecules, but it fails to explain the formation of chemical bond. It also does not give any reason for the difference in bond dissociation enthalpies and bond lengths in molecule like H2, that is 435.8 kJ per mole and 74 pm, and F2, that is 155 kJ per mole and 144 pm. Although in both the cases a single covalent bond is formed by the sharing of an electron pair between the respective atoms. It also gives no idea about the shapes of polyatomic molecule. Similarly, the VSEPR theory gives the geometry of simple molecules, but theoretically it does not explain them, and also it has a limited application. To overcome these limitations, the two important theories based on quantum mechanical principles are introduced. These are valence bond theory, VB theory, and molecular orbital theory. Valence bond theory was introduced by Hitler and London in 1927 and developed further by Pauling and others. As a discussion of the valence bond theory is based on the knowledge of atomic orbitals, electronic configuration of elements, the overlap criteria of atomic orbitals, the hybridization of atomic orbitals, and the principles of variation and superposition. A rigorous treatment of the VB theory in terms of their aspect is beyond the scope of this book. Therefore, for the sake of convenience, valence bond theory has been discussed in the terms of qualitative and non-mathematical treatment only. To start with, let us consider the formation of hydrogen molecule, which is the simplest of all molecules. Consider two hydrogen atoms A and B approaching each other, having nuclei Na and Nb, and electrons present in them are represented by Ea and Eb. When two atoms are at large distance from each other, there is no interaction between them. As these atoms approach each other, new attractive and repulsive forces begin to operate. Attractive forces arise between number 1, a nucleus of one atom and its own electron, that number 2, nucleus of one atom and electron of other atom, that is Na, Eb and Nbea. Similarly, repulsive forces arise between number 1, electrons of two atoms like Ea, Eb, number 2, nuclei of two atoms Na, Nb. Attractive forces tend to bring the two atoms close to each other, whereas repulsive forces tend to push them apart. Figure 4.7, that is forces of attraction and repulsion during the formation of H2 molecules. See the structure. Experimentally, it has been found that magnitude of new attractive forces is more than the new repulsive forces. As a result, two atoms approach each other and the potential energy decreases. Ultimately, a stage is reached where the net force of attraction balances the force of repulsion and system acquires minimum energy. At this stage, two hydrogen atoms are said to be bonded together to form a stable molecule having the bond length of 74 pm. Since the energy gets released when the bond is formed between two hydrogen atoms, the hydrogen molecule is more stable than that of isolated hydrogen atoms. The energy is released is called as bond enthalpy, which is corresponding to minimum in the curve depicted in figure 4.8. Conversely, 435.8 kJ of energy is required to dissociate 1 mole of H2 molecule. Here H2 plus 435.8 gives out H plus H. You can see figure 4.8, that is the potential energy curve for the formation of H2 molecule as a function of internuclear distance of the hydrogen atoms. The minimum in the curve correspond to the most stable state of H2. See the structure. 4.5.1 Orbital overlap concept. In the formation of hydrogen molecule, there is a minimum energy state when two hydrogen atoms are so near that their atomic orbitals undergo partial interpenetration. This partial merging of atomic orbital is called overlapping of atomic orbitals, which results in the pairing of electron. The extent of overlap decides the strength of covalent bond. In general, greater the overlap, the stronger is the bond formed between two atoms. Therefore, according to orbital overlap concept, the formation of a covalent bond between two atoms results by pairing of electrons present in the valence shell having opposite spins. 4.5.2 Directional properties of bonds. As we have already seen, the covalent bond is formed by overlapping of atomic orbitals. The molecule of hydrogen is formed due to the overlap of 1s orbitals of the two hydrogen atoms. In case of polyatomic molecules like CH4, NH3 and H2O, the geometry of the molecules is also important in addition to the bond formation. For example, why is it so that CH4 molecule has tetrahedral shape and HCH bond angles are 109.5 degree? Why is the shape of NH3 molecule pyramidal? The valence bond theory explains the shape, the formation and directional properties of bonds in polyatomic molecules like CH4, NH3 and H2O etc. in terms of overlap and hybridization of atomic orbitals. 4.5.3 Overlapping of atomic orbitals. When orbitals of two atoms come close to form bond, their overlap may be positive, negative or zero depending upon the sign and direction of orientation of amplitude of orbital wave function in space, that is figure 4.9. Positive and negative sign on boundary surface diagrams in the figure 4.9 show the sign of orbital wave function and are not related to charge. Orbitals forming bonds should have same sign and orientation in space. This is called positive overlap. Various overlap of s and p orbitals are depicted in figure 4.9. The criteria of overlap as the main factor for the formation of covalent bonds applies uniformly to the homonuclear, heteronuclear, diatomic molecules and polyatomic molecules. We know that the shapes of CH4, NH3, H2O molecules are tetrahedral, pyramidal and bent respectively. It would be therefore interesting to use VB theory to find out if these geometrical shapes can be explained in terms of the orbital overlaps. Let us first consider the CH4 molecule. The electronic configuration of carbon in its ground state is He, that is 2s2, 2p2, which in the excited state becomes, that is 2s1, 2px1, 2py1, 2pz1. The energy required for this excitation is compensated by the release of energy due to the overlap between the orbitals of carbon and the hydrogen. The four atomic orbitals of carbon, each with an unpaired electron, can overlap with the 1s orbital of the four hydrogen atoms which are also singly occupied. This will result in the formation of 4 CH bonds. It will, however, be observed that while the 3 p orbitals of carbon are at 90 degree to one another, the HCH angle for these will also be 90 degree. That is, 3 CH bonds will be oriented at 90 degree to one another. The 2s orbital of carbon and the 1s orbital of hydrogen are spherically symmetrical and they can overlap in any direction. Therefore, the direction of 4th CH bond cannot be ascertained. This description does not fit in with the tetrahedral HCH angle of 109.5 degree. Clearly, it follows that simple atomic orbital overlap does not account for the directional characteristics of bonds in CH4. Using similar procedure and arguments, it can be seen that in the case of NH3 and H2 molecules, the HNH and HOH angles should be 90 degree. This is in disagreement with the actual bond angles of 107 degree and 104.5 degree in the NH3 and H2 molecules respectively. 4.5.4 Types of overlapping and nature of covalent bonds. The covalent bond may be classified into two types of depending upon the types of overlapping, that is sigma bond, and number 2 is the pi bond. Number 1, sigma bond. This type of covalent bond is formed by the end-to-end overlap of bonding orbitals along the internuclear axis. This is called as head-on overlap or axial overlap. This can be formed by any one of the following types of combination of atomic orbitals. SS overlapping. In this case, their overlap is of two filled s orbitals along the internuclear axis is shown below. Here you can see SP overlapping. This type of overlap occurs between half-filled s orbitals of one atom and half-filled p orbitals of another atom. PP overlapping. This type of overlapping or overlap takes place between half-filled p orbitals. See the structure, everyone. Number 2 is the pi bond. Pi bond. In the formation of pi bond, the atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. Formed due to the sidewise overlapping consist of two saucer shape. Here you can see the structure. Saucer-shaped charged clouds above and below the plane of the participating atoms. 4.5.5 is strength of a sigma and pi bonds. Basically, the strength of bond depends upon the extent of overlapping. In case of sigma bond, the overlapping of orbitals takes place to a larger extent, hence it is stronger as compared to the pi bond where the extent of overlapping occurs to a smaller extent. Further, it is important to note that in the formation of multiple bond between two atoms of a molecules, pi bond is formed in addition to a sigma bond. 4.6 Hybridization. In order to explain the characteristic geometrical shapes of polyatomic molecules like CH4, NH3, H2O, etc., Pauling introduced the concept of hybridization. According to him, the atomic orbitals combine to form new set of equivalent orbitals known as hybrid orbitals. Unlike pure orbitals, the hybrid orbitals are used in bond formation. The phenomena is known as hybridization, which can be defined as the process of intermixing of the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shape. For example, when 1 2s and 3 2p orbitals of carbon hybridize, there is the formation of 4 new sp3 hybrid orbitals. Salient features of hybridization. The main features of hybridization are as under. Number 1, the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. The hybridized orbitals are always equivalent in energy and shape. Number 3, the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. Number 4, these hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between electron pairs and thus a stable arrangement. Therefore, the type of hybridization indicates the geometry of the molecules. Important conditions for hybridization. Number 1, the orbitals present in the valence shell of atom are hybridized. Number 2, the orbitals undergoing hybridization should have almost equal energy. Number 3, promotion of electron is not essential condition prior to hybridization. Number 4, it is not necessary that only half-filled orbitals participate in hybridization. In some cases, even filled orbitals of valence shell take part in hybridization. 4.6.1 Types of hybridization. There are various types of hybridization involving s, p and d orbitals. The different types of hybridization are as under. Number 1, sp hybridization. This type of hybridization involves the mixing of one s and p orbital resulting in the formation of two equivalent sp hybrid orbitals. The suitable orbitals for sp hybridization are s and pz. If the hybrid orbitals are to lie along the z-axis, each sp hybrid orbitals has 50% s character and 50% p character. Such a molecule in which the central atom is sp hybridized and linked directly to two other central atoms possesses linear geometry. This type of hybridization is also known as diagonal hybridization. The two sp hybrids point in the opposite direction along the z-axis with projecting positive lobes and very small negative lobes, which provides more effective overlapping resulting in the formation of stronger bonds. Example of molecule having sp hybridization: BeCl2. The ground state electronic configuration of Ba is 1s2 2s2. In the excited state, one of the 2s electron is promoted vacant 2p orbital to account for its bivalency. One 2s and 2p orbital gets hybridized to form two sp hybridized orbitals. These two sp hybrid orbitals are oriented in opposite direction, forming an angle of 180 degree. Each of the sp hybridized orbital overlaps with the 2p orbital of chlorine axially and form two BeCl sigma bonds. This is shown in figure 4.10. Here you can see the diagram 4.10. Number 2, sp2 hybridization. In this hybridization, there is involvement of 1s and 2p orbitals in order to form three equivalent sp2 hybridized orbitals. For example, in BeCl3 molecule, the ground state electronic configuration of central boron atom is 1s2, 2s2, 2p1. In the excited state, one of the 2s electron is promoted to vacant 2p orbital as, here you can see the figure 4.11. As a result, boron has 3 unpaired electrons. These 3 orbitals, 1, 2s and 2p, hybridize to form 3 sp2 hybrid orbitals. The 3 hybrid orbitals so formed are oriented in trigonal planar arrangement and overlap with 2p orbitals of chlorine to form 3 BeCl bonds. Therefore, in BeCl3, that is figure 4.11, the geometry is trigonal planar with Cl-BCl bond angle of 120 degree. Let me show you diagram 4.11 one more time. See this? That is formation of sp2 hybrids and the BCl3 molecules. Number third, sp3 hybridization. This type of hybridization can be explained by taking the example of CH4 molecule in which there is mixing of 1s orbital and 3 p orbitals of the valence shell to form 4 sp3 hybrid orbital of equivalent energies and shape. There is 25% s character and 75% p character in each sp3 hybrid orbital. The 4 sp3 hybrid orbitals so formed are directed towards the four corners of the tetrahedron. The angle between sp3 hybrid orbital is 109.5 degree as shown in figure 4.12. Here you can see the figure 4.12. The structure of NH3 and H2 molecules can also be explained with the help of sp3 hybridization. In NH3, the valence shell outer electronic configuration of nitrogen in the ground state is 2s2, 2px1, 2py1 and 2pz1 having 3 unpaired electrons in the sp3 hybrid orbitals and a lone pair of electron is present in the fourth one. These 3 hybrid orbitals overlap 1s orbitals of hydrogen atoms to form 3 NH sigma bonds. We know that the force of repulsion between a lone pair and a bond pair is more than the force of repulsion between two bond pairs of electron. The molecule thus gets distorted and the bond angle is reduced to 107 degree from 109.5 degree. The geometry of such a molecule will be pyramidal as shown in figure 4.13. Here you can see the figure 4.13. In case of H2O molecule, the 4 oxygen orbitals 1, 2s and 3, 2p undergo sp3 hybridization, forming 4 sp3 hybrid orbitals out of which 2 contain 1 electron each and the other 2 contain a pair of electrons. These 4 sp3 hybrid orbitals acquire a tetrahedral geometry with 2 corners occupied by hydrogen atoms while the other 2 by the lone pairs. The bond angle in this case is reduced to 104.5 degree from 109.5 degree. Figure 4.14. And the molecule thus acquires a V-shape or angular geometry. Here you can see formation of H2O molecule in figure 4.14. 4.6.2 other examples of sp3, sp2 and sp hybridization. sp3 hybridization in C2H6 molecule. In ethane molecule, both the carbon atoms assume sp3 hybrid state. One of the 4 sp3 hybrid orbitals of carbon atom overlaps axially with similar orbitals of other atom to form sp3 sigma bond, while the other 3 hybrid orbitals of each carbon atom are used in forming sp3s sigma bonds with hydrogen atoms as discussed in section 4.6.1. Therefore, in ethane, CC bond length is 154 pm and each CH bond length is 109 pm. sp2 hybridization in C2H4. In the formation of ethene molecule, one of the sp2 hybrid orbitals of carbon atom overlaps axially with sp2 hybridized orbital of another carbon atom to form CC sigma bond, while the other sp2 dihybrid orbitals of each carbon atom are used for making sp2s sigma bond with 2 hydrogen atoms. The unhybridized orbital of one carbon atom overlaps sidewise with the similar orbital of the other carbon atom to form weak pi bond, in which consists of 2 equal electron cloud distributed above and below the plane of carbon and hydrogen atom. Thus, in ethene molecule, the carbon-carbon bond consists of one sp2 sigma bond and one pi bond between p orbitals, which are not used in the hybridization and are perpendicular to the plane of molecule. The bond length 134 pm. The CH bond is sp2s sigma with bond length of 108 pm. The HCH bond angle is 117.6 degree while the HCC angle is 121 degree. The formation of sigma and pi bonds in ethene is shown in figure 4.15. Once more time I am showing you the diagram. sp hybridization in C2H2. In the formation of Ethyne molecule, both carbon atoms undergo sp hybridization having two unhybridized orbital, that is 2py and 2px. One sp hybrid orbital of one carbon atom overlaps axially with sp hybrid orbital of the other carbon atom to form cc sigma bond, while the other hybridized orbital of each carbon atom overlap axially with the half-filled s orbital of hydrogen atoms, forming sigma bonds. Each of the two unhybridized p orbitals of both the carbon atoms overlap sidewise to form two pi bonds between the carbon atoms. So the triple bond between the two carbon atoms is made up of one sigma and two pi bond as shown in figure 4.16. See the structure? 4.6.3 Hybridization of elements involving d orbitals. The elements present in the third period contain d orbital in addition to s and p orbital. The energy of the 3d orbitals are comparable to the energy of 3s and 3p orbitals. The energy of 3d orbitals are also comparable to those of 4s and 4p orbital. As a consequence, the hybridization involving either 3s, 3p and 3d or 3d, 4s and 4p is possible. However, since the difference in energies of 3p and 4s orbitals is significant, no hybridization involving 3p, 3d and 4s orbital is possible. The important hybridization schemes involving sp and d orbitals are summarized below. Here you can see the table. A square planar example is NiCN whole 4 to the power 2 negative and trigonal bipyramidal. Hybridization type is sp3d and examples are PF5, PCl5, and square pyramidal, the hybridization type is sp3d2 and the example is BRF5, and octahedral hybridization type is sp3d2, d2sp3, and examples are SF6, CRF6 3 negative, CONH3 whole 6 3 positive. Formation of PCl5, that is sp3d hybridization. The ground state and the excited state outer electronic configuration of phosphorids, that is Z15, are represented below. Here you can see the electronic configuration. Now the 5 orbitals, that is 1s, 3p and 1d orbitals are available for hybridization to yield a set of 5 sp3d hybrid orbitals which are directed towards the 5 corners of a trigonal bipyramidal as depicted in the figure 4.17. Here you can see the structure. It should be noted that all the bond angles in trigonal bipyramidal geometry are not equivalent. In PCl5, the 5 sp3d orbitals of phosphorus overlap with the singly occupied p orbitals of chlorine atoms to form 5 PCl sigma bonds. Their PCl bond lie in one plane and make an angle of 120 degrees with each other. These bonds are termed as equatorial bonds. The remaining 2 PCl bonds, one lying above and the other lying below the equatorial plane, make an angle of 90 degrees with the plane. These bonds are called axial bond. As the axial bond pairs suffer more repulsive interaction from the equatorial bond pairs, therefore axial bonds have been found to be slightly longer and hence slightly weaker than the equatorial bonds, which makes PCl5 molecules more reactive. Number 2, formation of SF6, that is sp3d2 hybridization. In SF6, the central sulfur has the ground state outer electronic configuration, that is 3s2, 3p4. In the excited state, the available 6 orbitals, that is 1s, 3p and 2d, are singly occupied by electrons. These orbitals hybridize to form 6 new sp3d2 hybrid orbitals which are projected towards the 6 corners of a regular octahedron in SF6. These 6 sp3d2 hybrid orbitals overlap with singly occupied orbitals of fluorine atoms to form 6 SF sigma bonds. The SF6 molecule has a regular octahedral geometry as shown in figure 4.18. Here you can see the electronic configuration as well as the octahedral geometry of SF6 molecule. 4.7 Molecular Orbital Theory. Molecular orbital theory was developed by F. Hunt and R. S. Millikan in 1932. The salient features of this theory are: number 1, the electrons in a molecule are present in the various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. Number 2, the atomic orbitals of comparable energies and proper symmetry combine to form molecule orbitals. Number 3, while an electron in an atomic orbital is influenced one nucleus in a molecular orbital, it is influenced by 2 or more nuclei depending upon the number of atoms in the molecule. Thus, an atomic orbital is monocentric while a molecular orbital is polycentric. Number 4, the number of molecular orbital formed is equal to the number of combining atom orbitals. When two atomic orbitals combine, two molecular orbitals are formed. One is known as bonding molecular orbital, while the other is called anti-bonding molecular orbital. Fifth, the bonding molecular orbital has lower energy and hence greater stability than the corresponding anti-bonding molecular orbital. Number 6, just as the electron probability distribution around a nucleus in an atom is given by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. Number 7, the molecular orbitals like atomic orbitals are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and the Hund's rule. 4.7.1, formation of molecular orbitals, linear combination of atomic orbitals. According to wave mechanics, the atomic orbitals can be expressed by wave function, which represent the amplitude of the electron waves. These are obtained from the solution of Schrodinger wave equation. However, since it cannot be solved for any system containing more than one electron, molecular orbitals, which are one electron wave function for molecules, are difficult to obtain directly from the solution of Schrodinger wave equation. To overcome this problem, an approximate method known as linear combination of atomic orbital has been adopted. Let us apply this method to the homonuclear diatomic hydrogen molecule. Consider the hydrogen molecule consisting of two atoms A and B. Each hydrogen atom in the ground state has one electron in one s orbital. The atomic orbitals of these atoms may be represented by the wave function psi A and psi B. Mathematically, the formation of the molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and by subtraction of wave function of individual atom orbitals as shown below. Psi MO is equals to psi A plus minus psi B. Therefore, the two molecular orbitals sigma and sigma star are formed. Here you can see the sigma is equals to psi A plus psi B and sigma star is equals to psi A minus psi B. The molecular orbital sigma formed by the addition of atomic orbitals is called the bonding molecular orbital, while the molecular orbital sigma star formed by the subtraction of atomic orbital is called anti-bonding molecular orbital as depicted in figure 4.19. Figure 4.19, here you can see the formation of bonding sigma and anti-bonding sigma star molecular orbitals by the linear combination of atomic orbitals psi A and psi B centered on two atoms A and B respectively. Qualitatively, the formation of molecule orbitals can be understood in terms of the constructive or destructive interference of the electron waves of the combining atoms. In the formation of bonding molecular orbital, the two electron waves of the bonding atoms reinforce each other due to constructive interference, while in the formation of anti-bonding molecular orbital, the electron waves cancel each other due to destructive interference. As a result, the electron density in a bonding molecular orbital is located between the nuclei of bonded atoms, because which the repulsion between the nuclei is very less, while in case of an anti-bonding molecular orbital, most of the electron density is located away from the space between the nuclei. In fact, there is a nodal plane on which the electron density is 0 between the nuclei and hence the repulsion between the nuclei is high. Electrons placed in a bonding molecular orbital tend to hold the nuclei together and stabilize a molecule. Therefore, a bonding molecular orbital always possesses lower energy than either of the atomic orbitals that have combined to form it. In contrast, the electrons placed in the anti-bonding molecular orbital destabilize the molecule. This is because the mutual repulsion of the electrons in this orbital is more than the attraction between the electrons and the nuclei, which causes a net increase in energy. It may be noted that energy of the anti-bonding orbital is raised above the energy of the parent atomic orbitals that have combined, and the energy of the bonding orbital has been lowered than the parent orbitals. The total energy of two molecular orbitals The total energy of two molecular orbitals, however, remains the same as that of two original atomic orbitals. 4.7.2 Conditions for the combination of atomic orbitals. The linear combination of atomic orbitals to form molecular orbitals takes place only if the following conditions are satisfied. Number 1. The combining atom orbitals must have the same or nearly the same energy. This means the first s orbital can combine with another 1s orbital but not with 2s orbital, because the energy of 2s orbital is appreciably higher than that of 1s orbital. This is not true if the atoms are very different. Number 2, the combining atomic orbitals must have the same symmetry about the molecular axis. By convention, z-axis is taken as the molecular axis. It is important to note that atomic orbital having same or nearly the same energy will not combine if they do not have the same symmetry. For example, 2pz orbital of one atom can combine with 2pz orbital of the other atom but not with the 2px or 2py orbitals because of their different symmetries. Number 3, the combining atom orbitals must overlap to the maximum extent. Greater the extent of overlap, the greater will be the electron density between the nuclei of a molecular orbital. 4.7.3 Types of molecular orbitals. Molecular orbitals of diatomic molecules are designated as sigma, pi, delta, etc. In this nomenclature, the sigma molecular orbitals are symmetrical around the bond axis, while pi molecular orbitals are not symmetrical. For example, the linear combination of 1s orbital centered on two nuclei produces two molecular orbitals which are symmetrical around the bond axis. Such molecular orbitals are of the sigma type and are designated as sigma 1s and sigma star 1s. If internuclear axis is taken to be in z direction, it can be seen that a linear combination of 2pz orbitals of two atoms also produces two sigma molecular orbitals designated as sigma 2pz and sigma star 2pz. Molecular orbitals obtained from 2px and 2py orbitals are not symmetrical around the bond axis because of the presence of positive lobes above and negative lobes below the molecular plane. Such molecular orbitals are labeled as pi and pi star, figure 4.20c. A pi bonding MO has large electron density above and below the internuclear axis. The pi star antibonding MO has a node between the nuclei. 4.7.4 Energy level diagram for molecular orbitals. We have seen that 1s atomic orbitals on two atoms from two molecular orbitals designated as sigma 1s and sigma star 1s. In the same manner, the 2s and 2p atomic orbital, here you can see 8 atomic orbitals. I will show this diagram again. On two atoms give rise to the following 8 molecular orbitals. Here you can see the antibonding and the bonding. Let me show you figure 4.20. The energy level of these molecular orbitals have been determined experimentally from spectroscopic data for homonuclear from diatomic molecules of second row elements of the periodic table. The increasing order of energies of various molecular orbitals for O2 and F2 is given below. Sigma 1s is less than sigma star 1s is less than sigma 2s is less than sigma star 2s is less than sigma 2pz is less than pi 2px equal to pi 2py is less than pi star 2px is equal to pi star 2py bracket close is less than sigma star 2pz. However, this sequence of energy levels of molecular orbital is not correct for the remaining molecules Li2, Be2, B2, C2, N2 for instance. It has been observed experimentally that for molecules such as B2, C2, N2, etc., the increasing order of energies of various molecular orbital is, here you can see, sigma 1s is less than sigma star 1s is less than sigma 2s is less than sigma star 2s is less than pi 2px is equal to pi 2py bracket close less than sigma 2pz is less than pi star 2px equal to pi star 2py is less than sigma star 2pz. The important characteristic feature of this order is that the energy of sigma 2pz molecular orbital is higher than that of pi 2px and pi 2py molecular orbitals. 4.7.5 Electronic configuration and molecular behavior. The distribution of electrons among various molecular orbital is called the electronic configuration of the molecule. From the electronic configuration of the molecule, it is possible to get important information about the molecule as discussed below. Stability of molecules. If Nb is the number of electrons occupying bonding orbitals and Na is the number of occupying the anti-bonding orbital, then the molecule number 1, the molecule is stable of Nb is greater than Na, and the molecule number 2, that is the molecule is unstable of Nb is less than Na. In first, more bonding orbitals are occupied and so the bonding influence is stronger and a stable molecule results. In second, the anti-bonding influence is stronger and therefore the molecule is unstable. Bond order. Bond order is defined as one of the difference between the number of electrons present in the bonding and the anti-bonding orbital. Bond order BO is equals to 1 by 2 Nb minus Na. The rules discussed above regarding the stability of the molecule can be restated in terms of bond order as follows. The positive bond order, that is Nb is greater than Na, means a stable molecule, while a negative, that is Nb is less than Na, or 0, that is Nb is equals to Na, bond order means an unstable molecule nature. Nature of the bond. Integral bond order values of 1, 2 or 3 correspond to single, double or triple bonds respectively as studied in the classical concept. Bond length. The bond order between two atoms in a molecule may be taken as an approximate measure of the bond length. The bond length decreases as bond order increases. Magnetic nature. If all the molecular orbitals in a molecule are doubly occupied, the substance is diamagnetic, repelled by magnetic field. However, if one or more molecular orbitals are singly occupied, it is paramagnetic, that is attracted by magnetic field. Example, O2 molecule. 4.8 Bonding in some homonuclear diatomic molecules. In this section, we shall discuss bonding in some homonuclear diatomic molecules. Number 1, hydrogen molecule. It is formed by the combination of two hydrogen atoms. Each hydrogen atom has one electron in one s orbital. Therefore, in all three are two electrons in hydrogen molecule which are present in sigma 1s molecular orbital. So, electronic configuration of hydrogen molecule is H2 ratio sigma 1s whole twice. The bond order of H2 molecule can be calculated as given below. Bond order is equals to Nb minus Na upon 2 is equals to 2 minus 0 upon 2 is equals to 1. This means that the two hydrogen atoms are bonded together by a single covalent bond. The bond dissociation energy of hydrogen molecule has been found to be 438 kJ per mole and bond length equal to 74 pm. Since no unpaired electron is present in hydrogen molecule, therefore it is diamagnetic. Number 2, helium molecule. The electronic configuration of helium atom is 1s2. Each helium atoms contain 2 electrons, therefore in He2 molecule, there would be 4 electrons. These electrons will be accommodated in sigma 1s and sigma star 1s molecular orbitals, leading to electronic configuration. Here you can see. He2 molecule is therefore unstable and does not exist. Similarly, it can be shown that Be2 molecule does not exist. Number 3, lithium molecule. The electronic configuration of lithium is 1s2, 2s1. There are 6 electrons in Li2. The electronic configuration of Li2 molecule therefore is Li ratio sigma 1s whole twice, sigma star 1s whole twice, sigma 2s whole twice. The above configuration is also written as Kk sigma 2s whole twice, where Kk presents the closed K shell structure, that is sigma 1s2 whole twice and sigma star 1s whole twice. From the electronic configuration of Li2 molecule, it is clear that 3 or 4 electrons present in bonding molecular orbitals and 2 electrons are present in anti-bonding molecular orbitals. It is bond order, therefore is 1 by 2, 4 minus 2 is equals to 1. It means that Li2 molecule is stable and since it has no unpaired electrons, it should be diamagnetic. Indeed, diamagnetic Li2 molecules are known to exist in the vapor phase. Number 4, carbon molecule. The electronic configuration of carbon is 1s2, 2s2, 2p2. Therefore, all 12 electrons in C2, the electronic configuration of C2 molecule, therefore, is C2. Here you can see this electronic configuration. The bond order of C2 is 1 by 2, 8 minus 4 is equals to 2, and C2 should be diamagnetic. Diamagnetic C2 molecules have indeed been detected in vapor phase. It is important to note that double bond in C2 consists of both pi bonds because of the presence of 4 electrons in 2 pi molecular orbitals. In most of the other molecules, a double bond is made up of a sigma bond and a pi bond. In a similar fashion, the bonding in N2 molecule can be discussed. 5. Oxygen molecule. The electronic configuration of oxygen atom is 1s2, 2s2, 2p4. Each oxygen atom has 8 electrons. Hence, in O2 molecule, there are 16 electrons. The electronic configuration of O2 molecule, therefore, is, you can see the electronic configuration. From the electronic configuration of O2 molecule, it is clear that 10 electrons are present in bonding molecular orbitals and 6 electrons are present in anti-bonding molecular orbital. Its bond order, therefore, is equals to 1 by 2, Nb minus Na is equals to 1 by 2, 10 minus 6 is equals to 2. So, in oxygen molecules, atoms are held by double bond. Moreover, it may be noted that it contains 2 unpaired electrons in pi star 2px and pi star 2py molecular orbitals. Therefore, O2 molecule should be paramagnetic, a prediction that corresponds to experimental observation. In this way, the theory successfully explains the paramagnetic nature of oxygen. Similarly, the electronic configuration of the homonuclear diatomic molecules of the second row of the periodic table can be written. In figure 4.21 are given the molecular orbital occupancy and molecular properties of B2 through Ne2. The sequence of MOs and their electron population are shown. The bond energy, bond length, bond order, magnetic properties, and valence electron configuration appear below the orbital diagrams. Here you can see the diagram. 4.9 Hydrogen bonding. Nitrogen, oxygen, and fluorine are the highly electronegative elements when they are attached to a hydrogen atom to form covalent bond. The electron of the covalent bond are shifted towards the more electronegative atom. This partially positively charged hydrogen atoms forms a bond with the other more electronegative atom. This bond is known as hydrogen bond, and is weaker than the covalent bond. For example, in HF molecule, the hydrogen bond exists between hydrogen atom of one molecule and fluorine atom of another molecule as depicted below. Here you can see the structure. Here hydrogen bond act as a bridge between two atoms which holds one atom by covalent bond and the other by hydrogen bond. Hydrogen bond is represented by a dotted line, while a solid line represents the covalent bond. Thus, hydrogen bond can be defined as the attractive force which binds hydrogen atom of one molecule with the electronegative atom, F, O or N, of another molecule. 4.9.1 Cause of formation of hydrogen bond. When hydrogen bond is bonded to strongly electronegative element X, the electron pair shared between the two atoms moves far away from the hydrogen atom. As a result, the hydrogen atoms becomes highly electropositive with respect to the other atom X. Since there is displacement of electrons towards X, the hydrogen acquires fractional positive charge while X attains fractional negative charge. This results in the formation of polar molecule having electrostatic force of attraction, which can be represented as: the magnitude of hydrogen bond depends on the physical state of the compound. It is maximum in the solid state and minimum in the gaseous state. Thus, the hydrogen bonds have a strong influence on the structure and properties of the compounds. 4.9.2 Types of hydrogen bonds. There are two types of hydrogen bonds. Number 1, intermolecular hydrogen bond. Number 2, intramolecular hydrogen bond. Number 1, intermolecular hydrogen bond. It is formed between two different molecules of the same or different types of compounds. For example, hydrogen bond in case of HF molecule, alcohol or water molecules, etc. Number 2, intramolecular hydrogen bond. It is formed when hydrogen atom is in between the two highly electronegative, that is F, O, and atoms present within the same molecule. For example, in orthonitrophenol, the hydrogen is in between the two oxygen atoms. Figure 4.22 you can see. Finally, summary. Kozl's first insight into the mechanism of formation of electropositive and electronegative ions related the process to attainment of noble gas configuration by the respective ions. Electrostatic attraction between ions is the cause for their stability. This gives the concept of electrovalency. The first description of covalent bonding was provided by Lewis in terms of sharing of electron pairs between atoms, and he related the process to the attainment of noble gas configuration by reaching atoms as a result of sharing of electrons. The Lewis dot symbols show the number of valence electrons of the atoms of a given element, and Lewis dot structures show pictorial representation of bonding in molecules. An ionic compound is pictured as three-dimensional aggregation of positive and negative ions in an ordered arrangement called the crystal lattice. In a crystalline solid, there is a charge balance between the positive and negative ions. The crystal lattice is stabilized by the enthalpy of lattice formation. While a single covalent bond is formed by sharing of an electron pair between two atoms, multiple bonds result from the sharing of 2 or 3 electron pairs. Some bonded atoms have additional pairs of electrons not involved in bonding. These are called lone pairs of electrons. A Lewis dot structure shows the arrangement of bonded pairs and lone pairs around each atom in a molecule. Important parameters associated with chemical bonds like bond length, bond angle, bond enthalpy, bond order, and bond polarity have significant effect on the properties of compound. A number of molecules and polyatomic ions cannot be described accurately by a single Lewis structure, and a number of descriptions, that is representation based on the same skeletal structure, are written, and these taken together represent the molecule or ion. This is a very important and extremely useful concept called resonance. The contributing structures are canonical forms taken together constitute the resonance hybrid, which represent the molecule or ion. The VSEPR model used for predicting the geometrical shapes of molecule is based on the assumption that electron pairs repel each other and therefore tend to remain as far apart as possible. According to this model, molecular geometry is determined by repulsion between lone pairs and lone pairs, lone pairs and bonding pairs, and bonding pairs and bonding pairs. The order of these repulsion being LP is greater than LP is greater than BP. The valence bond approach to covalent bonding is basically concerned with the energetics of covalent bonding formation, about which the Lewis and VSEPR models are silent. Basically, the VB theory discusses bond formation in terms of overlap of orbitals. For example, the formation of H2 molecule from two hydrogen atoms involves the overlap of the 1s orbitals of the two hydrogen atoms which are singly occupied. It is seen that the potential energy of the system gets lowered as the two hydrogen atoms come near to each other. At equilibrium internuclear distance, that is bond distance, the energy touches a minimum. Any attempt to bring the nuclei still closer results in a sudden increase in energy and consequent destabilization of the molecule. Because of orbital overlap, the electron density between the nuclei increases, which helps in bringing them closer. It is, however, seen that the actual bond enthalpy and bond length values are not obtained by overlap alone, and other variables have to be taken into account. For explaining the characteristic shapes of polyatomic molecules, Pauling introduced the concept of hybridization of atomic orbitals. sp, sp2, sp3 hybridization of atomic orbitals of Be, B, C, N, and O are used to explain the formation and geometrical shapes of molecules like BeCl2, BCl3, CH4, NH3, and H2O. They also explain the formation of multiple bonds in molecules like C2H2 and C2H4. The molecular orbital theory describes the bonding in terms of the combination and arrangement of atomic orbitals to form molecular orbitals that are associated with the molecule as a whole. The number of molecular orbitals are always equal to the number of atomic orbitals from which they are formed. Bonding molecular orbitals increase electron density between the nuclei and are lower in energy than the individual atomic orbitals. Anti-bonding molecular orbitals have a region of zero electron density between the nuclei and have more energy than the individual atomic orbitals. The electronic configuration of the molecules is written by fulfilling electrons in the molecular orbitals in order of increasing energy levels. As in the case of atoms, the Pauli exclusion principle and Hund's rule are applicable for the filling of molecular orbitals. Molecules are said to be stable if the number of electrons in bonding molecular orbital is greater than that in anti-bonding molecular orbitals. Hydrogen bond is formed when a hydrogen atom finds itself between two highly electronegative atoms such as fluorine, oxygen and nitrogen. It may be intermolecular, that is existing between two or more molecules of the same or different substances, or intramolecular, that is when present within the same molecule. Hydrogen bonds have a powerful effect on the structure and properties of many compounds. हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज मैं करने जा रही हूँ यूनिट 5 स्टेट्स ऑफ मैटर। तो आप लोगों की जैसे रिक्वेस्ट आ रही है ऑडियो बुक्स के लिए, मैं उस हिसाब से ही चैप्टर प्रिपेयर कर रही हूँ और मेरी प्रायोरिटी ये है कि थ्योरेटिकल चैप्टर्स को मैं पहले कवर कर लूँ। तो आप लोग कमेंट सेक्शन में मुझे अपने चैप्टर्स बताते जाइएगा। ऑल्दो आई विल कंप्लीट बिफोर नीट एग्जाम ऑल दी केमिस्ट्री चैप्टर्स सो दैट यू कैन डू योर रिविजन एट योर बेस्ट, राइट। बट थोड़ा सा टाइम लगेगा रिकॉर्ड करने में। सो चलिए टाइम वेस्ट नहीं करते हैं और शुरू करते हैं। स्टेट्स ऑफ मैटर। द स्नोफ्लेक फॉल्स येट लेज नॉट लॉन्ग इट्स फेदरी ग्रास्प ऑन मदर अर्थ ere sun returns it to the vapor whence it came or to water tumbling down the rocky slope. रॉड ओ कॉर्नर ने दिया था ये। Introduction. In previous unit we have learned about the properties related to single particle matter and much as atomic size, ionization enthalpy, electronic charge, density, molecular shape and polarity, etc. Most of the observable characteristics of chemical system with which we are familiar represent bulk properties of matter, that is, the properties associated with a collection of large number of atoms, ions and molecules. For example, an individual molecule of a liquid does not boil but the bulk boils. Collection of water molecules have wetting properties. Individual molecules do not wet. Water can exist as ice, which is as solid. It can exist as liquid, or it can exist in the gaseous state as water vapor or steam. Physical properties of ice, water and steam are very different. In all the three states of water, chemical composition of water remains the same, that is H2O. Characteristics of the three states of water depend on the energies of the molecules and on the manner in which water molecules aggregate. Same is true for the substances also. Chemical properties of a substance do not change with the change of its physical state, but rate of chemical reaction do depend upon the physical state. Many times in calculation, while dealing with data of experiments, we require knowledge of the state of matter. Therefore, it becomes necessary for a chemist to know the physical laws which govern the behavior of matter in different states. In this unit, we will learn more about these three physical states of matter, particularly liquid and gaseous states. To begin with, it is necessary to understand the nature of intermolecular forces, molecular interactions, and effect of thermal energy on the motion of particles, because a balance between these determines the state of a substance. 5.1 Intermolecular Forces. Intermolecular forces are the forces of attraction and repulsion between interacting particles, that is atom and molecules. This term does not include the electrostatic forces that exist between the two oppositely charged ions and the forces that holds atom of a molecule together, that is covalent bond. Attractive intermolecular forces are known as van der Waals forces, in honor of Dutch scientist Johannes van der Waals 1837 to 1923, who explained the aviation of real gases from the ideal behavior through these forces. We will learn about this later in this unit. Van der Waals forces vary considerably in magnitude and include dispersion forces or London forces, dipole-dipole forces and dipole-induced dipole forces. A particularly strong type of dipole-dipole interaction is hydrogen bonding. Only a few elements can participate in hydrogen bonding, or you can say in hydrogen bond formation. Therefore, it is treated as a separate category. We have already learnt about this interaction in Unit 4. At this point, it is important to note that attractive forces between an ion and a dipole are known as ion dipole forces, and these are not van der Waals forces. We will now learn about different types of van der Waals forces. 5.1.1 Dispersion forces or London forces. Atoms and nonpolar molecules are electrically symmetrical and have no dipole moment because their electronic charge cloud is symmetrically distributed. But a dipole may develop momentarily even in such atoms and molecules. This can be understood as follows. Suppose we have two atoms A and B in the close vicinity of each other, figure 5.1a. It may, here you can see this diagram 5.1a. It may so happen that momentarily electronic charge distribution in one of the atoms, say A, becomes unsymmetrical, that is, the charge cloud is more on one side than the other. Figure 5.b and c. This results in the development of instantaneous dipole on the atom A for a very short time. Here you can see the diagrams 5.1a, 5.1b and 5.1c. This instantaneous or transient dipole distorts the electron density of the atom B, which is close to it. As consequence, a dipole is induced in the atom B. The temporary dipoles of atom A and B attract each other. Similarly, temporary dipoles are induced in molecule also. This force of attraction was proposed by the German physicist Fritz London. And for this reason, force of attraction between two temporary dipole is known as London force. Another name for this force is dispersion force. These forces are always attractive and interaction energy is inversely proportional to the sixth power of the distance between the two interacting particles, that is 1 upon r to the power 6, where r is the distance between two particles. These forces are important only at short distances, that is approximately 500 picometer, and their magnitude depends on the polarizability of the particle. 5.1.2 Dipole-dipole forces. Dipole-dipole forces act between the molecules possessing permanent dipole. Ends of the dipole possesses partial charges, and these charges are shown by Greek letter delta. Partial charges are always less than the unit electronic charge 1.6 into 10 to the power minus 19, and the polar molecules interact with neighboring molecules. Figure 5.2a shows electron cloud distribution in the dipole of hydrogen chloride, and figure 5.2b shows dipole-dipole interaction between two HCl molecules. I will show you diagram later. This interaction is stronger than the London force but is weaker than ion-ion interaction because only partial charges are involved. The attractive force decreases with the increase of distance between the dipoles. As in the above case, here also the interaction energy is inversely proportional to distance between polar molecules. Dipole-dipole interaction energy between stationary polar molecule, as in solids, in proportional to 1 upon r cube, and that between rotating polar molecule is. Now you can see 5.2a diagram, that is the distribution of electron cloud in HCl, a polar molecule, and B diagram is dipole-dipole interaction between two HCl molecule. Come to the next slide. Proportional to 1 upon r to the power 6, where r is the distance between polar molecules. Besides dipole-dipole interaction, polar molecules can interact by London forces also. Thus, cumulative effect is that the total of intermolecular forces in polar molecules increase. 5.1.3 Dipole-induced dipole forces. This type of attractive forces operate between the polar molecules having permanent dipole and the molecules lacking permanent dipole. Permanent dipole of the polar molecule induces dipole on the electrically neutral molecule by deforming its electronic cloud. Thus, an induced dipole is developed in the other molecule. In this case, also interaction energy is proportional to 1 upon r to the power 6, where r is the distance between the two molecules. Induced dipole moments depends upon the dipole moment present in the permanent dipole and polarizability of the electrically neutral molecule. We have already learnt in Unit 4 that molecules of larger size can be easily polarized. High polarizability increases the strength of attractive interactions. Here you can see 5.3 dipole-induced dipole interaction between permanent dipole and induced dipole. In this case, also cumulative effect of dispersion forces and dipole-induced dipole interaction exist. 5.1.4 Hydrogen bond. As already mentioned in section 5.1, this is a special case of dipole-dipole interaction. We have already learnt about this in Unit 4. This is found in the molecules in which highly polar NH, OH and HF bonds are present. Although hydrogen bonding is regarded as being limited to nitrogen, oxygen and fluorine, but species such as chloride negative may also participate in hydrogen bonding. Energy of hydrogen bond varies between 10 to 100 kilojoule per mole. This is quite a significant amount of energy. Therefore, hydrogen bonds are powerful force in determining the structure and properties of many compounds, for example, proteins and nucleic acids. Strength of the hydrogen bond is determined by the Coulombic interaction between the lone pair electrons of the electronegative atom of one molecule and the hydrogen atom of other molecule. Following diagram shows the formation of hydrogen bond. Here you can see. Intermolecular forces discussed so far are all attractive. Molecules also exert repulsive forces on one another. When two molecules are brought into close contact with each other, the repulsion between the electron clouds and that between the nuclei of two molecules comes into play. Magnitude of the repulsion rises very rapidly as the distance separating the molecule decreases. This is the reason that liquids and solids are hard to compress. In these states, molecules are already in close contact. Therefore, they resist further compression as that would result in the increase of repulsive interactions. 5.2 Thermal energy. Thermal energy is the energy of body arising from motion of its atoms or molecules. It is directly proportional to the temperature of the substance. It is the measure of average kinetic energy of the particles of the matter and is thus responsible for movement of particles. This movement of particles is called the thermal motion. 5.3 Intermolecular forces versus thermal interaction. We have already learned that intermolecular forces tend to keep the molecules together, but thermal energy of the molecules tends to keep them apart. Three states of matter are the results of balance between intermolecular forces and the thermal energy of the molecules. When molecular interactions are very weak, molecules do not cling together to make liquid or solid unless thermal energy is reduced by lowering the temperature. Gases do not liquefy on compression only. All the molecules come very close to each other and intermolecular forces operate to the maximum. However, when thermal energy of molecule is reduced by lowering the temperature, the gases can be very easily liquefied. Predominance of thermal energy and the molecular interaction energy of a substance in three states is depicted as follows. Here you can see gas to liquid and liquid to solid. Predominance of intermolecular interaction, and here you can see solid to liquid and liquid to gas. Predominance of the thermal energy. We have already learned the cause for the existence of the three states of matter. Now we will learn more about gaseous and liquid states and the laws which govern the behavior of matter in these states. We shall deal with the solid state in class 12th. 5.4 The gaseous state. This is the simplest state of matter. Throughout our life, we remain immersed in the ocean of air, which is a mixture of gases. We spend our life in the lowermost layer of the atmosphere called troposphere, which is held to the surface of the earth by gravitational force. The thin layer of atmosphere is vital to our life. It shields us from harmful radiations and contains substances like dioxygen, dinitrogen, carbon dioxide, water vapor, etc. Let us now focus our attention on the behavior of substances which exist in the gaseous state under normal conditions of temperature and pressure. A look at the periodic table shows that only 11 elements exist as gases under normal condition. Figure 5.4. Here you can see the diagram. Here you can see all the 11 elements that exist as gases. The gaseous state is characterized by the following physical properties. Gases are highly compressible. Gases exert pressure equally in all directions. Gases have much lower density than the solids and liquids. The volume and the shape of gases are not fixed. These assume volume and shape of the container. Gases mix evenly and completely in all proportions without any mechanical aid. Simplicity of gases is due to the fact that the forces of interaction between their molecules are negligible. Their behavior is governed by some same general laws, which were discovered as a result of their experimental studies. These laws are relationship between measurable properties of gases. Some of these properties like pressure, volume, temperature, and mass are very important because relationship between these variables describe state of the gas. Interdependence of these variables leads to the formulation of gas laws. In the next section, we will learn about gas laws. 5.5 The gas laws. The gas laws which we will study now are the result of research carried on several centuries on the physical properties of gases. The first reliable measurement on properties of gases was made by Anglo-Irish scientist Robert Boyle in 1662. The law which he formulated is known as Boyle's law. Later on, attempts to fly in air with the help of hot air balloons motivated Jacques Charles and Joseph Louis Gay Lussac to discover additional gas laws. Contribution from Avogadro and other provided lot of information about gaseous state. 5.5.1 Boyle's law, that is pressure-volume relationship. On the basis of experiment, Robert Boyle reached to the conclusion that at constant temperature, the pressure of a fixed amount, that is the number of moles n, of gas varies inversely with its volume. This is known as Boyle's law. Mathematically, it can be written as P is proportional to 1 upon V at constant T and N. And now P is equals to K1 1 upon V. This is the equation 5.2, where K1 is the proportionality constant. The value of constant K1 depends upon the amount of gas, temperature of the gas, and the units in which P and V are expressed. On rearranging equation 5.2, we obtain PV is equals to K1, that is 5.3 equation. It means that at constant temperature, product of pressure and volume of a fixed amount of gas is constant. If a fixed amount of gas at constant temperature T occupying volume V1 at pressure P1 undergoes expansion, so that volume becomes V2 and pressure becomes P2, then according to Boyle's law, P1 V1 is equals to P2 V2 is equals to constant, and this is the equation number 5.4. So P1 upon P2 is equals to V2 upon V1. Now you can see this graph 5.5a, graph of pressure P versus volume V of a gas at different temperature. And here you can see the next graph 5.5b, graph of pressure of a gas P versus 1 upon V. Here you can see the table 5.1, the effect of pressure on the volume of 0.09 mole CO2 gas at 300 Kelvin. Figure 5.5 shows two conventional ways of graphically representing Boyle's law. Figure 5.5a is the graph of equation 5.3 at different temperatures, and the value of K1 for each curve is different because for a given mass of gas, it varies only with temperature. Each curve corresponds to a different constant temperature and is known as isotherm, that is constant temperature plot. Higher curves correspond to higher temperature. It should be noted that volume of the gas doubles if pressure is halved. Table 5.1 gives effect of pressure on volume of 0.09 mole of CO2 at 300 Kelvin. Figure 5.5b represents the graph between P and 1 upon V. It is a straight line passing through origin. However, at high pressure, gases deviate from Boyle's law, and under such condition, a straight line is not obtained in the graph. Experiments of Boyle in a quantitative manner prove that gases are highly compressible because when a given mass of a gas is compressed, the same number of molecules occupy a smaller space. This means that gases become denser at high pressure. A relationship can be obtained between density and pressure of a gas by using Boyle's law. By definition, density D is related to the mass m and the volume V by the relation D is equals to m upon V. If we put value of V in this equation from Boyle's law equation, we obtain the relationship. D is equals to M upon K1 bracket close P is equals to K dash P. This shows that at a constant temperature, pressure is directly proportional to the density of a fixed mass of the gas. Here you can see the problem 5.1. Now 5.5.2 Charles' law, that is temperature volume relationship. Charles and Gay-Lussac performed several experiments on gases independently to improve upon hot air balloon technology. Their investigation showed that for a fixed mass of a gas at constant constant pressure, volume of a gas increasing temperature and decrease on cooling. They found that each degree rise in temperature, volume of a gas increases by 1 upon 273.15 of the original volume of the gas at 0 degrees Celsius. Thus, if volumes of the gas at 0 degrees Celsius and T degrees Celsius are V0 and Vt respectively, then Vt is equals to V0 plus T upon 273.15 multiplied V0. And now Vt is equals to V0 in bracket 1 plus T upon 273.15. So Vt is equals to V0 bracket 273.15 plus T upon 273.15. At this stage, we define a new scale of temperature such that T degrees Celsius on new scale is given by T is equals to 273, that is capital T, is equals to 273.15 plus small t, and 0 degrees Celsius will be given. So T0 is equals to 273.15. This new temperature scale is called Kelvin temperature scale or absolute temperature scale. The 0 degree Celsius on the Celsius scale is equal to 273.15 Kelvin at the absolute scale. Note that degree sign is not used while writing the temperature in absolute temperature scale, that is Kelvin scale. Kelvin scale of temperature is also called thermodynamic scale of temperature and is used in all scientific works. Thus, we add 273, that is more precisely 273.15 to the Celsius temperature to obtain temperature at Kelvin cycle or Kelvin scale, If we write Tt is equals to 273.15 plus a small t and T0 is equals to 273.15 in the equation 5.6, we obtain the relationship Vt is equals to V0 in bracket Tt upon T0. Vt upon V0 is equals to Tt upon T0. Thus, we can write a general equation as V2 upon V1 is equals to T2 upon T1, or V1 upon T1 is equals to V2 upon T2, or we can say V upon T is equals to constant, that is K2. So, V is equals to K2T, that T is capital T. The value of constant K2 is determined by the pressure of the gas, its amount, and the units in which volume V is expressed. Equation 5.10 is the mathematical expression for Charles' law, which states that pressure remaining constant, the volume of a fixed mass of a gas is directly proportional to its absolute temperature. Charles found that for all gases at any given pressure, graph of volume versus temperature in Celsius is a straight line, and on extending to a zero volume, each line intercepts the temperature axis at minus 273.15 degrees Celsius. Slopes of lines obtained at different pressure are different, but a zero volume, all the lines meet the temperature axis at minus 273.15 degrees Celsius, and here you can see figure 5.6. Figure 5.6, that is volume versus temperature graph. Each line of the volume versus temperature graph is called isobar. Observation of Charles can be interpreted if we put the value of T in equation 5.6 as minus 273.15 degrees Celsius, we can see that the volume of the gas at minus 273.15 degrees Celsius will be 0. This means that the gas will not exist. In fact, all the gases get liquefied before this temperature is reached. The lowest hypothetical or imaginary temperature at which gases are supposed to occupy zero volume is called absolute zero. All gases obey Charles' law at very low pressure and high temperature. 5.5.3 Gay-Lussac law, that is pressure-temperature relationship. Pressure in well-inflated tires of automobile is almost constant, but on a hot summer day this increases considerably and tire may burst if pressure is not adjusted properly. During winters, on a cold morning, one may find the pressure in the tires of a vehicle decreased considerably. The mathematical relationship between pressure and temperature was given by Joseph Gay-Lussac and is known as Gay-Lussac law. It states that at constant volume, pressure of a fixed amount of gas varies directly with the temperature. Mathematically, that is P is proportional to T and P upon T is equals to constant, that is K3. This relationship can be derived from Boyle's law and Charles' law. Pressure versus temperature graph at constant molecular volume constant molar volume is shown in figure 5.7. Each line of this graph is called isochore. 5.5.4 Avogadro law, and here you can see the figure 5.7, that is pressure versus temperature graph of a gas. Now 5.5.4 Avogadro law, that is volume amount relationship. In 1811, Italian scientist Amedeo Avogadro tried to combine conclusions of Dalton's atomic theory and Gay-Lussac law of combining volumes, that is unit 1, which is now known as Avogadro law. It states that equal volumes of all gases under the same conditions of temperature and pressure contain equal number of molecules. This means that as long as the temperature and pressure remain constant, the volume depends upon number of molecules of the gas, or in other words, amount of the gas. Mathematically, we can write V is proportional to N, where N is the number of moles of the gas, V is equals to K4N, and the number of molecules in 1 mole of a gas has been determined to be 6.022 into 10 to the power 23 and is known as Avogadro constant. You will find that this is the same number which we came across while discussing the definition of a mole, that is in unit 1. Since volume of a gas is directly proportional to the number of moles, 1 mole of each gas at a standard temperature and pressure, that is STP, will have same volume. Standard temperature and pressure means 273.515 Kelvin, that is 0 degree Celsius temperature, and 1 bar, that is exactly 10 to the power 5 Pascal pressure. These values approximate freezing temperature of water and atmospheric pressure at sea level. At STP, molar volume of an ideal gas or a combination of ideal gases is 22.71098 liter per mole. Molar volume of some gases is given in table 5.2. Here you can see the molar volume in liters per mole of some gases at 273.15 Kelvin and 1 bar. Argon 22.37, carbon dioxide 22.54, dinitrogen 22.69, dioxygen 22.69, dihydrogen 22.72, ideal gas 22.71. Number of moles of gas can be calculated as follows. N is equals to m upon m, where small m is the mass of the gas under investigation and capital M is the molar mass. V is equals to K4 m upon m, and equation 5.13 can be rearranged as follows. M is equals to K4 m upon m is equals to K4D. The previous standard, that is a star point which I am reading, the previous standard is still often used and applies to all chemistry data more than decade old. In this definition, STP denotes the same temperature of 0 degree Celsius but a slightly high pressure of 1 atmosphere. 1 mole of any gas of a combination of gases occupies 22.413996 liter of volume at STP. Standard ambient temperature and pressure, that is SATP, conditions are also used in some scientific works. SATP conditions means 298.15 Kelvin and 1 bar, that is exactly 10 to the power 5 Pascal. At SATP 1 bar and 298.15 Kelvin, the molar volume of an ideal gas is 24.789 liter per mole. Here D is the density of the gas. We can conclude from equation 5.14 that the density of a gas is directly proportional to its molar mass. A gas that follows Boyle's law, Charles' law and Avogadro law is called an ideal gas. Such as gas is hypothetical. It is assumed that intermolecular forces are not present between the molecules of an ideal gas. Real gases follow these laws under a certain specific condition when forces of interaction are practically negligible. In all other situations, these deviate from ideal behavior. You will learn about the deviations later in this unit. 5.6 Ideal Gas Equation. The three laws which we have learned till now can be combined together in a single equation which is known as ideal gas equation. At constant temperature and N is equals to V is proportional to 1 upon P, that is the Boyle's law. As per the Charles law, at constant P and N, V is directly proportional to T, and at constant P and T, as per the Avogadro's law, that is V is directly proportional to N. Thus, V is proportional to Nt upon P and V is equals to Rnt upon P, where R is the proportionality constant. On rearranging the equation 5.16, this is the equation 5.16, we obtain PV is equals to nRT and the value of R is equals to PV upon Nt. R is called gas constant. It is same for all gases. Therefore, it is also called universal gas constant. That is equation 5.17 is ideal gas equation, that is PV is equals to nRT. Equation 5.18 shows that the value of R depends upon units in which P, V and T are measured. If three variables in this equation are known, fourth can be calculated. From this equation, we can see that at constant temperature and pressure, n moles of any gas will have the same volume because V is equals to nRT upon P and nRT and P are constant. This equation will be applicable to any gas under those conditions when behavior of the gas approaches ideal behavior. Volume of 1 mole of an ideal gas under STP condition, that is 273.15 Kelvin and 1 bar pressure, is 22.710981 liter per mole. Value of R for 1 mole of an ideal gas can be calculated under these conditions as follows. Here you can see the value of R, the final value of R after putting all these values, we will get 8.314 joule per kilo per mole. At STP conditions used earlier, 0 degree Celsius and 1 atmospheric pressure, value of R is 8.20578 into 10 to the power minus 2 L atmospheric per Kelvin per mole. Ideal gas equation is a relation between four variables and it describes the state of any gas. There it is also called equation of state. Let us now go back to the ideal gas equation. This is the relationship for the simultaneous variation of the variables. If temperature, volume and pressure of a fixed amount of gas vary T1 V1 and P1 to T2 V2 and P2, then we will write P1 V1 upon T1 is equals to P2 V2 upon T2. Equation 5.19 is very useful equation. If out of 6 values of 5 variables are known, the value of a known variable can be calculated from the equation 5.19. This equation is also known as combined gas law. 5.6.1 Density and molar mass of gaseous substance. Ideal gas equation can be rearranged as follows. N upon V is equals to P upon RT, and replacing N by M upon M, we can get M upon MV is equals to PRT, or you can say the D upon M is equals to P upon RT, where D is the density. On rearranging the equation, we get the relationship for calculating molar mass of gas, that is capital M is equals to dRT upon P. 5.6.2 Dalton's law of partial pressures. The law was formulated by John Dalton in 1801. It states that the total pressure exerted by the mixture of non-reactive gases is equal to the sum of the partial pressures of individual gases, that is the pressures which these gases would exert if they were enclosed separately in the same volume and under the same conditions of temperature. In a mixture of gases, the pressure exerted by the individual gas is partial pressure. Mathematically, P total is equals to P1 plus P2 plus P3 plus at constant T and V, that is up to the infinite, where P total is the total pressure exerted by the mixture of gases and P1, P2, P3 etc. are partial pressures of gases. Gases are generally collected over water and therefore are moist. Pressure of dry gas can be calculated by subtracting vapor pressure of water from the total pressure of the moist gas which contains water vapors also. Pressure exerted by saturated water vapor is called aqueous tension. Aqueous tension of water at different temperature is given in table 5.3. P dry gas is equals to P total minus aqueous tension. Now, table 5.3, that is the aqueous tension of water, that is the vapor pressure as a function of temperature. Here you can see all the values. Partial pressure in terms of mole fraction. Suppose at the temperature T, three gases enclosed in the volume V exert partial pressure P1, P2 and P3 respectively. Then P1 is equals to N1 RT upon V, P2 is equals to N2 RT upon V and P3 is equals to N3 RT upon V, where N1, N2 and N3 are number of moles of these gases. Thus expression for total pressure will be P total is equals to P1 plus P2 plus P3. That is N1 upon RT, N1 RT upon V plus N2 RT upon V plus N3 RT upon V. N1 plus N2 plus N3 in bracket and RT upon V. On dividing by P1 by P total, we will get P1 upon P total is equals to N1 upon N1 plus N2 plus N3 in bracket close and RTV upon RTV, where N is equals to N1 plus N2 plus N3. Here you can see the whole derivation. X1 is called mole fraction of first gas, thus P1 is equals to X1 P total. Similarly, for other two gases, we can write P2 is equals to X2 P total and P3 is equals to X3 P total. Thus, a general equation can be written as P1 Pi is equals to Xi P total, where Pi and Xi are partial pressure and mole fraction of ith gas respectively. If total pressure of a mixture of a gas is known, the equation 5.29, this is the equation 5.29, can be used to find out pressure exerted by individual gases. You can see the problem 5.4. Now 5.7, kinetic energy and molecular speeds. Molecules of gases remain in continuous motion. While moving, they collide with each other and with the walls of the container. This results in change of their speed and redistribution of energy. So the speed and energy of all the molecules of the gas at any instant are not the same. Thus, we can obtain only average value of speed of molecules. If there are n number of molecules in a sample and their individual speeds are u1, u2 up to the un, then average speed of molecules U average can be calculated as follows. U average is equals to u1 plus u2 plus up to the un upon n. Maxwell and Boltzmann have shown that actual distribution of molecular speeds depends on temperature and molecular mass of gas. Maxwell derived a formula for calculating the number of molecules possessing a particular speed. Figure 5.8 shows a schematic plot of number of molecule versus molecular speed at two different temperatures T1 and T2, where T2 is higher than T1. The distribution of speed shown in the plot is called Maxwell-Boltzmann distribution of speed. Here you can see this figure 5.8. The graph shows that number of molecules possessing very high and very low speed is very small. The maximum in the curve represents speed possessed by maximum number of molecules. This speed is called most probable speed, UMP. This is very close to the average speed of the molecules. On increasing the temperature, most probable speed increases. Also, speed distribution curve broadens at higher temperature. Broadening of the curve shows that number of molecules moving at higher speed increases. Speed distribution also depends upon mass of molecules. At the same temperature, gas molecules with heavier mass have slower speed than lighter gas molecules. For example, at the same temperature, light nitrogen molecules move faster than heavier chlorine molecules. Hence, at any given temperature, nitrogen molecules have higher value of most probable speed than the chlorine molecules. Look at the molecular speed distribution curve of chlorine and nitrogen given in figure 5.9. Here is the figure 5.9. Though at a particular temperature the individual speed of molecules keeps changing, the distribution of speeds remains same. We know that kinetic energy of a particle is given by the expression kinetic energy is equals to half mu square. Therefore, if we want to know average translational kinetic energy, half mu square for the movement of a gas particle in a straight line, we require the value of mean of square speeds. U square of all molecules, this is represented as follows. Here you can see this. The mean square speed is the direct measure of the average kinetic energy of gas molecules. If we take the square root of the mean of square root of speeds, then we get a value of speed which is different from the most probable speed and average speed. This speed is called root mean square speed and is given by the expression as follows. Root square speed, average speed and the most probable speed have following relationship. You can see URMS is greater than U average is greater than UMP. That is the most probable speed. The ratio between the three speeds is given below, that is the 1:1.128 to 1.224. 5.8 Kinetic Molecular Theory of Gases. So far we have learned the laws, that is Boyle's law, Charles' law, etc., which are concise statements of experimental facts observed in the laboratory by the scientist. Conducting careful experiment is an important aspect of scientific methods and it tells us how the particular system is behaving under different conditions. However, once the experimental facts are established, a scientist is curious to know why the system is behaving in that way. For example, gas laws help us to predict that pressure increases when we compress gases, but we would like to know what happens at molecular level when a gas is compressed. A theory is constructed to answer such questions. A theory is a model, that is a mental picture that enables us to better understand an observation. The theory that attempts to elucidate the behavior of gas is known as kinetic molecular theory. Assumptions or postulates of the kinetic molecular theory of gas are given below. These postulates are related to atoms and molecules which cannot be seen, hence it is said to provide a microscopic model of gases. Gases consist of a large number of identical particles, that is atoms or molecules, that are so small and so far apart on the average that the actual volume of the molecules is negligible. In comparison to the empty space between them, they are considered as point masses. This assumption explains the great compressibility of gases. There is no force of attraction between the particle of gas at ordinary temperature and pressure. The support for this assumption comes from the fact that gases expand and occupy all the space available to them. Particles of gas are always in constant and random motion. If the particles were at rest and occupied fixed positions, then a gas would have had a fixed shape which is not observed. Particles of a gas move in all possible directions in straight lines. During their random motion, they collide with each other and with the walls of the container. Pressure is exerted by the gas as a result of collision of the particles with the walls of the container. Collisions of gas molecules are perfectly elastic. This means that total energy of molecules before and after the collision remains same. There may be exchange of energy between colliding molecules. Their individual energies may change, but the sum of their energies remains constant. There was loss of kinetic energy. The motion of molecules will stop and gases will settle down. This is contrary to what is actually observed. At any particular time, different particles in the gas have different speeds and hence different kinetic energy. This assumption is reasonable because as the particles collide, we expect their speed to change. Even if initial speed of all the particles was the same, the molecular collisions will disrupt this uniformity. Consequently, the particles must have different speeds which go on changing constantly. It is possible to show that though the individual speeds are changing, the distribution of speeds remains constant at a particular temperature. If a molecule has variable speed, then it must have a variable kinetic energy. Under these circumstances, we can talk only about average kinetic energy. In kinetic theory, it is assumed that the average kinetic energy of the gas molecule is directly proportional to the absolute temperature. It is seen that on heating of a gas at constant volume, the pressure increases. On heating the gas, kinetic energy of the particles increases and these strike the walls of the container more frequently, thus exerting more pressure. Kinetic theory of gases allows us to derive theoretically all the gas laws studied in the previous section, calculations and predictions based on the kinetic theory of gases agree very well with the experimental observation and thus establish the correctness of this model. 5.9 Behavior of real gases, deviation from ideal gas behavior. Our theoretical model of gases correspond very well with the experimental observations. Difficulty arises when we try to test how far the relation PV is equals to nRT reproduce actual pressure volume temperature relationship of gases. To test this point, we plot PV versus P plot of gases because at constant temperature. PV will be constant at Boyle's law and PV versus P graph at all pressure will be straight line parallel to x-axis. Figure 5.10 shows such a plot constructed from an actual data for several gases at 273 Kelvin. Here you can see figure 5.10 and the next figure is figure 5.11. It can be seen easily that at constant temperature PV versus P plot for real gases is not a straight line. There is a significant deviation from ideal behavior. The two types of curves are seen. In the curves for dihydrogen and helium, as the pressure increases, the value of PV also increases. The second type of plot is seen in the case of other gases like carbon monoxide and methane. In these plots, first there is a negative deviation from ideal behavior and the PV value decreases with the increase in pressure and reaches to a minimum value characteristic of a gas. After that PV value starts increasing, the curve then crosses the line for ideal gas and after that shows positive deviation continuously. It is thus found that real gases do not follow ideal gas equation perfectly under all conditions. Deviation from ideal behavior also becomes apparent when the pressure versus volume plot is drawn. The pressure versus volume plot is experimental data, that is real gas, and that theoretically calculated from Boyle's law, that is ideal gas, should coincide. Figure 5.11 shows these plots. It is apparent that at very high pressure, the measured volume is more than the calculated volume. At low pressures, measured and calculated volumes approach each other. Here you can see the figure 5.11 again, that is a plot of pressure versus volume of real gas and ideal gas. It is found that real gases do not follow Boyle's law, Charles' law and Avogadro's perfectly under all conditions. Now two questions arise. Number 1, why do gases deviate from the ideal behavior? Number 2, what are the conditions which gases deviate from ideality? We get the answer of the first question if we look into the postulates of kinetic theory once again. We find that two assumptions of the kinetic theory do not hold good. These are A. There is no force of attraction between the molecules of gas. B. Volume of the molecules of a gas is negligibly small in comparison to the space occupied by the gas. If assumption A is correct, the gas will never liquefy. However, we know that gases do liquefy when cooled and compressed. Also, liquids formed are very difficult to compress. This means that forces of repulsion are powerful enough and prevent squashing of molecules in tiny volume. If assumption B is correct, the pressure versus volume graph of experimental data, that is of real gas, and that theoretically calculated from Boyle's law, that is ideal gas, should coincide. Real gases show deviation from ideal gases law because molecules interact with each other. At high pressures, molecules of gases are very close to each other. Molecule interactions start operating at high pressure. Molecules do not strike the walls of container with full impact because these are dragged back by other molecules due to molecular attractive forces. This affects the pressure exerted by the molecules on the walls of the container. Thus, the pressure exerted by the gas is lower than the pressure exerted by the ideal gas. Here you can see the P ideal is equals to P real plus AN square upon V square. Here A is the constant. Repulsive forces also become significant. Repulsive interactions are short-range interactions and are significant when molecules are almost in contact. This is the situation at high pressure. The repulsive forces cause the molecules to behave as small but impenetrable spheres. The volume occupied by the molecules also becomes significant because instead of moving in volume V, these are now restricted to volume V NB, where NB is approximately the total volume occupied by the molecules themselves. Here B is a constant, having taken into account the corrections of pressure and volume. We can rewrite equation P plus An square upon V square, V minus Nb is equals to nRT. Equation is known as van der Waals equation. In this equation, N is number of moles of the gas. Constants A and B are called van der Waals constant and their value depends on the characteristic of gas. Value of A is measure of magnitude of intermolecular attractive forces within the gas and is independent of temperature and pressure. Also, at very low temperature, intermolecular forces become significant. As the molecules travel with low average speed, these can be captured by one another due to attractive forces. Real gases show ideal behavior when conditions of temperature and pressure are such that intermolecular forces are practically negligible. The real gases show ideal behavior when pressure approaches zero. The deviation from an ideal behavior can be measured in terms of compressibility factor Z, which is the ratio of product PV and nRT mathematically. Z is equals to PV upon nRT. For ideal gas, Z is equals to 1 at all temperatures and pressure because PV is equals to nRT. The graph of Z versus P will be straight line parallel to pressure axis. For gases which deviate from ideality, value of Z deviates from unity. At very low pressures, all gases shown Z is equals to approximately 1 and behave as ideal gas. At high pressure, all the gases have Z is greater than 1. These are more difficult to compress. At intermediate pressure, most gases have Z is less than 1. Thus, gases show ideal behavior when the volume occupied is large, so that the volume of the molecules can be neglected in comparison to it. In other words, the behavior of the gas becomes more ideal when pressure is very low. Up to what pressure a gas will follow the ideal gas law depends upon nature of the gas and its temperature. The temperature at which a real gas obeys ideal gas law over an appreciable range of pressure is called boil temperature or boil point. Boil point of a gas depends upon its nature. Above their boil point, real gases show positive deviation from ideality and Z values are greater than 1. The forces of attraction between the molecules are very feeble. Below boil temperature, real gases first show decrease in Z value with increasing pressure, which reaches a minimum value. On further increase in pressure, the value of Z increases continuously. Above explanation shows that the low pressure and higher temperature gases show ideal behavior. These conditions are different for different gases. More insight is obtained in the significance of Z if we note the following derivation. Z is equals to PV real upon nRT. If the gas shows ideal behavior, then V ideal is equals to nRT. On putting this value of nRT upon P in equation 5.33, we have Z is equals to V real upon V ideal. From equation 5.34, we can see that compressibility factor is the ratio of actual molar volume of a gas to the molar volume of it, if it were an ideal gas at the temperature and pressure. In the following sections, we will see that it is not possible to distinguish between gaseous state and liquid state, that liquids may be considered as continuation of gas phase into a region of small volumes and very high molecular attraction. We will also see how we can use isotherm of gases for predicting the conditions for liquefaction of gases. 5.10 Liquefaction of gases. First, complete data on a pressure volume temperature relations of a substance in both gases and liquid state was obtained by Thomas Andrews on carbon dioxide. He plotted isotherms of carbon dioxide at various temperature, that is in 5.13. I will show you that diagram later on. Later on, it was found that the real gases behave in the same manner as carbon dioxide. Andrews noticed that at high temperature, isotherms looks like that of one ideal gas and the gas cannot be liquefied even at very high pressure. As the temperature is lowered, shape of the curve changes and data show considerable deviation from ideal behavior. At 30.98 degrees Celsius, carbon dioxide remains gas up to 73 atmospheric pressure. At 73 atmospheric pressure, liquid carbon dioxide appears for the first time. The temperature 30.98 degrees Celsius is called critical temperature of carbon dioxide. This is the highest temperature at which liquid carbon dioxide is observed. Above this temperature, it is gas. Volume of 1 mole of the gas at critical temperature is called critical volume, that is Vc, and pressure at this temperature is called critical pressure, that is Pc. The critical temperature, pressure and volume are called critical constants. Further increase in pressure simply compresses the liquid carbon dioxide and the curve represents the compressibility of the liquid. Here you can see the figure 5.3, that is isotherms of carbon dioxide at various temperatures. The steep line represents the isotherm of liquid. Even a slight compression results in a steep rise in pressure, indicating very low compressibility of the liquid. Below 30.98 degrees Celsius, the behavior of the gas on compression is quite different. At 21.5 degrees Celsius, carbon dioxide remains as a gas only up to point B. At point B, liquid of a particular volume appears. Further compression does not change the pressure. Liquid and gaseous carbon dioxide coexist and further application of pressure results in the condensation of more gas until the point C is reached. At point C, all the gas has been condensed and further application of pressure merely compresses the liquid as shown by steep line. A slight compression from volume V2 to V3 results in a steep rise in pressure P2 to P3. Below 30.98 degrees Celsius, each curve shows the similar trend. Only length of the horizontal line increases at lower temperature. At critical point, horizontal portion of the isotherm merges into one point. Thus, we see that a point like A in the figure 5.13, this is A point like D represents liquid states and a point under the dome-shaped area represents existence of a liquid and gaseous carbon dioxide in equilibrium. All the gas upon compression at constant temperature, that is isothermal compression, show the same behavior as shown by carbon dioxide. Also, above discussion shows that gases should be cooled below their critical temperature for liquefaction. Critical temperature of a gas is highest temperature at which liquefaction of the gas first occurs. Liquefaction of so-called permanent gas, that is gases which show continuous positive deviation in Z value, requires cooling as well as considerable compression. Compression brings the molecule in close vicinity and cooling slows down the movement of molecules. Therefore, intermolecular interactions may hold the closely and slowly moving molecules together and the gas liquefies. It is possible to change a gas into liquid or a liquid into a gas by a process in which always a single phase is present. For example, in figure 5.13, we can move from point A to F vertically by increasing the temperature. Then we can reach the point G by compressing the gas at the constant temperature along this isotherm at 31.1 degrees Celsius. The pressure will increase. Now we can move vertically down towards D by lowering the temperature. As soon as we cross the point H on the critical isotherm, we get liquid. We end up with liquid, but in the series of changes, we do not pass through two-phase region. If process is carried out at the critical temperature, substance always remains in one phase. Thus, there is continuity between the gases and liquid state. The term fluid is used for either a liquid or a gas to recognize this continuity. Thus, a liquid can be viewed as a very dense gas. Liquid and gas can be distinguished only when the fluid is below its critical temperature and its pressure and volume lie under the dome, since in that situation liquid and gas are in equilibrium and a surface separating the two phases is visible. In the absence of this surface, there is no fundamental way of distinguishing between two states. At critical temperature, liquid passes into gaseous state imperceptibly and continuously. The surface separating two phases disappears. Section 5.11.1. A gas below the critical temperature can be liquefied by applying pressure and is called vapor of the substance. Carbon dioxide gas below its critical temperature is called carbon dioxide vapor. Critical constants for some common substances are given in table 5.4. Here you can see for hydrogen, helium, nitrogen, oxygen, carbon dioxide, H2 and NH3, all the critical values of temperature, pressure and volume. Now the problem 5.5 you can see. 5.11 liquid state. Intermolecular forces are stronger in liquid state than in gaseous state. Molecules in liquids are so close that there is very little empty space between them, and under normal conditions liquids are denser than gases. Molecules of liquids are held together by the attractive intermolecular forces. Liquids have definite volume because molecules do not separate from each other. However, molecules of liquid can move past one another freely. Therefore, liquids can flow, can be poured, and can assume the shape of the container in which these are stored. In the following sections, we will look into some of the physical properties of the liquid such as vapor pressure, surface tension, and viscosity. 5.11.1 Vapor pressure. If an evacuated container is partially filled with a liquid, a portion of liquids evaporates to fill the remaining volume of the container with vapor. Initially, the liquid evaporates and pressure exerted by vapors on the walls of the container increases. After some time, it becomes constant and equilibrium is established between liquid phase and vapor phase. Vapor pressure at this stage is known as equilibrium vapor pressure or saturated vapor pressure. Since process of vaporization is temperature dependent, the temperature must be mentioned while reporting the vapor pressure of a liquid. When a liquid is heated in an open vessel, the liquid vaporizes from the surface at the temperature at which vapor pressure of the liquid becomes equal to the external pressure. Vaporization can occur throughout the bulk of the liquid and vapors expand freely into the surroundings. The condition of free vaporization throughout the liquid is called boiling. The temperature at which vapor pressure is of liquid is equal to the external pressure is called boiling temperature at that pressure. Vapor pressure of some common liquids at various temperatures is given in figure 5.14, page 155. At 1 atmospheric pressure, a boiling temperature is called normal boiling point. If pressure is 1 bar, then the boiling point is called standard boiling point of the liquid. Standard boiling point of the liquid is slightly lower than the normal boiling point because 1 bar pressure is slightly less than 1 atmospheric pressure. The normal boiling point of water is 100 degrees Celsius, that is 373 Kelvin. Its standard boiling point is 99.6 degrees Celsius, that is 372.6 Kelvin. Here you can see figure 5.14, vapor pressure versus temperature curve of some common liquids. At high altitudes, atmospheric pressure is low. Therefore, liquids at high altitudes boils at lower temperatures in comparison to that the sea level. Since water boils at low temperature on hills, the pressure cooker is used for cooking food in hospitals. Surgical instruments are sterilized in autoclaves in which boiling point of water is increased by increasing the pressure above the atmospheric pressure by using a weight covering the vent. Boiling does not occur when liquid is heated in a closed vessel. On heating continuously, vapor pressure increases. At first, a clear boundary is visible between liquid and vapor phase because liquid is more dense than vapor. As the temperature increases, more and more molecules go to vapor phase and density of a vapors rises. At the same time, liquid becomes less dense. It expands because molecules move apart. When density of liquid and vapors becomes the same, the clear boundary between liquid and vapors disappears. This temperature is called critical temperature, about which we have already discussed in section 5.10. 5.11.2 Surface tension. It is well known fact that liquids assume the shape of the container. Why is it then small drops of mercury form spherical bead instead of spreading on the surface? Why do particles of soil at the bottom of a river remain separated but they stick together when taken out? Why does a liquid rise in a thin capillary as soon as the capillary touches the surface of the liquid? All these phenomena are caused due to the characteristic property of liquids called surface tension. A molecule in the bulk of a liquid experiences equal intermolecular forces from all sides. The molecule therefore does not experience any net force. But for the molecule on the surface of liquid, net attractive force is towards the interior of the liquid, due to the molecules below it since there are no molecules above it. Liquids tend to minimize their surface area of the molecules on the surface, experience a net downward force and have more energy than. Figure 5.15 Forces acting on a molecule on a liquid surface and on a molecule inside the liquid. The molecules in the bulk which do not experiences any net force. Therefore, liquids tend to have minimum number of molecules at their surface. If surface of the liquid is increased by pulling a molecule from the bulk, attractive forces will have to be overcome. This will require expenditure of energy. The energy required to increase the surface area of the liquid by 1 unit is defined as surface energy. Its dimensions are J per meter square. Surface tension is defined as the force acting per unit length perpendicular to the line drawn on the surface of liquid. It is denoted by Greek letter gamma. It has dimensions of kilogram per second square, and in SI unit it is expressed in Newton per meter. The lowest energy state of liquid will be when surface area is minimum. A spherical shape satisfies these conditions. That is why mercury drops are spherical in shape. This is the reason that sharp glass edges are heated for making them smooth. On heating, the glass melts and the surface of the liquid tends to take rounded shape at the edges, which makes the edges smooth. This is called fire polishing of the glass. Liquid tends to rise or fall in the capillary because of surface tension. Liquids wet the things because they spread across their surfaces as thin film. Moist soil grains are pulled together because surface area of thin film of water is reduced. It is surface tension which gives stretching properties to the surface of liquid. On flat surface, droplets are slightly flattened by the effect of gravity. But in the gravity-free environments, drops are perfectly spherical. The magnitude of surface tension of liquid depends on the attractive forces between the molecules. When the attractive forces are large, the surface tension is large. Increase in temperature increases the kinetic energy of the molecules and effectiveness of intermolecular attraction decreases. So surface tension decreases as the temperature is raised. 5.11.3 Viscosity. It is one of the characteristic properties of liquids. Viscosity is a measure of resistance to flow which arises due to the internal friction between layers of fluid as they slip past one another while liquid flows. Strong intermolecular forces between molecules hold them together and resist movement of layers past one another. When a liquid flows over a fixed surface, the layer of molecules in the immediate contact of surface is stationary. The velocity of upper layers increases as the distance of layers from the fixed layer increases. This type of flow in which there is a regular gradation of velocity in passing from one layer to the next layer is called a laminar flow. If we choose any layer in the flowing liquid, the layer above it accelerates its flow and the layer below this retard its flow. Here you can see 5.16 gradation of velocity in the laminar. If the velocity of the layer at a distance dz is changed by the value du, then the velocity gradient is given by the amount du upon dz. A force is required to maintain the flow of layers. This force is proportional to the area of contact of layers and velocity gradient, that is F is proportional to A, that is the area of the contact. F proportional to A du dz, where du upon dz is velocity gradient, the change in velocity with distance. F is proportional to A into du upon dz, where F is equals to eta A du upon dz. That is a proportionality constant and is called coefficient of viscosity. Viscosity coefficient is the force when velocity gradient is unity and the area of contact is unit area. Thus eta is measure of viscosity. SI unit of viscosity coefficient is 1 Newton second per square meter, that is NSM to the power minus 2, that is equal to Pascal second. In CDS system, the unit of coefficient of viscosity is poise, named after great scientist Jean-Louis Poiseuille. 1 poise is equals to 1 gram per centimeter per second. Greater the viscosity, the more slowly the liquid flows. Hydrogen bonding and van der Waals forces are strong enough to cause high viscosity. Glass is an extremely viscous liquid. It is so viscous that many of its properties resemble solids. Viscosity of liquid decreases as the temperature rises because at high temperature molecules have high kinetic energy and can overcome the intermolecular forces to slip past one another between the layers. Summary. Intermolecular forces operate between the particles of matter. These forces differ from pure electrostatic forces that exist between two oppositely charged ions. Also, these do not include force that hold atoms of a covalent molecule together through covalent bond. Competition between thermal energy and intermolecular interaction determines the state of matter. Bulk properties of matter such as behavior of gases, characteristics of solid and liquids, and change of state depend upon energy of constituent particles and the type of interaction between them. Chemical properties of a substance do not change with change of state, but the reactivity depends upon the physical state. Forces of interaction between gas molecules are negligible and are almost independent of their chemical nature. Interdependence of some observable properties, namely pressure, volume, temperature, and mass, leads to different gas laws obtained from experimental studies on gases. Boyle's law states that under isothermal condition, pressure of a fixed amount of a gas is inversely proportional to its volume. Charles' law is a relationship between volume and absolute temperature under isobaric condition. It states that the volume of a fixed amount of gas is directly proportional to its absolute temperature, that is V proportional to T. If a state of gas is represented by P1, V1 and T1 and it changes to state P2, V2 and T2, then relationship between these two states is given by combined gas law, according to which P1 V1 upon T1 is equals to P2 V2 upon T2. Any one of the variable of this gas can be found out if other 5 variables are known. Avogadro law states that equal volumes of all gases under same conditions of temperature and pressure contain equal number of mixture of non-reacting gases is equal to the sum of partial pressure exerted by them. Thus, P is equals to P1 plus P2 plus P3 plus and so on. Relationship between pressure and volume, temperature and number of moles of a gas describes its state and is called equation of state of the gas. Equation of state for ideal gas is equals to PV is equals to nRT, where R is a gas constant and its value depends upon units chosen for pressure, volume and temperature. At high pressure and low temperature, intermolecular forces start operating strongly between the molecules of gases because they come close to each other. Under suitable temperature and pressure conditions, gases can be liquefied. Liquids may be considered as continuation of gas phase into a region of a small volume and very strong molecular attractions. Some properties of liquids, example surface tension and viscosity, are due to strong intermolecular attractive forces. Chapter done. हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज हम करने जा रहे हैं क्लास 11th यूनिट 6 थर्मोडायनेमिक्स। ये आपकी रिक्वेस्ट के अकॉर्डिंग ही मैं ऑडियो बुक रिकॉर्ड कर रही हूँ बच्चों। दिस इज ओनली एन ऑडियो बुक, सो बच्चों वेन एवर यू आर लिसनिंग इट बी स्पेसिफिक विद दैट, इट्स नॉट द एक्सप्लेनेटरी वन। बच्चों इसको अपने दोस्तों के साथ में ज़्यादा से ज़्यादा शेयर करिए ताकि उनको भी इसका बेनिफिट मिल सके। और साथ ही साथ कमेंट सेक्शन में आप मुझे ये भी बताते जाइएगा कि और क्या इंप्रूवमेंट चाहिए और आफ्टर केमिस्ट्री आप किसकी ऑडियो बुक चाहते हैं। अगर आपको बायो में ही किसी और बुक की ऑडियो बुक चाहिए या केमिस्ट्री में, तो आप वो नेम्स मुझे सजेस्ट करिए, सो देन आई विल चूज दैट विच ऑडियो बुक आई हैव टू प्रिपेयर फर्स्ट। सो चलिए टाइम वेस्ट नहीं करते हैं, शुरू करते हैं। यूनिट 6 थर्मोडायनेमिक्स। इट इज द ओनली फिजिकल थ्योरी of universal content concerning which I am convinced that within the framework of the applicability of its basic concept, it will never be overthrown. Albert Einstein. Chemical energy stored by molecules can be released as heat during chemical reaction when a fuel like methane, cooking gas, or coal burns in air. The chemical energy may also be used to do mechanical work when a fuel burns in an engine or to provide electrical energy through a galvanic cell like dry cell. Thus, various forms of energy are interrelated and under certain conditions, these may be transformed from one form into another. The study of these energy transformation forms the subject matter of thermodynamics. The laws of thermodynamics deal with the energy changes of macroscopic system involving a large number of molecules rather than microscopic systems containing a few molecules. Thermodynamics is not concerned about how and at what rate these energy transformations are carried out, but is based on initial and final states of system undergoing the change. Laws of thermodynamics apply only when a system is in equilibrium or moves from one equilibrium state to another equilibrium state. Macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. In this unit, we would like to answer some of important questions through thermodynamics, like how do we determine the energy changes involved in a chemical reaction or process? Will it occur or not? What drives a chemical reaction or process? To what extent do the chemical reactions proceed? 6.1 Thermodynamic terms. We are interested in chemical reactions and the energy changes accompanying them. For this, we need to know certain thermodynamic terms. These are discussed below. 6.1.1 The system and the surroundings. A system in thermodynamics refers to that part of universe in which observations are made and remaining universe constitutes the surroundings. The surroundings include everything other than the system. System and the surroundings together constitute the universe. The universe is equals to the system plus the surroundings. However, the entire universe other than the system is not affected by the changes taking place in the system. Therefore, for all practical purposes, the surroundings are the portion of the remaining universe which can interact with the system. Usually, the region of space in the neighborhood of the system constitutes its surroundings. For example, if we are studying the reaction between two substances A and B kept in a beaker, the beaker containing the reaction mixture is the system and the room where the beaker is kept is the surroundings. Here you can see the figure 6.1 system and the surroundings. Note that the system may be defined as the physical boundaries like beaker or test tube, or the system may simply be defined by a set of Cartesian coordinate specifying a particular volume in space. It is necessary to think of the system as separated from the surroundings by some sort of wall which may be real or imaginary. The wall that separates the system from the surroundings is called boundary. This is designed to allow us to control and keep track of all movements of matter and energy in or out of the system. 6.1.2 Types of system. We further classify the systems according to the movements of matter and energy in or out of the system. Number 1. Open system. In an open system, there is exchange of energy and matter between system and surroundings. Figure 6.2a. The presence of reactants in an open beaker is an example of an open system. Here the boundary is an imaginary surface enclosing the beaker and reactants. Number 2. Closed system. In a closed system, there is no exchange of matter but exchange of energy is possible between system and the surroundings. Figure 6.2b. The presence of reactants in a closed vessel made of conducting material, example copper or steel, is an example of a closed system. Here you can see the board diagram of open system, closed system, and the C1 is isolated system. Number 3. Isolated system. In an isolated system, there is no exchange of energy or matter between the system and the surroundings. The presence of reactants in a thermos flask or any other closed insulated vessel is an example of an isolated system. 6.1.3 The state of the system. The system must be described in order to make any useful calculation by specifying quantitatively each of the properties such as its pressure, volume, and temperature, as well as the composition of the system. We need to describe the system by specifying it before and after the change. You would recall from your physics course that the state of a system in mechanics is completely specified at a given instant of time by the position and velocity of each mass point of the system. In thermodynamics, a different and much simpler concept of system of a state of a system is introduced. It does not need detailed knowledge of motion of each particle because we deal with average measurable properties of the system. We specify the state of the system by state functions or state variables. The state of a thermodynamic system is described by its measurable or macroscopic properties. We can describe the state of a gas by quoting its pressure, volume, temperature, amount, etc. Variables like P, V, T are called state variables or state functions because their values depends only on the state of the system and not on how it is reached. In order to completely define the state of a system, it is not necessary to define all the properties of the system, as only a certain number of properties can be varied independently. This number depends on the nature of the system. Once these minimum number of macroscopic properties are fixed, others automatically have definite values. The state of the surrounding can never be completely specified. Fortunately, it is not necessary to do so. 6.1.4 The internal energy as a state function. When we talk about our chemical system losing or gaining energy, we need to introduce a quantity which represents the total energy of the system. It may be chemical, electrical, mechanical, or any other type of energy you may think of. The sum of all these is the energy of the system. In thermodynamics, we call it the internal energy, U of the system, which may change when heat passes into or out of the system, work is done on or by the system, matter enters or leaves the system. These systems are classified accordingly as you have already studied in section 6.1.2. A. Work. Let us first examine a change in internal energy by doing work. We take a system containing some quantity of water in a thermos flask or in an insulated beaker. This would not allow exchange of heat between the system and surroundings through its boundary, and we call this type of system as adiabatic. The manner in which the state of such a system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between the system and the surroundings. Here, the wall separating the system and the surroundings is called the adiabatic wall, figure 6.3. Let us bring the change in the internal energy of the system by doing some work on it. Let us call the initial state of the system as a state A and its temperature as TA. Let the internal energy of the system in state A be called UA. We can change the state of the system in two different ways. One way, we do some mechanical work, say 1 kilojoule, by rotating a set of small pedals and thereby churning water. Let the new state be called B state and its temperature as TB. It is found that TB is greater than TA and the change in temperature delta T is equals to TB minus TA. Let the internal energy of the system in state B be UB and the change in internal energy delta U is equals to UB minus UA. Second way, we now do an equal amount of electrical work with the help of an immersion rod and note down the temperature change. We find the change in temperature is same as the earlier case, say TB minus TA. In fact, the experiments in the above manner were done by J.P. Joule between 1840 to 50, and he was able to show that a given amount of work done on the system, no matter how it was done, irrespective of path, produced the same change of state as measured by the change in the temperature of the system. So it seems appropriate to define a quantity, the internal energy U, whose value is characteristic of the state of a system, whereby the adiabatic work WAD required to bring about a change of state is equal to the difference between the value of U in one state and that in another state, delta U. That is, delta U is equals to U2 minus U1 is equals to WAD. Therefore, internal energy U of the system is a state function. By conventions of IUPAC in chemical thermodynamics, the positive sign expresses that WAD is positive when work is done on the system and the internal energy of system increases. Similarly, if the work is done by the system, WAD will be negative because internal energy of the system decreases. Can you name some other familiar state functions? Some of other familiar state functions are V, P, and T. For example, if we bring a change in temperature of the system from 25 to 35 degrees Celsius, the change in temperature is equals to plus 10 degrees Celsius. Whether we go straight up to 35 or we cool the system for a few degrees, then take the system to the final temperature. Thus, T is a state function and the change in temperature is independent the route taken. Volume of water in a pond, for example, is a state function because change in volume of its water is independent of the route by which water is filled in the pond, either by rain or by tubewell or by both. B. Heat. We can also change the internal energy of a system by transfer of heat from the surroundings to the system or vice versa, without expenditure of work. This exchange of energy, which is a result of temperature difference, is called heat. Q. Let us consider bringing about the same change in temperature, that is the same initial and final state as before in section 6.1.4a by transfer of heat through thermally conducting walls instead of adiabatic walls. Figure 6.4, a system which allows heat transfer through its boundary. We take water at temperature TA in a container having thermally conducting walls, say made of copper, and enclose it in a huge heat reservoir at temperature TB. The heat absorbed by the system, that is water, Q, can be measured in the term of temperature difference, TB minus TA. In this case, change in internal energy delta U is equals to Q when no work is done at constant volume. By conventions of IUPAC in chemical thermodynamics, the Q is a positive when heat is transferred from the surroundings to the system and the internal energy of the system increases, and Q is negative when heat is transferred from system to the surroundings, resulting in decrease of the internal energy of the system. Earlier, negative sign was assigned when the work is done on the system and positive sign when the work is done by the system. This is still followed in physics books, although IUPAC has recommended the use of new sign convention. See the general case. Let us consider the general case in which a change of state is brought about both by doing work and by transfer of heat. We write change in internal energy for this case as delta U is equals to Q plus W. For a given change in state, Q and W can vary depending on how the change is carried out. However, Q plus W is equals to delta U will depend only on initial and final state. It will be independent of the way the change is carried out. If there is no transfer of energy as heat or as work isolated system, that is, if W is equals to 0 and Q is equals to 0, then delta U is equals to 0. The equation 6.1, that is delta U is equals to Q plus W, is mathematical statement of the first law of thermodynamics, which states that the energy of an isolated system is constant. It is commonly stated as the law of conservation of energy, that is, energy can neither be created nor be destroyed. Note, there is considerable difference between the character of the thermodynamic property energy and that of mechanical property such as volume. We can specify an unambiguous, that is absolute, value for volume of a system in a particular state, but not the absolute value of the internal energy. However, we can measure only the changes in the internal energy, delta U, of the system. Application 6.2. Many chemical reactions involve the generation of gases capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them to the changes in the internal energy. Let us see how. 6.2.1 Work. First of all, let us concentrate on the nature of work a system can do. We will consider only mechanical work, that is pressure volume work. For understanding pressure volume work, let us consider a cylinder which contains 1 mole of an ideal gas fitted with a frictionless piston. Total volume of the gas is Vi and pressure of the gas inside is P. If external pressure is Px, where is greater than P, piston is moved inward till the pressure inside becomes equal to Pex. Let this change. See the figure 6.5a. Work done on an ideal gas in a constant external pressure Pex, that is in single step, is equal to the shaded area. Let this change be achieved in a single step and the final volume be Vf. During this compression, suppose piston moves a distance L and its cross-sectional area of the piston is A. The volume change is equals to L into A is equals to delta V is equals to Vf minus Vi. We also know pressure is equals to force upon area. Therefore, force on the piston is equals to P dot A. If W is the work done on the system by movement of the piston, then W is equals to force into distance is equals to Pex dot A dot L. Pex dot minus delta V is equals to minus Pex delta V is equals to minus Pex in bracket Vf minus Vi. The negative sign of this expression is required to obtain conventional sign for W, which will be positive. It indicates that in case of compression work is done on the system, here Vf minus Vi will be negative and negative multiplied by negative will be positive. Hence, the sign obtained for the work will be positive. If the pressure is not constant at every stage of compression but changes in number of finite steps, work done on the gas will be summed over all the steps and will be equal to negative summation Pwv Here you can see the 6.5b plot. If the pressure is not constant but changes during the process such that it is always infinitesimally greater than the pressure of the gas, then at each stage of compression the volume decreases by an infinitesimal amount dV. In such a case, we can calculate the work done on the gas by the relation. Here you can see this relation. Here Pex at each stage is equal to Pin, that is initial, plus dP in case of compression, figure 6.5c. In an expansion process under similar conditions, the external pressure is always less than the pressure of the system. That is Pex is equals to P initial minus dP. In general case, we can write Pex is equals to P initial plus minus dP. Such processes are called reversible processes. A process or change is said to be reversible if a change is brought out in such a way that the process could at any moment be reversed by an infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that system and the surroundings are always in near equilibrium with each other. Processes other than reversible processes are known as irreversible processes. Here you can see the figure 6.5c. In chemistry, we face problems that can be solved if we relate the work term the internal pressure of the system. We can relate work to internal pressure of the system under reversible condition by writing equation. Here you can see the equation. Now the pressure of the gas P, which we can write as P now, can be expressed in terms of its volume through gas equation. For n mole of an ideal gas, that is PV is equals to nRT. P is equals to nRT upon V. Therefore, at constant temperature, here you can see the reaction. The final reaction is minus 2.303 is nRT log Vf upon Vi. Free expansion. Expansion of a gas in a vacuum, Pax is equals to 0, is called free expansion. No work is done during free expansion of an ideal gas, whether the process is reversible or irreversible. Now we can write equation 6.1 in number of ways depending on the type of processes. Let us substitute W is equals to minus Pex delta V in equation 6.1 and we get delta U is equals to Q minus Pex delta V. If a process is carried out at constant volume, it means the delta V is equals to 0, then delta U is equals to QV. The subscript V in QV denotes that heat is supplied at constant volume. Isothermal and free expansion of an ideal gas. For isothermal, T constant expansion of an ideal gas into vacuum, W is equals to 0. Since Pex is equals to 0, also Joule determined experimentally that Q is equals to 0, therefore delta U is equals to 0. Here you can see the equation 6.1 and the complete calculation. First, for isothermal irreversible change, Q is equals to minus W is equals to Pex Vf minus Vi, and in the second, for isothermal reversible change, the final equation is 2.303 nRT log Vf upon Vi, and third, for the adiabatic change, Q is equals to 0, delta U is equals to W adiabatic. 6.2.2, that is enthalpy H, a useful new state function. We know that heat absorbed at constant volume is equal to change in the internal energy, that is delta U is equals to QV. But most of chemical reactions are carried out not at constant volume, but in flask or test tubes under constant atmospheric pressure. We need to define another state function which may be suitable under these conditions. We may write equation 6.1 as delta U is equals to QP minus P delta V at constant pressure, where QP is heat absorbed by the system and minus P delta V represents expansion work done by the system. Let us represent the initial state by subscript 1 and final state by 2. We can rewrite the above equation as U2 minus U1 is equals to QP minus P, V2 minus V1. On rearranging, we get QP is equals to U2 plus PV2 minus U1 plus PV1. Now we can define another thermodynamic function, the enthalpy H. H is equals to U plus PV. So equation 6.6 becomes QP is equals to H2 minus H1 is equals to delta H. Although Q is a path dependent function, H is a state function because it depends on U, P and V, all of which are a state function. Therefore, delta H is independent of path, hence QP is also independent of path. For finite changes at constant pressure, we can write equation 6.7 as delta H is equals to delta U plus delta PV. Since P is constant, we can write delta H is equals to delta U plus P delta V. It is important to note that when heat is absorbed by the system at constant pressure, we are accurately measuring changes in the enthalpy. Remember, delta H is equals to QP, heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions which evolve heat during the reaction, and delta H is positive for endothermic reactions which absorb heat from the surroundings. At constant volume, delta V is equals to 0, delta U is equals to QV, therefore equation 6.8 becomes delta H is equals to delta U is equals to QV. The difference between delta H and delta U is not usually significant for systems consisting of only solids and or liquids. Solids and liquids do not suffer any significant volume changes upon heating. The difference, however, becomes significant when gases are involved. Let us consider a reaction involving gases. If Va is the total volume of the gaseous reactants, Vb is the total volume of the gaseous product. Na is the number of moles of gaseous reactants and Nb is the number of moles of gaseous products. All at constant pressure and temperature. Then using the ideal gas law, we write PVA is equals to NART, PVB is equals to NBRT, PVB minus PVA is equals to NBRT minus NART is equals to NB minus NART. Then P common लेने पर VB minus VA is equals to NB minus NA and bracket close then RT. So it means the P delta V is equals to delta N RT. Here delta N refers to the number of moles of gaseous products minus the number of moles of gaseous reactants. Substituting the value of P delta V from equation 6.9 in equation 6.8, we get delta H is equals to delta U plus delta N GRT. The equation 6.10 is useful for calculating delta H and delta U and vice versa. B. Extensive and intensive properties. In thermodynamics, a distinction is made between extensive property and intensive properties. An extensive property is a property whose value depends on the quantity or size of matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity, etc. are extensive properties. Those properties which do not depend on the quantity or size of matter present are known as intensive property. For example, temperature, density, pressure, etc. are intensive property. A molar property Xm is the value of an extensive property X of the system for 1 mole of the substance. If N is the amount of matter, then Xm is equals to X upon N is independent of the amount of matter. Other examples are molar volume, that is Vm, and molar heat capacity, Cm. Let us understand the distinction between extensive and intensive properties by considering a gas enclosed in a container of volume V and at temperature T. Let us make a partition such that volume is halved. Each part now has 1/2 of the original volume, V upon 2, but the temperature will still remain the same, that is the T. It is clear that volume is an extensive property and the temperature is an intensive property. C. Heat capacity. Here you can see the figure 6.6a and 6.6b. C. Heat capacity. In this subsection, let us see how to measure heat transfer to a system. This heat appears as a rise in temperature of the system in case of heat absorbed by the system. The increase of temperature is proportional to the heat transfer. Q is equals to coefficient into delta T. The magnitude of the coefficient depends on the size, composition and nature of the system. We can also write it as Q is equals to C delta T. The coefficient C is called the heat capacity. Thus, we can measure the heat supplied by monitoring the temperature rise provided we know the heat capacity. Where C is large, a given amount of heat results in only a small temperature rise. Water has large heat capacity, that is, a lot of energy is needed to raise its temperature. C is directly proportional to amount of substances. The molar heat capacity of a substance Cm is equals to C upon N is the heat capacity for 1 mole of the substance and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius or 1 Kelvin. The specific heat, also called specific heat capacity, is the quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. For finding out the heat Q required to raise the temperatures of a sample, we multiply the specific heat of the substance C by the mass M and temperature change delta T as Q is equals to C into M into delta T is equals to C delta T. D. The relationship between Cp and Cv. for an ideal gas. At constant volume, the heat capacity C is denoted by Cv, and at constant pressure, this is denoted by Cp. Let us find the relationship between the two. We can write the equation for heat Q. At constant volume, as Qv is equals to Cv delta T is equals to delta U. At constant pressure, Qp is equals to Cp delta T is equals to delta H. The difference between Cp and Cv can be derived for an ideal gas as here the final delta H is equals to delta U plus R delta T. So delta H is equals to delta U plus R delta T. On putting the values of delta H and delta U, we have final reaction, that is Cp minus Cv is equals to R. 6.3 Measurement of delta U and delta H calorimetry. We can measure energy changes associated with chemical or physical processes by an experimental technique called calorimetry. In calorimetry, the process is carried out in a vessel called calorimeter, which is immersed in a known volume of a liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of the calorimeter, it is possible to determine the heat evolved in the process of measuring temperature changes. Measurements are made under two different conditions. Number 1, at constant volume, Qv, at constant pressure, Qp. A. Delta U measurements. For a chemical reaction, heat absorbed at constant volume is measured in a bomb calorimeter. Here a steel vessel is immersed in a water bath. The whole device is called calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost due to the surroundings. A combustible substance is burned in pure dioxygen supplied in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change, that is, the energy changes associated with reactions are measured at constant volume. Under these conditions, no work is done as the reaction is carried out at constant volume in the bomb calorimeter. Even for reactions involving gases, there is no work done as delta V is equals to 0. Temperature change of the calorimeter produced by the completed reaction is then converted to QV by using the known heat capacity of the calorimeter with the help of equation 6.1.11. Delta H, measurement of heat change at constant pressure, generally under atmospheric pressure, can be done in a calorimeter shown in figure 6.8. Here is the figure 6.8. We know that delta H is equals to Qp at constant P, and therefore heat absorbed or evolved Qp at constant pressure is also called the heat of reaction or enthalpy of reaction delta RH. In an exothermic reaction, heat is evolved and system loses heat to the surroundings. Therefore, Qp will be negative and delta RH will also be negative. Similarly, in an endothermic reaction, heat is absorbed, Qp is positive and delta RH will be positive. 6.4 Enthalpy change, delta RH of a reaction enthalpy. In a chemical reaction, reactants are converted into products and is represented by reactant gives out products. The enthalpy change accompanying a reaction is called the reaction enthalpy. The enthalpy change of a chemical reaction is given by the symbol delta RH. Delta RH is equals to sum of enthalpies of product minus sum of enthalpies of reactants. Here you can see, here the symbol sigma is used for summation, and AI and BI are the stoichiometric coefficients of the products and reactants respectively in the balanced chemical equation. For example, for the reaction CH4 plus 2O2 gives out CO2 plus 2H2O. Here you can see the complete delta HM value, and delta HM is the molar enthalpy here, and the complete delta RH value you can see here. Enthalpy change is a very useful quantity. Knowledge of this quantity is required when one need to plan the heating or cooling required to maintain an industrial chemical reaction at constant temperature. It is also required to calculate temperature dependence of equilibrium constant. A. Standard enthalpy of reactions. Enthalpy of reaction depends on the conditions under which a reaction is carried out. It is therefore necessary that we must specify some standard conditions. The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in their standard states. The standard state of a substance at a specified temperature is its pure form at 1 bar. For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. The standard state of solid iron at 500 K is pure iron at 1 bar. Usually data are taken at 298 Kelvin. Standard conditions are denoted by adding the superscript negative to the symbol delta H. Example, delta H negative. The B, enthalpy changes during phase transformation. Phase transformations also involve energy changes. Ice, for example, requires heat for melting. Normally, this melting takes place at constant pressure, that is atmospheric pressure, and during phase change. Temperature remains constant at 273 Kelvin. H2O gives out H2O liquid. Initially, it was solid, so delta H of fusion is equals to 6 kilojoule per mole. Here, delta H fusion is enthalpy of fusion in standard state. If water freezes, then process is reversed and equal amount of heat is given off to the surrounding. The enthalpy change that accompanies melting of 1 mole of solid substance in a standard state is called standard enthalpy of fusion or molar enthalpy of fusion. Melting of a solid in is endothermic, so all enthalpies of fusion are positive. Water requires heat for evaporation at constant temperature of its boiling point Tb, and at constant pressure H2O gives out H2O gaseous, so delta vaporization H is equals to plus 40.79 kilojoule per mole is the standard enthalpy of vaporization. Here you can see the table, that is the standard enthalpy changes of fusion and vaporization. Here TF and TB are melting and boiling points respectively. Amount of heat required to vaporize 1 mole of liquid at constant temperature and standard pressure. 1 bar is called its standard enthalpy of vaporization or molar enthalpy of vaporization. Sublimation is direct conversion of a solid into its vapor. Solid CO2 or dry ice sublimes at 195 Kelvin with delta sublime H is equals to 25.2 kilojoule per mole. Naphthalene sublimes slowly, and for this delta H sublimation is equals to 73.0 kilojoule per mole. Standard enthalpy of sublimation, delta H sublimation, is the change in enthalpy when 1 mole of solid substance sublimes at constant temperature and under standard pressure. The magnitude of the enthalpy change depends on the strength of the intermolecular interaction in the substance undergoing the phase transformations. For example, the strong hydrogen bonds between water molecules hold them tightly in liquid phase. For an organic liquid such as acetone, the intermolecular dipole-dipole interactions are significantly weaker. Thus, it requires less heat to vaporize 1 mole of acetone than it does to vaporize 1 mole of water. Table 6.1 give values of standard enthalpy change of fusion and vaporization for some substances. This is the table 6.2, that is the standard molar enthalpies of formation at 298 Kelvin of a few selected substances. See standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of a compound from its element in their most stable states of aggregation, also known as reference states, is called standard molar enthalpy of formation. Its symbol is delta FH, where the subscript F indicates that 1 mole of the compound in question has been formed in its standard state from its elements in their most stable states of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of dihydrogen is H2 gas, and those of dioxygen, carbon and sulfur are O2 gas, C graphite and S rhombic respectively. Some reactions with the standard molar enthalpies of formation are as follows. H2O plus half O2 gives out H2O. Delta FH is equals to minus 285.8 kilojoule per mole. C plus 2H2 gives out CH4, and delta FH is equals to minus 74.81 kilojoule per mole. 2C plus 3H2 gives plus half O2 gives out C2H5OH. Delta FH is minus 277.7 kilojoule per mole. It is important to understand that a standard molar enthalpy of formation delta FH is just a special case of delta RH, where 1 mole of a compound is formed from its constituent elements. As in the above 3 equations, where 1 mole of each water, methane and ethanol is formed. In contrast, the enthalpy change for an exothermic reaction, CaO plus CO2 gives out CaCO3. Here delta RH is equals to minus 178.3 kilojoule per mole. is not an enthalpy of formation of calcium carbonate, since calcium carbonate has been formed from other compounds and not from its constituent elements. Also, for the reaction given below, enthalpy change is not standard enthalpy of formation. Delta FH for HBr, H2 plus Br2 gives out 2HBr. Delta RH is equals to minus 178.3 kilojoule per mole. Here 2 moles instead of 1 mole of the product is formed from the elements, that is delta RH is equals to 2 delta FH. Therefore, by dividing all coefficients in the balanced equation by 2, expression for enthalpy of formation of HBr is written as half H2 plus half Br2 is equals to HBr. Delta FH is equals to minus 36.4 kilojoule per mole. Standard enthalpies of formation of some common substances are given in table 6.2. This is table 6.2. Here you can see the standard molar enthalpies of formation delta FH at 298 Kelvin of a few selected substances. There are so many, I can't read all of them. So better you just see this table here only. By convention, standard enthalpy for formation delta FH of an element in reference state, that is, its most stable state of aggregation, is taken as 0. Suppose you are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime and carbon dioxide with all the substances in their standard state. CaCO3 gives out CaO plus CO2, and here the delta RH is unknown. Here we can make use of a standard enthalpy of formation and calculate the enthalpy change for the reaction. The following general equation can be used for enthalpy change calculation, and here is that equation. You can see this reaction for the products as well as for reactants, where A and B represent the coefficient of the products and reactants in the balanced equation. Let us apply the above equation for decomposition of calcium carbonate. Here coefficient A and B are 1 each. Therefore, delta RH is equals to delta FH is equals to CaO plus delta FH CO2 minus delta FH is equals to CaCO3. So the final value we will get here 178.3 kilojoule per mole. Thus, the decomposition of CaCO3 is an endothermic process and you have to heat it for getting the desired products. D. Thermochemical equations. A balanced chemical equation together with the value of its delta RH is called a thermochemical equation. We specify the physical state along with allotropic state of the substance in an equation. For example, C2H5OH plus 3O2 gives out 2CO2 plus 3H2O. Delta RH is equals to minus 1367 kilojoule per mole. The above equation describes the combustion of liquid ethanol at constant temperature and pressure. The negative sign of enthalpy change indicates that this is an exothermic reaction. It would be necessary to remember the following conventions regarding thermochemical equations. Number 1. The coefficients in a balanced thermochemical equation refer to the number of moles, never molecules of reactants and products involved in the reaction. Number 2. The numerical value of delta RH refers to the number of moles of substances specified by an equation. The standard enthalpy change delta RH will have units as kilojoule per mole. To illustrate the concept, let us consider the calculation of heat of reaction for the following reaction. Fe2O3 plus 3H2 gives out 2Fe plus 3H2O. And from the table 6.2 of a standard enthalpy of formation, we will find here you can see the complete calculation and the final value of delta FH1 we will get here minus 33.3 kilojoule per mole. Note that the coefficient used in these calculations are pure numbers which are equal to the respective stoichiometric coefficients. The unit for delta RH is kilojoule per mole, which means per mole of reaction. Once we balance the chemical equation in a particular way as above, this defines the mole of reaction. If we had balanced the equation differently, for example, half Fe2O3 plus 3 by 2 H2 gives out Fe plus 3 by 2 H2O. Then this amount of reaction would be 1 mole of reaction and delta RH would be minus 16.6 kilojoule per mole. That is half of delta RH1. It shows that enthalpy is an extensive quantity. Number 3, when a chemical equation is reversed. The value of delta RH is reversed in sign. For example, N2 plus 3H2 gives out 2NH3, and here delta RH is equals to minus 91.8 kilojoule per mole, and 2NH3 gives out N2 plus 3H2, and here the delta RH is equals to plus 91.8 kilojoule per mole. E. Hess's law of constant heat summation. We know that enthalpy is a state function. Therefore, the change in enthalpy is independent of the path between initial state, that is reactants, and final state products. In other words, enthalpy change for a reaction is the same whether it occurs in one step or in a series of steps. This may be stated as follows in the form of Hess's law. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. Let us understand the importance of this law with the help of an example. Consider the enthalpy change for the reaction C graphite plus 1 by 2 O2 gives out CO delta RH. Although CO is a major product, some CO2 gas is always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. However, if we can find some other reactions involving related species, it is possible to calculate the enthalpy change for the above reaction. Let us consider the following reactions. C graphite plus O2 gives out CO2. Delta RH is equals to minus 393.5 kilojoule per mole, and here CO plus half O2 gives out CO2, and here it is delta RH is minus 283.0 kilojoule per mole. We can combine the above two reactions in such a way so as to obtain the desired reaction. To get 1 mole of CO on the right, we reverse equation second. In this, heat is absorbed instead of being released, so we change sign of delta RH value. CO2 gives out CO plus half O2, and here the value of delta RH is equals to plus 283.0 kilojoule per mole. Adding equation 1 and 3rd, we get the desired equation. C plus half O2 gives out CO, and the value of delta RH is equals to minus 110.5 kilojoule per mole. In general, if enthalpy of an overall reaction A gives out B along one route is delta RH, and delta RH1, delta RH2, and delta RH3 representing enthalpies of reactions leading to the same product. B along another route, then we have delta RH is equals to delta RH1, delta RH2, and so on. It can be represented as, here you can see this, 6.5 enthalpies for different types of reaction. It is convenient to give name to enthalpy specifying the types of reactions. A. Standard enthalpy of combustion, symbol delta CH. Combustion reactions are exothermic in nature. These are important in industry, rocketry, and other walks of life. A standard enthalpy of combustion is defined as the enthalpy change per mole of a substance when it undergoes combustion, and all the reactants and products being in their standard states at the specified temperature. Cooking gas in cylinders contain mostly butane, C4H10. During complete combustion of 1 mole of butane, 2658 kJ of heat is released. We can write the thermochemical reaction for this as C4H10 plus 13 by 2 O2 gives out 4CO2 plus 5H2O. Here the delta CH is equals to minus 2658.0 kJ per mole. Similarly, combustion of glucose gives out 2802.0 kJ. It means the 2802.0 kJ per mole of heat, for which the overall equation is C6H12O6 plus 6O2 gives out 6CO2 plus 6H2O, and the delta CH is equals to minus 2802.0 kJ per mole. Our body also generates energy from food by the same overall process as combustion, although the final products are produced after a series of complex or biochemical reactions involving enzymes. The problem 6.9 you can see here. B. Enthalpy of atomization, symbol delta AH. Consider the following example of atomization of dihydrogen. H2 gives out 2H, and here the delta AH is equals to 435.0 kJ per mole. You can see that H atoms are formed by breaking HH bond in dihydrogen. The enthalpy change in this process is known as enthalpy of atomization, delta AH. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. In case of diatomic molecules like dihydrogen, The enthalpy of atomization is also the bond dissociation enthalpy. The other examples of enthalpy of atomization can be CH4 gives out C plus 4H, and here the delta AH value is 1665 kilojoule per mole. Note that the products are only atoms of carbon and hydrogen in gaseous phase. Now see the following reaction. Sodium gives out sodium, and here the solid is converting into the gaseous form. So it means the delta AH is equals to 108.4 kilojoule per mole. In this case, the enthalpy of atomization is same as the enthalpy of sublimation. C. Bond enthalpy symbol is delta bond H. Chemical reactions involve the breaking and making of chemical bonds. Energy required to break a bond and energy is released when a bond is formed. It is possible to relate heat of reaction to changes in energy associated with breaking and making of chemical bonds. With reference to the enthalpy changes associated with chemical bonds, two different terms are used in thermodynamics. Number one, bond dissociation enthalpy. Number two, mean bond enthalpy. Let us discuss these terms with reference to diatomic and polyatomic molecules. Diatomic molecules, consider the following processes in which the bonds in 1 mole of dihydrogen gas are broken. H2 gives out 2H, and here the delta HH bond H enthalpy is equals to 435.0 kilojoule per mole. The enthalpy change involved in this process is the bond dissociation enthalpy of HH bond, and the bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. Note that it is the same as the enthalpy of atomization of dihydrogen. This is true for all diatomic molecules. For example, Cl2 gives out 2Cl, and here the delta H value is 242 kilojoule per mole, and for O2 gives out 2O, and here the delta O double bond OH is equals to 428 kilojoule per mole. In the case of polyatomic molecules, bond dissociation enthalpy is different from different bonds within the same molecule. Polyatomic molecules. Let us now consider a polyatomic molecule like methane, CH4. The overall thermochemical equation for its atomization reaction is given below. CH4 gives out C plus 4H. Here the delta AH is equals to 1665 kilojoule per mole. In methane, all the 4 carbon-hydrogen bonds are identical in bond length and energy. However, the energies required to break the individual CH bonds in each successive step differ. See all these steps. In the first step, when the CH4 is breaking down into the CH3 plus hydrogen, so delta H value is equals to 427 kilojoule per mole. In the next step, when CH3 is converting into the CH2 plus hydrogen, the delta H value is 439 kilojoule per mole. When CH2 is breaking down into the CH plus H, the delta H value is equals to plus 452 kilojoule per mole. And when the CH is breaking down into the carbon plus hydrogen, then its delta H value is 347 kilojoule per mole. Therefore, CH4 gives out C plus 4H, and the delta H is 1665 kilojoule per mole. In such cases, we use mean bond enthalpy of CH bond. And for example, in CH4, the delta CHH is calculated as the final value we will get here, the 416 kilojoule per mole. We find that mean CH bond enthalpy in methane is 416 kilojoule per mole. It has been found that mean CH bond enthalpies differ slightly from compound to compound, as in CH3, CH2, Cl, CH3, NO2, etc. But it does not differ in a great deal. Using Hess law, bond enthalpies can be calculated. Bond enthalpy value of some single and multiple bonds are given in table 6.3. The reaction enthalpies are very important quantities, as these arise from the changes that accompany the breaking of old bonds and formation of the new bonds. We can predict enthalpy of a reaction in gas phase if we know different bond enthalpies. The standard enthalpy of reaction delta RH is related to bond enthalpies of the reactants and products in gas phase reactions. So here you can see the delta RH is equals to summation of bond enthalpies of reactants minus the summation of bond enthalpies of the product. This relationship is particularly more useful when the required value of delta FH are not available. The net enthalpy change of a reaction is the amount of energy required to break all the bonds in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. Remember that this relationship is approximate and is valid when all substances, that is reactants and products in the reactions, are in gaseous state. Now see the table 6.3a, some mean single bond enthalpies in kilojoule per mole at 298 Kelvin. And in table 6.3, the same mean multiple bond enthalpies in kilojoule per mole at 298 Kelvin. D. Lattice enthalpy. The lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. NaCl gives out Na positive plus Cl negative, and here the delta lattice H is equals to plus 788 kilojoule per mole. Since it is impossible to determine lattice enthalpies directly by experiment, we use an indirect method where we construct an enthalpy diagram called a Bond-Haber cycle. Let us now calculate the lattice enthalpy of NaCl by following the steps given below. Na gives out solid to gaseous Na, sublimation of sodium metal. Here the delta sublimation H is equals to 108.4 kilojoule per mole. See this enthalpy diagram for lattice enthalpy of NaCl. Number 2. Na gaseous gives out Na ion plus 1 electron, the ionization of sodium atoms, ionization enthalpy, and the value is 496 kilojoule per mole. Number 3, half Cl2 gives out Cl, the dissociation of chlorine, the reaction enthalpy is half the bond dissociation enthalpy, and that is equivalent to 121 kilojoule per mole. Number 4, Cl plus 1 electron gives out Cl negative, and electron gained by chlorine atom, the electron gain enthalpy is equals to minus 348.6 kilojoule per mole. You have learnt about ionization enthalpy and electron gain enthalpy in Unit 3. In fact, these terms have been taken from thermodynamics. Earlier terms, ionization energy and electron affinity, were in practice in place of the above terms. And now I am reading the ionization energy and electron affinity. The ionization energy and electron affinity are defined at absolute zero. At any other temperature, heat capacities for the reactants and the products have to be taken into account. Enthalpies of reactions for M gaseous form converted into the M positive plus 1 electron for ionization, and M plus 1 electron gives out M negative for electron gain at temperature T is equals to, and here you can see the complete reaction. Therefore, delta RH is equals to E naught plus 5 by 2 RT, and delta RH electron gain enthalpy is equals to minus A minus 5 by 2 RT. Number 5, Na positive plus Cl negative gives out NaCl. The sequence of a step is shown in the figure 6.9, the diagram here, and is known as Bond-Haber cycle. See this cycle again. Importance of the cycle is that the sum of the enthalpy change around a cycle is zero. Applying Hess's law, we get the delta lattice H value is equals to 788 kilojoule. For NaCl, internal energy is smaller by 2 RT because delta Ng is equals to 2 and is equal to plus 783 kilojoule per mole. Now we use the value of lattice enthalpy to calculate enthalpy of solution. From the expression, the delta solution H is equals to delta lattice H plus delta hydration H. For 1 mole of NaCl, the lattice enthalpy is equals to plus 788 kilojoule per mole, and delta hydration H is equals to minus 784 kilojoule per mole from the literature. And the final value, delta sol H, we will get here the plus 4 kilojoule per mole. The dissolution of NaCl is accompanied by very little heat change. E. Enthalpy of solution. Enthalpy of solution of a substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. The enthalpy of solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent when the interaction between the ions or solute molecules are negligible. When an ionic compound dissolves in a solvent, the ions leave their ordered positions on the crystal lattice. These are now more free in solution, but solvation of these ions, hydration in case solvent is water, also occurs at the same time. This is shown diagrammatically for an ionic compound AB. See this. The enthalpy of solution of AB delta solution H in water is therefore determined by the selective values of the lattice enthalpy delta lattice H and enthalpy of hydration of ion delta hydration H as delta solution H is equals to delta lattice H plus delta hydration H. For most of ionic compounds, delta solution H is positive and the dissociation process is endothermic. Therefore, the solubility of the most salt in water increases with rise of temperature. If the lattice energy is very high, the dissolution of the compound may not take place at all. Why do many fluorides tend to be less soluble than the corresponding chlorides? Estimates of the magnitudes of enthalpy change may be made by using tables of bond energies, enthalpies, and lattice energy enthalpies. F. Enthalpy of dilution. It is known that the enthalpy of solution is the enthalpy change associated with the addition of a specified amount of solute to specified amount of solvent at a constant temperature and pressure. This argument can be applied to any solvent with slight modification. Enthalpy change for dissolving 1 mole of gaseous hydrogen fluoride in 10 mole of water can be represented by the following equation. For convenience, we will use the symbol aqueous for water. HCl plus 10 aqueous equals to HCl multiplied by 10. Delta H value is minus 69.01 kilojoule per mole. Let us consider the following set of enthalpy changes here. The HCl plus 25 aqueous, that is the value of delta H is here minus 72.03 kilojoule per mole, and HCl plus 40 aqueous, so HCl into 40 aqueous, delta H value is minus 72.79 kilojoule per mole. HCl plus infinite aqueous, the HCl into infinite aqueous, and the delta H value is minus 74.85 kilojoule per mole. The values of delta H show general dependence of the enthalpy of solution on amount of solvent. As more and more solvent is used, the enthalpy of solution approaches a limiting value. That is the value in infinite dilute solution. For hydrochloric acid, the value of delta H is given above in equation S3, and here is the equation S3. If we subtract the first equation from the second equation, that is S2, in the above set of equation, we will obtain the final delta H value is here minus 0.76 kilojoule per mole. This value of delta H is enthalpy of dilution. It is of the heat withdrawn from the surroundings when additional solvent is added to the solution. The enthalpy of dilution of a solution is dependent on the original concentration of the solution and the amount of solvent added. 6.6 is spontaneity. The first law of thermodynamics tells us about the relationship between the heat absorbed and the work performed on or by a system. It puts no restrictions on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. For example, a gas expanding to fill the available volume, burning carbon in dihydrogen giving carbon dioxide. But heat will not flow from cooler body to warmer body on its own. The gas in a container will not spontaneously contract into one corner, or carbon dioxide will not form carbon and dioxygen spontaneously. These and many other spontaneously occurring changes show unidirectional change. We may ask, what is the driving force of a spontaneously occurring changes? What determines the direction of a spontaneous change? In this section, we shall establish some criteria for these processes, whether these will take place or not. Let us first understand what do we mean by spontaneous reaction or change. You may think by your common observation that spontaneous reaction is one which occurs immediately when contact is made between the reactants. Take the case of combination of hydrogen and oxygen. These gases may be mixed at room temperature and left for many years without observing any perceptible change, although the reaction is taking place between them. It is at an extremely slow rate. It is still called spontaneous reaction. So spontaneity means having the potential to proceed without the assistance of external agency. However, it does not tell about the rate of reaction of the process. Another aspect of a spontaneous reaction or process, as we see, is that these cannot reverse their direction on their own. We may summarize it as follows. A spontaneous process is an irreversible process and may only be reversed by some external agency. A. Is decrease in enthalpy a criteria for spontaneity? If we examine the phenomena like flow of water downhill or fall of a stone onto the ground, we find that there is a net decrease in potential energy in the direction of change. By analogy, we may be tempted to state that a chemical reaction is spontaneous in a given direction because decrease in energy has taken place, as in the case of exothermic reaction. For example, half N2 plus 3 by 2 H2 gives out NH3. Delta RH value is minus 46.1 kilojoule per mole. Half H2 plus half Cl2 gives out HCl. Delta RH value is minus 92.32 kilojoule per mole. H2 plus half O2 gives out H2O. Delta RH value is equals to minus 285.8 kilojoule per mole. The decrease in enthalpy in passing from reactants to product may be shown for any exothermic reaction on an enthalpy diagram as shown in figure 6.10a. Thus, the postulates that driving force for a chemical reaction may be due to the decrease in energy sounds reasonable as the basis of evidence so far. Now, let us examine the following reactions. Half N2 plus O2 gives out NO2 and the delta RH is plus 33.2 kilojoule per mole. C plus 2S gives out CS2 and the delta RH value is plus 128.5 kilojoule per mole. Figure 6.10a enthalpy diagram for exothermic reactions. These reactions, though endothermic, are spontaneous. The increase in enthalpy may be represented on an enthalpy diagram as shown in figure 6.10b. Figure 6.10b enthalpy diagram for endothermic reaction. Therefore, it becomes obvious that while decrease in enthalpy may be a contributory factor for spontaneity, but it is not true for all cases. B. Entropy and spontaneity. Then what drives the spontaneous process in a given direction? Let us examine such a case in which delta H is equals to 0. That is, there is no change in enthalpy, but still the process is spontaneous. Let us consider diffusion of two gases into each other in a closed container which is isolated from the surrounding as shown in figure 6.11. The two gases, say gas A and gas B, are represented by black dots and white dots respectively. Here 6.11 diagram, diffusion of two gases, and separated by a movable partition. When the partition is withdrawn, that is in 6.11b, and the gases begin to diffuse into each other, and after a period of time diffusion will be complete. Here you can see the both diagram A and B. Let us examine the process before partition. If we were to pick up the gas molecules from left container, we would be sure that these will be molecules of gas A, and similarly if we were to pick up the gas molecules from right container, we would be sure that these molecules will be molecules of gas B. But if we were to pick up molecules from container when partition is removed, we are not sure whether the molecules picked are of gas A or gas B. We say that the system has become less predictable or more chaotic. We may now formulate another postulate. In an isolated system, there is always a tendency for the system's energy to become more disordered or chaotic, and this could be a criteria for spontaneous change. At this point, we introduce another thermodynamic function, entropy, denoted as S. The above mentioned disorder is the manifestation of entropy. To form a mental picture, one can think of entropy as a measure of the degree of randomness or disorder in the system. The greater the disorder in an isolated system, the higher is the entropy. As far as a chemical reaction is concerned, this entropy change can be attributed to rearrangement of atoms or ions from one pattern in the reactants to another in the products. If the structure of the product is very much disordered than that of reactants, there will be a resultant increase in entropy. The change in entropy accompanying a chemical reaction may be estimated qualitatively by a consideration of the structures of a species taking part in the reaction. Decrease of regularity in a structure would mean increase in entropy for a given substance. The crystalline solid state is the state of lowest entropy, most ordered, and the gaseous state is the state of highest entropy. Now let us try to quantify entropy. One way to calculate the degree of disorder or chaotic distribution of energy among molecules would be through statistical method, which is beyond the scope of this treatment. Other way would be to relate this process to the heat involved in a process, which would make entropy a thermodynamic concept. Entropy, like any other thermodynamic property such as internal energy U and enthalpy H, is a state function, and delta S is independent of path. Whenever heat is added to the system, it increases molecular motions, causing increased randomness of the system. Thus, heat has randomizing influence on the system. Can we equate delta S with Q? Wait. Experience suggests us that the distribution of heat also depends on the temperature at which heat is added to the system. A system at higher temperature has greater randomness in it than one at lower temperature. Thus, temperature is the measure of average chaotic motion of particles in the system. Heat added to a system at lower temperature causes greater randomness than when the same quantity of heat is added to at higher temperature. This suggests that the entropy change is inversely proportional to the temperature. Delta S is related with Q and T for a reversible reaction as delta S is equals to Q reversible upon T. The total entropy change delta S total for the system and surrounding of a spontaneous process is given by delta S total, delta S system and delta S surrounding is greater than 0. When a system is in equilibrium, the entropy is maximum and the change in entropy delta S is equals to 0. We can say that entropy for a spontaneous process increases till it reaches maximum and at equilibrium the change in entropy is 0. Since entropy is a state property, we can calculate the change in entropy of a reversible process by delta S system equal to Q system reversible upon T. We find that both the reversible and irreversible expansion for an ideal gas under isothermal condition delta U is equals to 0. But delta S total, that is delta S system plus delta S surrounding, is not 0 for irreversible process. Thus, delta U does not discriminate between reversible and irreversible processes, whereas delta S does. C. Gibbs energy and spontaneity. We have seen that for a system it is the total entropy change delta S total which decides the spontaneity of the process. But most of the chemical reactions fall into the category of either closed system or open systems. Therefore, for most of the chemical reactions there are changes in both enthalpy and entropy. It is clear from the discussion in previous sections that neither decrease in enthalpy nor increase in entropy alone can determine the direction of spontaneous change for these systems. For this purpose, we define a new thermodynamic function, the Gibbs energy or Gibbs function G. G is equals to H minus Ts. Gibbs function G is an extensive property and a state function. The change in Gibbs energy for the system, delta G system, can be written as delta G system is equals to delta H system minus T delta S system minus S system delta T. At constant temperature, delta T is equals to 0. Delta G system is equals to delta S system minus T delta S system. Usually the subscript system is dropped and we simply write this equation as delta G is equals to delta H minus T delta S. Thus Gibbs energy change, enthalpy change minus temperature into entropy change, that is equivalent to the Gibbs energy change and is referred to as the Gibbs equation, one of the most important equation in chemistry. Here we have considered both terms together for spontaneity, energy in terms of delta H and entropy delta S, a measure of disorder, as indicated earlier. Dimensionally, if we analyze, we find the delta G has units of energy because both delta H and the T delta S are energy terms, since T delta S is equals to K, J upon K is equals to J, Joule. Now let us consider delta G is related to the reaction spontaneity. We know delta S total is equals to delta S system plus delta S surrounding. If the system is in thermal equilibrium with the surrounding, then the temperature of the surrounding is the same as that of the system. Also, increase in enthalpy of the surrounding is equal to decrease in enthalpy of the system. Therefore, entropy change of surroundings, delta S surrounding is equals to delta H surrounding upon T is equals to minus delta H system upon T. So, delta S total is equals to delta S system plus in bracket minus delta H system upon T. After rearranging the above equation, we are having T delta S total is equals to T delta S system minus delta H system. And for spontaneous process, S delta S total is greater than 0. So, T delta S system is minus delta H system is greater than 0. So, the final we are having the negative in bracket delta H system minus T delta S system is greater than 0. Using equation 6.21, the above equation can be written as minus delta G is greater than 0. So, delta G is equals to delta H minus T delta S is less than 0. Delta S system is the enthalpy change of a reaction. T delta S system is the energy which is not available to do useful work. So, delta G is the net energy available to do useful work and is thus a measure of the free energy. For this reason, it is also known as the free energy of the reaction. Delta G gives a criteria for spontaneity at constant pressure and temperature. Number 1, delta G is negative. If then it means it is less than 0. The process is spontaneous. Number 2, if delta G is positive, it means greater than 0. The process is non-spontaneous. Note, if a reaction has a positive enthalpy change and positive entropy change, it can be spontaneous when T delta S is large enough to outweigh delta H. This can happen in two ways. A, the positive entropy change of the system can be small, in which case T must be large. B, the positive entropy change of the system can be large, in which case T may be small. The former is one of the reasons why reactions are often carried out at high temperature. Table 6.4 summarizes the effect of temperature on the spontaneity of reactions. D. Entropy and second law of thermodynamics. We know that for an isolated system, the change in energy remains constant. Therefore, increase in entropy in such system is the natural direction of spontaneous change. This is in fact the second law of thermodynamics. Like first law of thermodynamics, second law can also be stated in several ways. The second law of thermodynamics explains why spontaneous exothermic reactions are so common. In exothermic reactions, heat released by the reaction increases the disorder of the surroundings and overall entropy change is positive, which makes the reaction spontaneous. E. Absolute entropy and third law of thermodynamics. Molecules of a substances may move in a straight line in any direction. They may spin like a top and the bonds in the molecules may stretch and compress. These motions of the molecule are called translational, rotational, and vibrational motion respectively. When temperature of the system rises, these motions become more vigorous and entropy increases. On the other hand, when temperature is lowered, the entropy decreases. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. This is called third law of thermodynamics. This is so because there is a perfect order in a crystal at absolute zero. The statement is confined to pure crystalline solid because theoretical arguments and practical evidences have shown that entropy of a solution and supercooled liquid is not zero at 0 K. The importance of third law lies in the fact that it permits the calculation of absolute values of entropy of a pure substance from thermal data alone. For a pure substance, this can be done by summing Q reversible upon T increments from 0 Kelvin to 298 Kelvin. Standard entropies can be used to calculate standard entropy changes by a Hess law type of calculation. 6.7 Gibbs energy change and equilibrium. We have seen how a knowledge of the sign and magnitude of the free energy change of chemical reaction allows. Number 1. Prediction of the spontaneity of the chemical reaction. Number 2. Prediction of the useful work that could be extracted from it. So far, we have considered free energy changes in irreversible reactions. Let us now examine the free energy changes in reversible reactions. Reversible under strict thermodynamic sense is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surroundings. When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously so that a dynamic equilibrium is set up. This means that the reaction in both the directions should proceed with a decrease in free energy, which seems impossible. It is possible only if at equilibrium the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. So the criteria for equilibrium A plus B reversible C plus D is delta Rg is equals to 0. Gibbs energy for a reaction in which all reactants and products are in a standard state. Delta Rg is related to the equilibrium constant of the reaction as follows. So 0 is equals to delta Rg plus RT ln K, and delta Rg is equals to minus RT ln K, and delta Rg is equals to minus 2.303 RT log K. We also know that delta Rg is equals to delta Rh minus T delta Rs is equals to minus RT ln K. For strongly endothermic reactions, the value of delta Rh may be large and positive. In such a case, value of K will be much smaller than 1 and the reaction is unlikely to form much product. In case of exothermic reaction, delta Rh is large and negative and delta Rh is likely to be large and negative too. In such cases, K will be much larger than 1. We may expect strongly exothermic reactions to have a large K and hence can go to near completion. Delta Rg also depends upon delta Rs if the changes in the entropy of reaction is also taken into account. The value of K or extent of chemical reaction will also be affected. Table 6.4 Effect of temperature on spontaneity of the reaction. The term low temperature and high temperature are relative for a particular reaction. High temperature could even mean room temperature. depending on whether delta Rs is positive or negative. Using equation 6.24, number 1, it is possible to obtain an estimate of delta G from the measurement of delta H and delta S and then calculate K at any temperature for economic yields of the product. Number 2, if K is measured directly in the laboratory, value of delta G at any other temperature can be calculated using equation 6.24. Summary. Thermodynamics deals with energy change in chemical or physical processes and enable us to study these changes quantitatively and to make useful predictions. For these purposes, we divide the universe into the system and the surroundings. Chemical or physical processes lead to evolution for absorption of heat, part of which may be converted into work. These quantities are related through the first law of thermodynamics via delta U is equals to Q plus W. Delta U change in internal energy depends on initial and final states only and is a state function, whereas Q and W depends on the path and are not the state functions. We follow sign conventions of Q and W by giving the position sign to these quantities when these are added to the system. We can measure the transfer of heat from one system to another, which causes the change in temperature. The magnitude of rise in temperature depends on the heat capacity of a substance. Therefore, heat absorbed or evolved as Q is equals to C delta T. Work can be measured by W is equals to minus Px delta V in case of expansion of gases. Under reversible processes, we can put Pex is equals to P for infinitesimal changes in the volume of making W reversible is equals to minus P delta V or dV. In this condition, we can use gas equation PV is equals to nRT. At constant volume, W is equals to 0, then delta U is equals to QV. Heat transfer at constant volume, but in a study of chemical reaction, we usually have constant pressure. We define another state function, enthalpy. Enthalpy change delta H is equals to delta U plus delta NGRT can be found directly from the heat changes at constant pressure. Delta H is equals to QP, where the varieties of enthalpy changes, changes of phases such as melting, vaporization, and sublimation usually occur at constant temperature and can be characterized by enthalpy changes which are always positive. Enthalpy of formation, combustion, and other enthalpy changes can be calculated using Hess law. Enthalpy change for chemical reactions can be determined by delta RH is equals to summation AI delta F H products minus summation BI delta F H reactions or reactants, I think. And in gaseous state, delta RH is equals to summation bond enthalpies of the reactants minus summation of bond enthalpies of the products. First law of thermodynamics does not guide us about the direction of chemical reaction, that is what is the driving force of a chemical reaction. For isolated system, delta U is equals to 0, we define another state functions S entropy for this purpose. Entropy is a measure of disorder or randomness for a spontaneous change. Total entropy change is positive, therefore an isolated system delta U is equals to 0, delta S is greater than 0. So entropy change distinguishes a spontaneous change while energy change does not. Entropy change can be measured by the equation delta S is equals to Q reversible upon T for a reversible process. Q reversible T is an independent of path. Chemical reactions are generally carried at constant pressure, so we define another state function Gibbs Energy G, which is related to entropy and enthalpy changes of the system by the equation. Delta RG is equals to delta RH minus T delta RS. For a spontaneous change, delta G system is less than 0 and at equilibrium, delta G system is equals to 0. The standard Gibbs energy change is related to equilibrium constant by delta RG is equals to minus RT ln K. K can be calculated from this equation if we know delta RG, which can be found from delta RG is equals to delta RH minus T delta S. Temperature is an important factor in the equation. Many reactions which are non-spontaneous at lower temperature are made spontaneous at higher temperature for systems having positive entropy of reaction. And आज मैं बनाने वाली हूँ ऑडियो बुक क्लास 11th यूनिट 7 इक्विलिब्रियम चैप्टर की. ये चैप्टर थोड़ा सा लेंदी है, इसलिए इसके मैं 2 पार्ट में रिकॉर्ड करूंगी. सो आज मैं इसका फर्स्ट पार्ट रिकॉर्ड कर रही हूँ एंड सेम डे ही आपको इसका सेकेंड पार्ट प्रोवाइड कर दूंगी. बच्चों, अगर ये ऑडियो बुक्स आपकी रिवीजन में हेल्प कर रही हैं तो इसको प्लीज अपने दोस्तों के साथ भी शेयर करिए और इसको लाइक भी जरूर करिएगा. और अगर आप मेरे चैनल पे नए हैं तो इसको सब्सक्राइब भी कीजिएगा. चलिए टाइम वेस्ट नहीं करते हैं और जल्दी से स्टार्ट करते हैं. केमिकल इक्विलिब्रिया are important in numerous biological and environmental processes. For example, equilibria involving O2 molecules and the protein hemoglobin play a crucial role in the transport and delivery of O2 from our lungs to our muscles. Similar equilibria involving CO molecules and hemoglobin account for the toxicity of CO. When a liquid evaporates in a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, and number of liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. It gives rise to a constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equals the number returning to liquid from the vapor. We say that the system has reached equilibrium state at this stage. However, this is not a static equilibrium and there is a lot of activity at the boundary between the liquid and the vapor. Thus, at equilibrium, the rate of evaporation is equal to the rate of condensation. It may be represented by H2O, reversible reaction, that is liquid, and it is forming vapor. The double half arrows indicate that the process in both directions are going on simultaneously. The mixture of reactants and products in the equilibrium state is called an equilibrium mixture. Equilibrium can be established for both physical processes and chemical reactions. The reaction may be fast or slow depending on the experimental conditions and the nature of reactants. When the reactants in a closed vessels are a particular temperature react to give products, the concentration of the reactants keep on decreasing while those of products keep on increasing for some time alter which there is no change in the concentration of either of the reactants or products. This stage of the system is the dynamic equilibrium and the rates of the forward and reverse reactions become equal. It is due to this dynamic equilibrium stage that there is no change in the concentrations of various species in the reaction mixture. Based on the extent to which the reactions proceed to reach the state of chemical equilibrium, these may be classified in these groups. Number 1. The reactions that proceed nearly to completion and only negligible concentration of the reactants are left. In some cases, it may not be even possible to detect these experimentally. Number 2. The reactions in which only small amounts of products are formed and most of the reactants remain unchanged at equilibrium stage. Number 3. The reactions in which the concentration of the reactants and products are comparable when the system is in equilibrium. The extent of a reaction in equilibrium varies with the experimental conditions such as concentration of reactants, temperature, etc. Optimization of the operational conditions is very important in industry and laboratory so that the equilibrium is favorable in the direction of desired product. Some important aspects of equilibrium involving physical and chemical processes are dealt in this unit along with equilibrium involving ions in aqueous solution, which is called as ionic equilibrium. 7.1 Equilibrium in physical processes. The characteristics of system at equilibrium are better understood if we examine some physical processes. The most familiar examples are phase transformation processes, example solid to liquid, liquid to gas, solid to gas, and the vice versa. 7.1.1 Solid liquid equilibrium. Ice and water kept in a perfectly insulated thermos flask. There is no exchange of heat between its content and the surroundings. At 273 Kelvin and the atmospheric pressure are in equilibrium state and the system shows interesting characteristic features. We observe that the mass of ice and water do not change with time and the temperature remains constant. However, the equilibrium is not static. The intense activity can be noticed at the boundary between ice and water. Molecules from the liquid water collide against ice and adhere to it, and some molecules of ice escape into liquid phase. There is no change of mass of ice and water as the rates of transfer of molecules from ice into water and the reverse transfer from water into ice are equal at atmospheric pressure and 273 Kelvin. It is obvious that ice and water are in equilibrium only at particular temperature and pressure. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium is called the normal melting point or normal freezing point of the substance. The system here is in dynamic equilibrium and we can infer the following. Number 1. Both the opposing processes occur simultaneously. Number 2. Both the processes occurs at the same rate so that the amount of ice and water remains constant. 7.1.2 Liquid Vapor Equilibrium. This equilibrium can be better understood if we consider the example of a transparent box carrying a U-tube with mercury manometer. Drying agent like anhydrous calcium chloride or phosphorus pentaoxide is placed for a few hours in the box. After removing the drying agent by tilting the box on one side, a watch glass or petri dish containing water is quickly placed inside the box. It will be observed that the mercury level in the right limb of the manometer slowly increases and finally attains a constant value. That is, the pressure inside the box increases and reaches a constant value. Also, the volume of water in the watch glass decreases. Figure 7.1. Initially, there was no water vapor or very less inside the box. 7.1 measuring equilibrium of vapor pressure of water at a constant temperature. As water evaporated, the pressure in the box increased due to addition of water molecules into the gaseous phase inside the box. The rate of evaporation is constant. However, the rate of increase in pressure decreases with time due to condensation of vapor into water. Finally, it leads to an equilibrium condition when there is no net evaporation. This implies that the number of water molecules from the gaseous state into the liquid state also increases till the equilibrium is attained. That is, rate of evaporation is equal to the rate of condensation. At equilibrium, the pressure exerted by the water molecules at a given temperature remains constant and is called the equilibrium vapor pressure of water, or just vapor pressure of water. Vapor pressure of water increases with temperature. If the above experiment is repeated with methyl alcohol, acetone and ether, it is observed that different liquids have different equilibrium vapor pressure at the same temperature, and the liquid which has a higher vapor pressure is more volatile and has lower boiling point. If we expose 3 watch glasses containing separately 1 ml each of acetone, ethyl alcohol and water to atmosphere and repeat the experiment with different volumes of the liquids in a warmer room, it is observed that in all such cases the liquid eventually disappears and the time taken for complete evaporation depends on number 1, the nature of the liquid, number 2, the amount of the liquid, and number 3, the temperature. When the watch glass is opened to the atmosphere, this rate of evaporation remains constant, but the molecules are dispersed into large volume of the room. As a consequence, the rate of condensation from vapor to liquid state is much less than the rate of evaporation. These are open systems and it is not possible to reach equilibrium in an open system. Water and water vapor are in equilibrium position at atmospheric pressure, that is 1.013 bar, and at 100 degrees Celsius in a closed vessel. The boiling point of water is 100 degrees Celsius at 1.013 bar pressure. For any pure liquid at 1 atmospheric pressure, that is 1.013 bar, the temperature at which the liquid and vapors are at equilibrium is called the normal boiling point of the liquid. Boiling point of the liquid depends on the atmospheric pressure. It depends on the altitude of the place. At high altitude, the boiling point decreases. 7.1.3 Solid Vapor Equilibrium. Let us now consider the systems where solids sublime to vapor phase. If we place solid iodine in a closed vessel, after some time the vessel gets filled up with the violet vapor and the intensity of the color increases with time. After a certain time, the intensity of color becomes constant and at this stage equilibrium is attained. Hence, solid iodine sublimes to give iodine vapor and the iodine vapor condenses to give solid iodine. The equilibrium can be represented as I2 solid, and here is the I2 vapor. Other examples showing this kind of equilibrium, that is a camphor solid to the camphor vapor and NH4Cl solid to the NH4Cl vapor. 7.1.4 Equilibrium involving dissolution of solid or gases in liquids. Solids in liquids. We know from our experience that we can dissolve only a limited amount of salt or sugar in a given amount of water at room temperature. If we make a thick sugar syrup solution by dissolving sugar at higher temperature, sugar crystals separate out if we cool the syrup to the room temperature. We call it at a saturated solution when no more of solute can be dissolved in it at a given temperature. The concentration of the solute in a saturated solution depends upon the temperature. In a saturated solution, a dynamic equilibrium exists between the solute molecules in the solid state and in the solution. Sugar solution converted into the sugar solid, and the rate of dissolution of sugar is equals to the rate of crystallization of sugar. Equality of the two rates and dynamic nature of equilibrium has been confirmed with the help of radioactive sugar. If we drop some radioactive sugar into saturated solution of non-radioactive sugar, then after some time radioactivity is observed both in the solution and in the solid sugar. Initially, there were no radioactive sugar molecules in the solution, but due to dynamic nature of equilibrium, there is exchange between the radioactive and non-radioactive sugar molecules between the two phases. The ratio of the radioactive to non-radioactive molecules in the solution increases till it attains a constant value. Gases and liquids. When a soda water bottle is opened, some of the carbon dioxide gas dissolved in it fizzes out rapidly. The phenomena arises due to difference in solubility of carbon dioxide at different pressures. There is equilibrium between the molecules in the gaseous state and the molecules dissolved in the liquid under pressure, that is, CO2 gas converted into the CO2 in solution. This equilibrium is governed by Henry's law, which states that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to pressure of the gas above the solvent. This amount decreases with increase of temperature. The soda water bottle is sealed under pressure of gas when its solubility in water is high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escapes to reach a new equilibrium condition required for the lower pressure, namely its partial pressure in the atmosphere. This is how the soda water in bottle, when left open to the air for some time, turns flat. It can be generalized that number 1, for solid to liquid equilibrium, there is only one temperature melting point at 1 atmospheric at which the two phases can coexist. If there is no exchange of heat with the surroundings, the mass of the two phases remain constant. Number 2, for liquid vapor equilibrium, the vapor pressure is constant at a given temperature. Number 3, for dissolution of solids and liquids, the solubility is constant at given temperature. Number 4, for dissolution of gases in liquids, the concentration of gas in liquid is proportional to the pressure, that is concentration of the gas over the liquid. These observations are summarized in table 7.1. Here you can see some features of physical equilibria. That is the process and the conclusion. In liquid to vapor, that is H2O liquid to the H2O vapor, that is PH2O constant at given temperature. In the solid to liquid phase, the melting point is fixed at constant pressure. And in the solute to the solute solution, just like sugar to the sugar solution, the concentration of solute in solution is constant at a given temperature. Gas to gas aqueous form, that is CO2 gaseous to CO2 aqueous form, that is constant at a given temperature. 7.1.5 General characteristics of equilibria involving physical processes. For the physical processes discussed above, following characteristics are common to the system at equilibrium. Number 1, equilibrium is possible only in a closed system at a given temperature. Number 2, both the opposing processes occur at the same rate and there is a dynamic but stable condition. Number 3, all measurable properties of the system remain constant. Number 4, when equilibrium is attained for a physical processes, it is characterized by constant value of one of its parameters at a given temperature. Table 7.1 lists such quantities. Number 5, the magnitude of such quantities at any stage indicates the extent to which the physical processes has proceeded before reaching equilibrium. 7.2 Equilibrium in chemical processes, that is dynamic equilibrium. Analogous to the physical system, chemical reaction also attain a state of equilibrium. These reactions can occur both in forward and backward directions. When the rates of the forward and reverse reactions become equal, the concentration of the reactants and the products remain constant. This is the stage of chemical equilibrium. This equilibrium is dynamic in nature as it consists of forward reaction in which the reactants give products and reverse reaction in which product gives the original reactants. For a better comprehension, let us consider a general case of reversible reaction, that is A plus B reversible C plus D. With passage of time, there is accumulation of the product C and D and depletion of the reactants A and B, figure 7.2. This leads to a decrease in the rate of forward reaction and an increase in the rate of reverse reaction. Here you can see figure 7.2, that is the attainment of chemical equilibrium. Eventually, the reaction occurs at same rate and the system reaches a state of equilibrium. Similarly, the reaction can reach the state of equilibrium even if we start with only C and D. That is, no A and B being present initially, as the equilibrium can be reached from either direction. The dynamic nature of chemical equilibrium can be demonstrated in the synthesis of ammonia by Haber's process. In a series of experiments, Haber started with known amounts of dinitrogen and dihydrogen maintained at high temperature and pressure, and regular intervals determined the amount of ammonia present. He was successful in determining also the concentration of unreacted dihydrogen and dinitrogen. Figure 7.4, page number 191, shows that after a certain time the composition of the mixture remains the same even though some of the reactants are still present. This constancy in composition indicates that the reaction has reached equilibrium. In order to understand the dynamic nature of the reaction, synthesis of ammonia is carried out with exactly the same starting condition of partial pressure and temperature, but using D2, that is deuterium, in place of H2. The reaction mixture starting either with H2 or D2 reach equilibrium with the same composition, except that D2 and ND3 are present instead of H2 and NH3. After equilibrium is attained, these two mixtures are mixed together and left for a while. Later, when this mixture is analyzed, it is found that the concentration of ammonia is just the same as before. However, when this mixture is analyzed by a mass spectrometer, it is found that ammonia and all deuterium containing forms of ammonia, NH3, NH2D, NHD2 and ND3, and dihydrogen and its deuterated forms H2, HD and D2 are present. Thus, one can conclude that scrambling of H and D atoms in the molecule must result from a continuation of the forward and reverse reactions in the mixture. If the reaction had simply stopped when they reached equilibrium, then there would have been no mixing of isotopes in this way. Use of isotope deuterium in the formation of ammonia clearly indicates that chemical reaction reach a state of dynamic equilibrium in which the rates of forward and reverse reaction are equal and there is no net change in composition. Equilibrium can be attained from both sides, whether we start reaction by taking H2 and N2 and get NH3, or by taking NH3 and decomposing it into the N2 and H2. N2 plus 3H2 gives out 2NH3. 2NH3 gives out N2 plus 3H2. Similarly, let us consider the reaction H2 plus I2 gives out 2HI, and if we start with equal initial concentration of H2 and I2, the reaction proceeds in the forward direction and the concentration of H2 and I2 decreases while that of HI increases until all of these become a constant at equilibrium, figure 7.5. We can also start with HI alone and make the reaction to proceed in the reverse direction. The concentration of HI will increase and concentration of H2 and I2 will increase until they all become constant when equilibrium is reached, figure 7.5. If total number of H and I atoms are same in a given volume, the same equilibrium mixture is obtained whether we start it from pure reactants or pure products. You can see figure 7.4 here, that is a depiction of equilibrium for the reaction. And this is the figure 7.5, that is chemical equilibrium in the reaction H2 plus I2 gives out 2HI can be attained from either direction. We have one separate paragraph, that is the dynamic equilibrium, and that is a student activity. You can see here. That is a figure 7.3. Now come to the 7.3 law of equilibrium and equilibrium constant. A mixture of reactants and products in the equilibrium state is called an equilibrium mixture. In this section, we shall address a number of important questions about the composition of equilibrium mixtures. What is the relationship between the concentration of reactants and products in an equilibrium mixture? How can we determine equilibrium concentration from initial concentrations? What factors can be exploited to alter the composition of an equilibrium mixture? The last question in particular is important when choosing condition for synthesis of industrial chemicals such as H2, NH3, CaO, etc. To answer these questions, let us consider a general reversible reaction, A plus B reversible C plus D, where A and B are the reactants, C and D are the products in the balanced chemical equation. On the basis of experimental studies of many reversible reactions, the Norwegian chemist Cato, Maximilian Guldberg and Peter Wagg proposed in 1864 that the concentration in an equilibrium mixture are related by the following equilibrium equation. Kc is equals to Cd upon AB, where Kc is the equilibrium constant and the expression on the right side is called the equilibrium constant expression. The equilibrium equation is also known as the law of mass action because in the early days of chemistry, concentration was called active mass in order to appreciate their work better. Let us consider reaction between gases S2 and I2 and carried out in a sealed vessel at 731 Kelvin. H2 plus I2 and gives out 2Hi and 1 mole of H2, 1 mole of I2 and it is forming the 2 mole of Hi. 6 sets of experiment with varying initial condition were performed, starting with only gases S2 and I2 in a sealed reaction vessel in first 4 experiment and only Hi in other 2 experiment. Experiment 1, 2, 3 and 4 were performed taking different concentration of S2 and or I2, and with time it was observed that intensity of the purple color remained constant and equilibrium was attained. Similarly, for experiment 5 and 6, the equilibrium was attained from the opposite direction. Data obtained from all 6 sets of experiments are given in table 7.2. It is evident from the experiments 1, 2, 3 and 4 that number of moles of dihydrogen reacted is equal to the number of moles of iodine reacted is equals to the half number of moles of Hi formed. Also, experiment 5 and 6 indicates that H2 is equals to I2. Knowing the above facts, in order to establish a relationship between the concentration of reactants and products, several combinations can be tried. Let us consider the simple expression, that is Hi upon H2 and I2. It can be seen from table 7.3 that if we put the equilibrium concentration of the reactant and products, the above expression, here you can see the table 7.2, initial and equilibrium constant of S2 and Hi, different values it is. And here is the table 7.3, that is the expression involving the equilibrium concentration of reactant, that is H2 plus I2 gives out 2Hi. So here the different experiment, all the 6 experiments and all the different values you can get. We find that this expression gives constant value as shown in table 7.3 in all the 6 cases. It can be seen that in the expression the power of the concentration for reactants and the products are actually the stoichiometric coefficient in the equation for the chemical reaction. Thus, for the reaction H2 plus I2 gives out 2Hi. Following equation 7.1, the equilibrium constant Kc is written as Kc is equals to Hi the whole square upon H2 plus I2. This is equation 7.2. Generally, the subscript EQ used for equilibrium is omitted from the concentration terms. It is taken for granted that the concentrations in the expression for Kc are equilibrium values. We therefore write Kc is equals to Hi whole square upon H2 plus H2 and I2. So this is the equation 7.3. The subscript C indicates that Kc is expressed in concentration of mole per liter. At a given temperature, the product of concentrations of the reaction products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of concentration of the reactants raised to their individual stoichiometric coefficient has a constant value. This is known as the equilibrium law or law of chemical equilibrium. The equilibrium constant for a general reaction AA plus BB reversible reaction, it is Cc plus dt, and is expressed as Kc is equals to C to the power C D to the power D upon A to the power A and B to the power B, where A, B, C and D are the equilibrium concentrations of the reactants and product. Equilibrium constant for the reaction 4NH3 plus 5O2 reversible reaction gives out 4NO plus 6H2O is written as Kc is equals to NO whole power 4 H2O whole to the power 6 upon NH3 whole to the power 4 and O2 whole to the power 5. Molar concentration of different species is indicated by enclosing these in a square bracket and as mentioned above. It is implied that these are equilibrium concentration while writing expression for equilibrium constant, symbol for phases are generally ignored. Let us write equilibrium constant for the reaction H2 plus I2 gives out 2Hi and Kc is equals to Hi whole square upon H2 I2 is equals to X. The equilibrium constant for the reverse reaction 2Hi gives out H2 plus I2 at the same temperature is K dash C is equals to H2I2 upon Hi whole square, that is 1 upon X is equals to 1 upon Kc. So thus K dash C is equals to 1 upon Kc. Equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. If we change the stoichiometric coefficients in a chemical equation by multiplying throughout by a factor, then we must make sure that expression for equilibrium constant also reflects that change. For example, if the reaction is written as half H2 plus half I2 gives out Hi. The equilibrium constant for the above reaction is given by K double dash C is equals to Hi upon H2 to the power half, and I2 to the power half is equals to Hi whole square upon H2 I2 the whole to the power half. So x to the power 1 by 2 is equals to Kc to the power 1 by 2. On multiplying the equation 7.5 by n, we get NH2 plus Ni2 gives out 2NHI. Therefore, equilibrium constant for the reaction is equal to Kc to the power n. These findings are summarized in table 7.4. It should be noted that because of the equilibrium constant Kc and K-C have different numerical values, it is important to specify the form of balanced chemical equation when quoting the value of an equilibrium constant. Here is the table 7.4, relationship between equilibrium constant for a general reaction and its multiples. Here you can see the problems. 7.4 Homogeneous Equilibria. In a homogeneous system, all the reactants and products are in the same phase. For example, in the gaseous reaction N2 plus 3H2 reversible to NH3, reactants and products are in the homogeneous phase. Similarly, for the reaction CH3COO C2H5 plus H2O gives out CH3COOH plus C2H5OH, that is a reversible reaction. Here all the reactions are the reversible. And Fe3 positive plus SCN negative gives out FeSCN2 positive. All the reactants and the products are in homogeneous solution phase. We shall now consider equilibrium constant for some homogeneous reactions. 7.4.1 Equilibrium constant in gaseous system. So far we have expressed equilibrium constant of the reactions in terms of molar concentration of the reactants and products and used symbol Kc for it. For reactions involving gases, however, it is usually more convenient to express the equilibrium constant in terms of partial pressure. The ideal gas equation is written as PV is equals to nRT and P is equals to N upon V RT. Here P is the pressure in Pascal, N is the number of moles of the gas, V is the volume in meter cube and T is the temperature in Kelvin. Therefore, N upon V is concentration expressed in mole per meter cube. If concentration C is in mole per liter or mole per dm cube and P is in bar, then P is equals to CRT. We can also write P is equals to gas RT. And here R is equals to 0.0831 bar liter per mole K. At constant temperature, the pressure of the gas is proportional to its concentration, that is P is proportional to gas. For reaction in equilibrium, H2 plus I2 gives out 2Hi. We can write either Kc is equals to Hi whole square upon H2 plus I2. So Kc is equals to Phi whole square upon Ph2 upon Pi2. Further, since Phi is equals to HiRT, Pi2 is equals to I2RT and Ph2 is equals to H2RT. Therefore, Kp is equals to Phi whole square upon Ph2 Pi2. Hi whole square RT whole square upon H2 RT dot, it means multiply, so IT R2. RT and Hi whole square upon H2 I2 is equals to Kc. In this example, Kp is equals to Kc, that is both equilibrium constants are equal. However, this is not always the case. For example, in the reaction N2 plus 3H2 is equals to 2NHR NH3 and Kp is equals to PNH3 whole square upon Pn2 and PH2 whole cube. And here you can see the remaining calculation. So after the complete calculation, we are getting Kp is equals to Kc RT whole to the power minus 2. Similarly, for a general reaction AA plus BB reversible, that is Cc plus Dd. And here you can see the value of Kp. And the final value of Kp we are getting here, that is the Kc RT to the power delta N, where delta N is equals to number of moles of gaseous product minus number of moles of gaseous reactants in the balanced chemical equation. It is necessary that while calculating the value of Kp, pressure should be expressed in bar, because the standard state for pressure is 1 bar. We know from unit 1 that 1 Pascal is equals to 1 Newton per meter square and 1 bar is equals to 10 to the power 5 Pascal. Kp values for a few selected reactions at different temperatures are given in table 7.5, that is equilibrium constant Kp for a few selected reactions. Here you can see the reactions and their temperature, and at that particular temperature the value of Kp. 7.5 Heterogeneous Equilibria. Equilibrium in a system having more than one phase is called heterogeneous equilibrium. The equilibrium between water vapor and liquid water in a closed container is an example of heterogeneous equilibrium. H2O liquid gives out H2O gas. In this example, there is a gas phase and a liquid phase. In the same way, equilibrium between a solid and its saturated solution, CaOH whole twice plus, that is the solid form, plus aqueous is equals to Ca2 positive plus 2OH negative, is a heterogeneous equilibrium. Heterogeneous equilibrium often involve pure solids or liquids. We can simplify equilibrium expressions for the heterogeneous equilibria involving a pure liquid or a pure solid as the molar concentration of pure solid or liquid is constant, that is independent of the amount present. In the other words, if a substance X is involved, then X and X solid and X liquid are constant. Whatever the amount of X is taken, contrary to this, X gaseous and X aqueous will vary as the amount of X in a given volume varies. Let us take thermal dissociation of calcium carbonate, which is an interesting and important example of heterogeneous chemical equilibrium. CaCO3, on heating it gives out CaO plus CO2. On the basis of a stoichiometric equation, we can write Kc is equals to CaO into CO2 upon CaCO3. Since CaCO3 and CaO are both constant, therefore modified equilibrium constant for the thermal decomposition of calcium carbonate will be K-C is equals to CO2 or Kp is equals to PCO2. Units of equilibrium. The value of equilibrium constant Kc can be calculated by substituting the concentration terms in mole per liter, and for Kp partial pressure is substituted in Pascal, kPa bar or atmospheric. This results in units of equilibrium constant based on molarity or pressure, unless the exponents of both the numerator and denominator are same. For the reactions, H2 plus I2 gives out 2Hi, Kc and Kp have no unit. N2O4 gives out 2NO2 and both are gaseous form. Kc has unit mole per liter and Kp has unit bar. Equilibrium constants can also be expressed as dimensionless quantities if the standard state of reactants and products are specified. For a pure gas, the standard state is 1 bar. Therefore, a pressure of 4 bar in a standard state can be expressed as 4 bar per 1 bar is equals to 4. It means 4 upon 1, which is a dimensionless number. Standard state C0 for a solute is 1 molar solution and all concentration can be measured with the respect to it. The numerical value of equilibrium constant depends on a standard state chosen. Thus, in this system, both Kp and Kc are dimensionless quantities but have different numerical values due to different standard states. This shows that at a particular temperature, there is a constant concentration or pressure of CO2 in equilibrium with CaO and CaCO3. Experimentally, it has been found that at 1100 Kelvin, the pressure of CO2 in equilibrium with CaCO3 and CaO is 2 into 10 to the power 5 Pascal. Therefore, equilibrium constant at 1100 Kelvin for the above reaction is Kp is equals to PCO2 is equals to 2 into 10 to the power 5 Pascal upon 10 to the power 5 Pascal is equals to 2. Similarly, in the equilibrium between nickel carbon monoxide and nickel carbonyl used in purification of nickel. So, Ni plus 4CO gives out NiCO whole 4. And the equilibrium constant is written as Kc is equals to NiCO whole 4 upon CO to the power 4. And it must be remembered that for the existence of heterogeneous equilibrium, pure solids or liquid must also be present. However small the amount may be at equilibrium, but their concentrations or partial pressures do not appear in the expression of the equilibrium constant. In the reaction, Ag2O plus 2HNO3 gives out 2AgNO3 plus H2O. Kc is equals to AgNO3 whole twice upon HNO3 whole twice. 7.6 Applications of equilibrium constants. Before considering the application of equilibrium constant, let us summarize the important features of equilibrium constant as follows. Number 1. Expression for equilibrium constant is applicable only when concentration of the reactants and products have attained constant value at equilibrium state. Number 2, the value of equilibrium constant is independent of initial concentration of the reactants and products. Number 3, equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by a balanced equation at a given temperature. Number 4, the equilibrium constant for the reverse reaction is equal to the inverse of the equilibrium constant for the forward reaction. Number 5, the equilibrium constant K for a reaction is related to the equilibrium constant of the corresponding reaction, whose equation is obtained by multiplying or dividing the equation for the original reaction by a small integer. Let us consider applications of equilibrium constant to predict the extent of a reaction on the basis of its magnitude, predict the direction of the reaction, and calculate equilibrium concentration. 7.6.1 Predicting the extent of a reaction. The numerical value of the equilibrium constant for a reaction indicates the extent of the reaction. But it is important to note that an equilibrium constant does not give any information about the rate at which the equilibrium is reached. The magnitude of Kc or Kp is directly proportional to the concentrations of the product as these appear in the numerator of equilibrium constant and inversely proportional to the concentration of the reactant. This implies that a high value of K is suggestive of a high concentration of products and vice versa. We can make the following generalizations concerning the composition of equilibrium mixture. If Kc is greater than 10 to the power 3, products predominate over reactants, that is, if Kc is very large, the reaction proceeds nearly to completion. Consider the following example. A. The reaction of H2 with O2 at 500 K has a very large equilibrium constant. Kc is equals to 2.4 into 10 to the power 47. B. H2 plus Cl2 gives out 2HCl at 300 K as Kc is equals to 4 into 10 to the power 31. C. H2 plus Br2 gives out 2 HBr at 300 K. Kc is equals to 5.4 into 10 to the power 18. If Kc is less than 10 to the power minus 3, reactants predominate over products, that is, if Kc is very small, the reaction proceeds rarely. Consider the following examples. A. The decomposition of H2O into H2 and O2 at 500 K has a very small equilibrium constant. Kc is equals to 4.1 into 10 to the power minus 48. B. N2 plus O2 reversible to NO at 298 K has Kc is equals to 4.8 into 10 to the power minus 31. If Kc is in the range of 10 to the power minus 3 to 10 to the power 3, appreciable concentrations of both reactants and products are present. Consider the following examples. A. For reaction of H2 with I2 to give Hi, Kc is equals to 57 at 700 Kelvin. B. Also gas phase decomposition of N2O4 to NO2 is another reaction with a value of Kc is equals to 4.64 into 10 to the power minus 3 at 25 degrees Celsius, which is neither too small nor too large. Hence, equilibrium mixture contain appreciable concentrations of both N2O4 and NO2. These generalizations are illustrated in figure 7.6. You can see here the dependence of extent of reaction on Kc in figure 7.6. 7.6.2 Predicting the direction of reaction. The equilibrium constant helps in predicting the direction in which a given reaction will proceed at any stage. For this purpose, we calculate the reaction quotient, that is Q. The reaction quotient QC with molar concentration and QP with partial pressures is defined in the same way as the equilibrium constant Kc kept that concentration in QC are not necessarily equilibrium values. For a general reaction, AA plus BB gives out CC plus DD. QC is equals to C to the power C, D to the power D upon A to the power A, B to the power B. Then, if QC is greater than Kc, the reaction will proceed in the direction of reactants, that is a reverse reaction. And if QC is less than Kc, the reaction will proceed in the direction of the products, that is a forward reaction. If Qc is equals to Kc, the reaction mixture is already at equilibrium. Consider the gaseous reaction of H2 with I2. H2 plus I2 reversible reaction to Hi. Kc is equals to 57 at 700 Kelvin. Suppose we have molar concentration H2 0.10 m and I2 is 0.20 m and Hi is 0.40 m. The subscript T on the concentration symbols means that the concentration were measured at some arbitrary time T, not necessarily at equilibrium. Thus, the reaction quotient, that is Qc at this stage of the reaction, is given by Qc is equals to Hi whole square upon H2 and I2, and the suffix is T, and that is the 0.40 upon 0.10 into 0.20, and here in the above reaction the 0.40 whole square it is, so the answer is 8. Now in this case QC8 does not equal to Kc57, so the mixture of H2, I2 and Hi is not at equilibrium, that is more H2 and I2 will react to form more Hi and their concentration will decrease till Qc is equals to Kc. The reaction quotient Qc is useful in predicting the direction of reaction by comparing the value of Qc and Kc. Thus, we can make the following generalization concerning the direction of the reaction in figure 7.7. That is actually predicting the direction of the reaction. So, if Qc is less than Kc, net reaction goes from left to right. If Qc is greater than Kc, net reaction goes from right to left. And if Qc is equals to Kc, no net reaction occurs. 7.6.3 Calculating Equilibrium Concentrations. In case of a problem in which we know that initial concentration but do not know any of the equilibrium concentrations, the following 3 steps shall be followed. Step 1. Write the balanced equation for the reaction. Step 2. Under the balanced equation, make a table that lists for each substance involved in the reaction. A. The initial concentration. B. The change in concentration on going to equilibrium. And C. The equilibrium concentration. In constructing the table, define X as the concentration mole per liter of one of the substances that reacts on going to equilibrium. Then use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. Step 3. Substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve for X. If you are to solve a quadratic equation, choose the mathematical solution that makes chemical sense. Step 4. Calculate the equilibrium concentrations from the calculated value of X. And step 5. Check your result by substituting them into the equilibrium equation. And here is the problem 7.8 and 7.9. 7.7 Relationship between equilibrium constant K, reaction quotient Q and Gibbs energy G. The value of Kc for a reaction does not depend on the rate of reaction. However, as you have studied in Unit 6, it is directly related to the thermodynamics of the reaction and in particular to the change in Gibbs energy delta G. If delta G is negative, then the reaction is spontaneous and proceeds in the forward direction. If delta G is positive, then reaction is considered non-spontaneous. Instead, a reverse reaction would have a negative delta G. The products of the forward reaction shall be converted into the reactants. And delta G is if 0, then the reaction has achieved equilibrium at this point. There is no longer any free energy left to drive the reaction. And here is a mathematical expression of this thermodynamic view of equilibrium can be described by the following equation. Delta G is equals to delta G negative plus RT ln Q. And here the G negative is a standard Gibbs energy, and at equilibrium when delta G is equals to 0, Q is equals to Kc. And we are having the final equation ln K is equals to minus delta G upon RT. So here K value we are having e to the power minus delta G upon RT. Hence, using the equation 7.23, the reaction and spontaneity can be interpreted in the terms of value of delta G. If delta G negative is less than 0, then minus delta G negative upon RT is positive and the E to the power minus dG upon RT is greater than 1, making K is equals greater than 1, which implies a spontaneous reaction or the reaction which proceeds in the forward direction to such an extent that the products are present predominantly. And if delta G negative is greater than 0, then minus delta G upon RT is negative and E minus delta G upon RT is less than 1, that is K is less than 1, which implies a non-spontaneous reaction for a reaction which proceeds in forward direction to such a small degree that only a very minute quantity of product is formed. Now the problem 7.10, 7.11. 7.8 Factors affecting equilibria. One of the principal goals of chemical synthesis is to maximize the conversion of the reactants to products while minimizing the expenditure of energy. That this implies maximum yield of products at mild temperature and pressure condition. If does not happen, then the experimental condition need to be adjusted. For example, in the Haber process for the synthesis of ammonia from N2 and H2, the choice of experimental conditions is of real economic importance. Annual world product of ammonia is about 100 million tons, primarily for use as fertilizers. Equilibrium constant Kc is independent of initial concentrations, but if a system at equilibrium is subjected to a change in the concentration of one or more of the reacting substances, then the system is no longer at equilibrium and net reaction takes place in some direction until the system returns to equilibrium once again. Similarly, a change in temperature or pressure of the system may also alter the equilibrium. In order to decide what course the reaction adopts and make a qualitative prediction about the effect of a change in conditions on equilibrium, we use Le-Chatelier's principle. It states that a change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. This is applicable to all physical and chemical equilibria. We shall now be discussing factors which can influence the equilibrium. 7.8.1 Effect of concentration change. In general, when equilibrium is disturbed by the addition or removal of any reactant or product, Le-Chatelier's principle predicts that number 1. The concentration stress of an added reactant or product is relieved by net reaction in the direction that consumes the added substance. Number 2. The concentration stress of removed reactant or product is relieved by net reaction in the direction that replenishes the removed substance, or in other words, we can say, when the concentration of any of the reactants or products in a reaction at equilibrium is changed, the composition of the equilibrium mixture changes so as to minimize the effect of concentration changes. Let us take the reaction H2 plus I2 reversible to HI. If H2 is added to the reaction mixture at equilibrium, then the equilibrium of the reaction is disturbed. In order to restore it, the reaction proceeds in a direction wherein H2 is consumed, that is, more of H2 and I2 react to form HI, and finally the equilibrium shifts in right direction, that is forward. And this is in accordance with the Le-Chatelier's principle, which implies that in case of addition of reactant or product, a new equilibrium will set up in which concentration of the reactant or product should be less than what it was after the addition but more than what it was in the original mixture. Here you can see figure 7.8. That is the effect of addition of H2 on change of concentration for the reactants and products in the reaction. The same point can be explained in terms of the reaction quotient QC, that is QC is equals to HI whole square upon H2I2. Addition of hydrogen at equilibrium results in value of QC being less than Kc. Thus, in order to attain equilibrium, again reaction moves in the forward direction. Similarly, we can say that removal of a product also boosts the forward reaction and increases the concentration of the products, and this has great commercial application in cases of reaction where the product is a gas or a volatile substance. In case of manufacture of ammonia, ammonia is liquefied and removed from the reaction mixture so that reaction keeps moving in forward direction. Similarly, in the large-scale production of CaO used as important building material from CaCO3, constant removal of CO2 from the kiln drives the reaction to completion. It should be remembered that continuous removal of a product maintains QC at a value less than Kc and reaction continues to move in the forward direction. Effect of concentration, that is an experiment. This can be demonstrated by the following reaction, and here is the reaction. Fe3 positive plus SCN negative gives out FeSCN whole 2 positive. And that was initially yellow Fe and SCN was the color red, and final product we are getting the deep red. So the value of Kc also you can see here. A reddish color appears on adding 2 drops of 0.002 m potassium thiocyanate solution to 1 ml of 0.2 m iron nitrate solution due to the formation of FeSCN whole 2 positive. The intensity of the red color becomes constant on attaining equilibrium. This equilibrium can be shifted in either forward or reverse direction depending on our choice of adding a reactant or a product. The equilibrium can be shifted in the opposite direction by adding reagents that remove Fe3 positive or SCN negative ions. For example, oxalic acid H2C2O4 reacts with Fe3 positive ions to form the stable complex ion FeC2O4 whole thrice to the power whole 3 negative, thus decreasing the concentration of free Fe3 positive. In accordance with the Le-Chatelier's principle, the concentration stress of Removed Fe3 positive is relieved by dissociation of FeSCN whole 2 positive to replenish the Fe3 positive ions. Because the concentration of FeSCN 2 positive decreases, the intensity of red color decreases. Addition of aqueous HgCl2 also decreases red color because Hg2 positive reacts with HCN and HCN negative ions to form a stable complex ion HgSCN whole 4 the whole power 2 negative. Removal of free SCN negative shifts the equilibrium in equation from right to left to replenish SCN negative ions. Addition of potassium thiocyanate on the other hand increases the color intensity of the solution as it shifts the equilibrium to right. 7.8.2 Effect of pressure change. A pressure change obtained by changing the volume can affect the yield of a product in case of gaseous reaction where the total number of moles of gaseous reactants and total number of moles of gaseous products are different. In applying Le-Chatelier's principle to a heterogeneous equilibrium, the effect of pressure changes on solid and liquids can be ignored because the volume and concentration of a solution/liquid is nearly independent of pressure. Consider the reaction CO plus 3H2 gives out CH4 plus H2O, that is a reversible reaction. And here you can see that 4 mole of gaseous reactants, that is CO and 3H2, become 2 mole of gaseous products CH4 and H2. Suppose equilibrium mixture for the above reaction kept in a cylinder fitted with a piston at constant temperature is compressed to 1/2 of its original volume. Then total pressure will be doubled. The partial pressure and therefore concentration of reactants and products have changed and the mixture is no longer at equilibrium. The direction in which the reaction goes to re-establish equilibrium can be predicted by applying the Le-Chatelier's principle. Since pressure has doubled, the equilibrium now shifts in the forward direction, a direction in which the number of moles of the gas or pressure decreases. We know pressure is proportional to moles of the gas. This can also be understood by using reaction quitant, that is QC. Let CO, H2, CH4 and H2O be the molar concentrations at the equilibrium for methanation reaction. When volume of the reaction mixture is halved, the partial pressure and the concentration are doubled. We obtained the reaction quitant by replacing each equilibrium concentration by double its value. So here is the QC value, CH4 H2O upon CO H2 whole to the power 3, where the QC is less than Kc. The reaction proceeds in the forward direction. In reaction C plus O2, that is, and 2CO, when pressure is increased, the reaction goes into the reverse direction because the number of moles of gas increases in the forward direction. 7.8.3 Effect of inert gas addition. If the volume is kept constant and an inert gas such as argon is added which does not take part in the reaction, the equilibrium remains undisturbed. It is because the addition of an inert gas at constant volume does not change the partial pressure or the molar concentration of the substance involved in the reaction. The reaction quitant changes only if the added gas is a reactant or product involved in the reaction. 7.8.4 Effect of temperature change. Whenever an equilibrium is disturbed by a change in the concentration, pressure or volume, the composition of the equilibrium mixture changes because the reaction quitant QC no longer equals the equilibrium constant Kc. However, when a change in temperature occurs, the value of equilibrium constant Kc is changed. In general, the temperature dependence of the equilibrium constant depends on the sign of delta H for the reaction. The equilibrium constant for an exothermic reaction, that is negative delta H, decreases as the temperature increases. The equilibrium constant for an endothermic reaction, that is positive delta H, increases as the temperature increases. Temperature changes affect the equilibrium constant and rate of reactions. Product of ammonia according to the reaction N2 plus 3H2 reversible 2NH3. Delta H is equals to minus 92.38 kilojoule per mole is an exothermic reaction, and according to Le-Chatelier's principle, raising the temperature shifts the equilibrium to left and decreases the equilibrium concentration of ammonia. In other words, low temperature is favorable for high yield of ammonia, but practically very low temperatures slow down the reaction and thus a catalyst is used. Effect of temperature, and here is an experiment. Effect of temperature on equilibrium can be demonstrated by taking NO2 gas, that is brown in color, which Dimerizes into N2O4 gas that is colorless. 2NO2 reversible N2O4 delta H is equals to minus 57.2 kilojoule per mole. NO2 gas prepared by addition of CO turning to concentration HNO3 is collected in two 5 ml test tubes, ensuring same intensity of color of gas in each test tube, and a stopper sealed with aryl dyed, and 3 to 50 ml beakers 1, 2 and 3 containing freezing mixture water at room temperature and hot water 363 Kelvin respectively are taken. Figure 7.9. Both the test tubes are placed in beaker 2 for 8 to 10 minutes. After this done is placed in beaker 1 and the other in beaker 3. The effect of temperature on direction of reaction is depicted very well in this experiment. At low temperatures in beaker 1, the forward reaction of formation of N2O4 is preferred, as reaction is exothermic and thus intensity of brown color due to NO2 decreases, while in beaker 3 high temperature favors the reverse of reaction. Here you can see the figure 7.9. Formation of NO2 and thus the brown color intensifies. Effect of temperature can also be seen in endothermic reaction. COH2O whole 6 to the whole power 3 positive and plus 4Cl negative reversible COCl4 to negative plus 6H2O, and here the COH2O whole 6 3 positive color is pink and 4Cl negative is colorless, and the product is forming is in the blue color. At room temperature the equilibrium mixture is blue due to COCl4 2 negative. When cooled in freezing mixture the color of the mixture turns pink due to COH2O whole 6 3 positive. And 7.8.5, that is the effect of catalyst. A catalyst increases the rate of chemical reaction by making available a new low energy pathway for the conversion of reactants to products. It increases the rate of forward and reverse reaction that passes through the same transition state and does not affect equilibrium. Catalyst lowers the activation energy for the forward and reverse reaction by exactly the same amount. Catalyst does not affect the equilibrium composition of a reaction mixture. It does not appear in the balanced chemical equation or in the equilibrium constant expression. Let us consider the formation of NH3 from dinitrogen and dihydrogen, which is highly exothermic reaction and proceeds with decrease in total number of moles formed as compared to the reactants. Equilibrium constant decreases with increase in temperature. At low temperature, rate decreases and it takes long time to reach at equilibrium, whereas high temperature gives satisfactory rates but poor yields. German chemist Fritz Haber discovered that a catalyst consisting of iron catalyzes the reaction to occur at a satisfactory rate at temperatures where the equilibrium concentration of NH3 is reasonably favorable. Since the number of moles formed in the reaction is less than those of reactants, the yield of NH3 can be improved by increasing the pressure. Optimum conditions of temperature and pressure for the synthesis of NH3 using catalyst are around 500 degrees Celsius and 200 atm. Similarly, in the manufacture of sulfuric acid of bi-contact process, 2SO2 plus O2 reversible 2SO3, and the Kc value is here 1.7 into 10 to the power 26. Though the value of K is suggestive of reaction going to completion, but practically the oxidation of SO2 to SO3 is very slow. Thus platinum or divanadium pentaoxide V2O5, that is the divanadium pentaoxide V2O5 is used as catalyst to increase the rate of reaction. Note, if a reaction has an exceedingly small K, a catalyst would be a little help. 7.9 Ionic Equilibrium in solution. Under the effect of change of concentration on the direction of equilibrium, you have incidentally come across with the following equilibrium which involves ions Fe3 positive plus SCN negative, reversible Fe SCN2 positive. There are numerous equilibria that involve ions only. In the following sections, we will study the equilibria involves ions. It is well known that the aqueous solution of sugar does not conduct electricity. However, when common salt is added to water, it conducts electricity. Also, the conductance of electricity increases with an increase in concentration of common salt. Michel Faraday classified the substances into two categories based on their ability to conduct electricity. One category of substances conduct electricity in their aqueous solutions and are called electrolytes, while the other do not and are thus referred to as non-electrolytes. Faraday further classified electrolytes into strong and weak electrolytes. Strong electrolytes on dissolution in water are ionized almost completely, while the weak electrolytes are partially dissociated. For example, an aqueous solution of sodium chloride is comprised entirely of sodium ions and chloride ions, while that of acetic acid mainly contains unionized acetic acid molecules and only some acetate ions and hydronium ions. This is because there is almost 100% ionization in case of sodium chloride as compared to less than 5% ionization of acetic acid, which is a weak electrolyte. It should be noted that in weak electrolytes, equilibrium is established between ions and the unionized molecules. This type of equilibrium involving ions in aqueous solution is called ionic equilibrium. Acids, bases, and salts come under the category of electrolytes and may act as either strong or weak electrolytes. 7.10 Acids, bases, and salts. Acid, bases, and salts find widespread occurrence in nature. Hydrochloric acid present in the gastric juice is secreted by the lining of our stomach in an significant amount of 1.2 to 1.5 liter per day and is essential for digestive processes. Acetic acid is known to be the main constituent of vinegar. Lemon and orange juices contain citric acid and ascorbic acids, and tartaric acid is found in tamarind paste. As most of the acid tastes sour, the word acid has been derived from a Latin word acidus meaning sour, and acids are known to turn blue litmus paper into red and liberate dihydrogen on reacting with some metals. Similarly, bases are known to turn red litmus paper blue, taste bitter, and feel soapy. A common example of a base is washing soda used for washing purpose. When acids and bases are mixed in the right proportion, they react with each other to give salts. Some commonly known examples of salts are sodium chloride, barium sulfate, sodium nitrate. Sodium chloride, that is common salt, is an important component of our diet and is formed by the reaction between hydrochloric acid and sodium hydroxide. It exists in solid state as a cluster of positively charged sodium ions and negatively charged chloride ions, which are held together due to electrostatic interaction between oppositely charged species. The electrostatic forces between two charges are inversely proportional to dielectric constant of the medium. Water, a universal solvent, possesses a very high dielectric constant of 80. Thus, when sodium chloride is dissolved in water, the electrostatic interactions are reduced by a factor of 80, and this facilitates the ions to move freely in the solution. Also, they are well separated due to hydration with water molecules. Comparing the ionization of hydrochloric acid with that of acetic acid in water, we find that though both of them are polar covalent molecules, former is completely ionized into its constituent ions, while the latter is only partially ionized. The extent to which ionization occurs depends upon the strength of the bond and the extent of solvation of ions produced. The terms dissociation and ionization have earlier been used with different meaning. Dissociation refers to the process of separation of ions in water already existing as such in the solid state of the solute, as in sodium chloride. On the other hand, ionization corresponds to a process in which a neutral molecule splits into charged ions in the solution. Here we shall not distinguish between the two and use the two terms interchangeably. Here, some information about Faraday. Faraday was born near London into a family of very limited means. At the age of 14, he was an apprentice to a kind of bookbinder who allowed Faraday to read the books he was binding. Through a fortunate chance, he became laboratory assistant to Davy, and during 1813-4, Faraday accompanied him to the continent. During this trip, he gained much from the experience of coming into contact with many of leading scientists of the time. In 1825, he succeeded Davy as director of the Royal Institution Laboratories, and in 1833, he also became the first Fullerian professor of chemistry. Faraday's first important work was in analytical chemistry. After 1821, much of his work was on electricity and magnetism and different electromagnetic phenomena. His ideas have led to the establishment of modern field theory. He discovered his two laws of electrolytes in 1834. Faraday was a very modest and kind-hearted person. He declined all honors and avoided scientific controversies. He performed to work alone and never had any assistant. He disseminated science in a variety of ways, including his Friday evening discourses, which he founded at the Royal Institution. He has been very famous for his Christmas lecture on the chemical history of a candle. He published nearly 450 scientific papers. Great information it is. Hydronium and hydroxyl ions. But before that is 7.10.1 Arrhenius concept of acid and bases. According to Arrhenius theory, acids are substances that dissociates in water to give hydrogen ions, and bases are substances that produce hydroxyl ions. The ionization of an acid HX can be represented by the following equation. HX gives out H ion plus X negative. So HX plus H2O gives out H3O positive plus X negative. A bare proton H ion is very reactive and cannot exist freely in aqueous solution. Thus it bonds to the oxygen atom of a solvent water molecule to give trigonal pyramidal hydronium ion H3O positive it is. In this chapter, we shall use H ion and H3O positive interchangeably to mean the same, that is a hydrated proton. Similarly, a base molecule like MOH ionizes in aqueous solution according to the equation. MOH gives out M positive plus OH negative. The hydroxyl ion also exists in the hydrated form in the aqueous solution. Arrhenius concept of acid and base, however, suffers from the limitation of being applicable only to aqueous solution and also does not account for the basicity of substances like ammonia, which do not possess a hydroxyl group. Hydronium ion and hydroxyl ions. Hydrogen ion by itself is a bare proton with very small size, that is approximately 10 to the power minus 15 meter radius, and intense electric field, binds itself with the water molecule at one of the two available lone pairs on its, giving H3O positive. This species has been detected in many compounds. Example, H3O positive, Cl negative in the solid state. In aqueous solution, the hydronium ion is further hydrated to give species like H5O2 positive, H7O3 positive, and H9O4 positive. Similarly, the hydroxyl ion is hydrated to give several ionic species like H3O2 negative, H5O3 negative, and H7O4 negative, etc. See the structure of H9O4 positive. 7.10.2 The Bronsted-Lowry acids and bases. The Danish chemist Johannes Bronsted and English chemist Thomas M. Lowry gave a more general definition of acid and bases. According to Bronsted-Lowry theory, acid is a substance that is capable of donating a hydrogen ion H ion, and bases are substances capable of accepting a hydrogen ion H ion. In short, acids are proton donors and bases are proton acceptors. Consider the example of dissolution of NH3 in H2O represented by the following equation, and you can see the equation here. NH3 plus H2O reversible NH4 positive plus OH ion, and here you can see that is the base and H2O is the acid here, and NH4 positive is conjugate acid and OH negative is the conjugate base, and you can see this reaction here. The basic solution is formed due to the presence of hydroxyl ions. In this reaction, water molecule acts as a proton donor and ammonia molecule acts as a proton acceptor and are thus called Lowry-Bronsted acid and base respectively. In the reverse reaction, H ion is transferred from NH4 ion to OH negative. In this case, NH4 positive acts as a Bronsted acid while OH negative acted as a Bronsted base. The acid-base pair that differs only by one proton is called conjugate acid-base pair. Therefore, OH negative is called the conjugate base of an acid H2O and NH4 positive is called conjugate acid of the base NH3. If Bronsted acid is a strong acid, then its conjugate base is a weak base and vice versa. It may be noted that conjugate acid has one extra proton and each conjugate base has one less proton. Consider the example of ionization of hydrochloric acid in water. HCl acts as an acid of donating a proton to H2O molecule which acts as a base, and reaction is HCl plus H2O gives out H3O positive plus Cl negative. H3O positive is a conjugate base acid and Cl negative is a conjugate base. It can be seen in the above equation that water acts as a base because it accepts the proton. The species H3O positive is produced when water accepts a proton from HCl. Therefore, Cl negative is a conjugate base of HCl and HCl is a conjugate acid of Cl negative. Similarly, H2O is a conjugate base of an acid H3O positive and H3O positive is a conjugate acid of a base H2O. It is interesting to observe the dual role of water as an acid and base. In case of reaction with HCl, water acts as a base, while in case of ammonia, it acts as an acid by donating a proton. Some information about Arrhenius. Arrhenius was born near Uppsala, Sweden, and he represented his thesis on the conductivities of electrolyte solution to the University of Uppsala in 1884. For the next 5 years, he traveled extensively and visited a number of research centers in Europe. In 1895, he was appointed professor of physics at the newly formed University of Stockholm, serving its rector from 1897 to 1902. From 1905 until his death, he was director of physical chemistry at the Nobel Institution in Stockholm. He continued to work for many years in electrolytic solutions. In 1899, he discussed the temperature dependence of reaction rates on the basis of an equation, now usually known as Arrhenius equation. He worked in a variety of fields and made important contribution to immunochemistry, cosmology, the origin of life, and the causes of ice age. He was the first to discuss the greenhouse effect, calling by the name. He received a Nobel Prize in Chemistry in 1903 for his theory of electrolytic dissociation and its use in the development of chemistry. 7.10.3 Lewis acid and Lewis bases. G. N. Lewis in 1923 defined an acid as a species which accepts electron pair and base which donates an electron pair. As far as base are concerned, there is not much difference between Bronsted-Lowry and Lewis concept, as the base provides a lone pair in both the cases. However, in Lewis concept, many acids do not have proton. A typical example in a reaction of electron deficient species is BF3 with NH3. BF3 does not have a proton but still acts as an acid and reacts with NH3 by accepting its lone pair of electrons. The reaction can be represented by BF3 plus NH3 gives out BF3 NH3. Electron deficient species like AlCl3, CO3 positive, Mg2 positive, etc. can act as Lewis acids, while species like H2O, NH3, OH negative, etc., which can donate a pair of electrons, can act as Lewis bases. 7.11 Ionization of acid and bases. Arrhenius concept of acid and bases becomes useful in case of ionization of acids and bases, as mostly ionization in chemical and biological system occur in aqueous medium. Strong acids like perchloric acid HClO4, hydrochloric acid HCl, hydrobromic acid HBr, hydroiodic acid HI, nitric acid HNO3, and sulfuric acid H2SO4 are termed strong because they are almost completely dissociated into their constituent ions in an aqueous medium, thereby acting as proton donors. Similarly, strong bases like lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide CSOH, and barium hydroxide BaOH whole twice are almost completely dissociated into ions in an aqueous medium, giving hydroxyl ions, OH ion. According to Arrhenius concept, they are strong bases and acids as they are able to completely dissociate and produce H3O ion and OH ions respectively in the medium. Alternatively, the strength of an acid or base may also be gauged in terms of Bronsted-Lowry concept of acid and bases, wherein a strong acid means a good proton donor and a strong base implies a good proton acceptor. Consider the acid-base dissociation equilibrium of a weak acid HA. HA plus H2O gives out H3O positive plus A negative, and H3O positive is a conjugate acid and A negative is a conjugate base, and that is a reversible reaction. In section 7.10.2, we saw that acid or base dissociation equilibrium is dynamic, involving a transfer of proton in forward and reverse directions. Now the question arises that if the equilibrium is dynamic, then with passage of time, which direction is favored? What is the driving force behind it? In order to answer these questions, we shall deal into the issue of comparing the strengths of the two acids or bases involved in the dissociation equilibrium. Consider the two acids HA and H3O positive present in the above mentioned acid dissociation equilibrium. We have to see which among them is a stronger proton donor. Whichever exceeds in its tendency of donating a proton over other shall be termed as the stronger acid, and the equilibrium will shift in the direction of weaker acid. Say if HA is a stronger acid than H3O positive, then HA will donate protons and not H3O ion. and the solution will mainly contain A negative and H3O ions. The equilibrium moves in the direction of formation of weaker acid and weaker base, because the stronger acid donates a proton to the stronger base. It follows that as a stronger acid dissociates completely in water, the resulting base formed would be very weak. That is, a strong acid have very weak conjugate bases. Strong acids like perchloric acid HClO4, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid and sulfuric acid will give conjugate base ion ClO4 negative, ClBr negative, I negative, NO3 negative and HSO4 negative, which are much weaker bases than H2O. Similarly, a very strong base would give a very weak conjugate acid. On the other hand, a weak acid, say HA, is only partially dissociated in aqueous medium, and thus the solution mainly contains undissociated HA molecules. Typical weak acids are nitrous acid, hydrofluoric acid and acetic acid. It should be noted that the weak acids have very strong conjugate bases. For example, NH2 negative, O2 negative and H negative are very good proton acceptors and thus much stronger bases than H2O. Certain water-soluble organic compounds like phenolphthalein and bromothymol blue behave as weak acids and exhibit different color in their acids. HIN in and conjugate base ion negative forms. And here you can see this reaction. Such compounds are useful as indicators in acid-base titrations and finding out HIN concentration. 7.11.1 the ionization constant of water and its ionic product. Some substances like water are unique in their ability of acting both as an acid and a base. We have seen this in case of water in section 7.10.2 in presence of an acid. It accepts a proton and acts as the base, while in the presence of a base B negative it acts as an acid by donating a proton. In pure water, one H2O molecule donates proton and acts as an acid, and another water molecule accepts a proton and acts as a base at the same time. The following equilibrium exists: H2O plus H2O, reversible reaction, it is H3O positive plus OH negative. The dissociation constant is represented by K is equals to H3O positive into OH negative upon H2O. The concentration of water is omitted from the denominator, as water is a pure liquid and its concentration remains constant. H2O is incorporated within the equilibrium constant to give a new constant Kw, which is called the ionic product of water. Kw is equals to H ion into OH ion. The concentration of H positive has been found out experimentally as 1 into 10 to the power minus 7 m at 298 Kelvin. And as dissociation of water produces equal number of H ion and OH ions, the concentration of hydroxyl ions OH negative is equals to H ion is equals to 1 into 10 to the power minus 7 m. Thus the value of Kw at 298 Kelvin is equals to 1 into 10 to the power minus 4 m square. The value of Kw is temperature dependent as it is an equilibrium constant. The density of pure water is 1000 gram per liter and its molar mass is 18 gram per mole. From this, the molarity of a pure water can be given as, that is 55.55 m. Therefore, the ratio of dissociated water to that of undissociated water can be given as, here you can see the value, that is the 1.8 into 10 to the power minus 9 or approximately 2 in 10 to the power minus 9. Thus, equilibrium lies mainly towards undissociated water. We can distinguish acidic, neutral and basic aqueous solutions by the relative values of the H3O positive and OH negative concentration. Acidic, H3O positive is greater than OH negative. Neutral, H3O positive is equal to OH ion, and basic, H3O positive is less than OH negative. 7.11.2 the pH scale. Hydronium ion concentration in molarity is more conveniently expressed on a logarithmic scale known as the pH scale. The pH of a solution is defined as the negative logarithm to base 10 of the activity of hydrogen ion. In dilute solutions, that is less than 0.01 m, activity of hydrogen ion is equal in magnitude to molarity represented by H ion. It should be noted that activity has no units and is defined as H ion per mole per liter. From the definition of pH, the following can be written here, that pH is equals to minus log H ion. Thus, an acidic solution of HCl will have a pH of 2, and similarly a basic solution of NaOH having OH ion is equals to 10 to the power minus 4 m and H3O ion is equals to 10 to the power minus 10 m will have a pH 10. At 25 degrees Celsius, pure water has a concentration of hydrogen ions. H ion is equals to 10 to the power minus 7 m, hence the pH of pure water is given as pH is equals to 7. Acidic solutions possesses a concentration of hydrogen ions that is greater than 10 to the power minus 7 m, while basic solution possesses a concentration of hydrogen ion that is less than 10 to the power minus 7 m. Thus, we can summarize that acidic solution has pH less than 7, basic has pH greater than 7, and neutral is having pH is equals to 7. Now again consider the equation at 298 Kelvin, Kw is equals to 10 to the power minus 14. Taking negative logarithm on the both side of equation, we obtain here the final equation I am reading, that is equals to minus log 10 to the power minus 14, and pKw is equals to pH plus POH is equals to 14. Note that although Kw may change with temperature, the variations in pH with temperature are so small that we often ignore it. pKw is a very important quantity for aqueous solutions and controls the relative concentration of hydrogen and hydroxyl ions as their product is a constant. It should be noted that as the pH scale is a logarithmic, a change in pH by just 1 unit also means change in H ion by a factor of 10. Similarly, when the hydrogen ion concentration H ion changes by a factor of 100, the value of pH changes by 2 units. Now you can realize why the change in pH with temperature is often ignored. Measurement of pH of a solution is very essential as its value should be known when dealing with biological and cosmetic application. The pH of a solution can be found roughly with the help of a pH paper that has different color in solutions of different pH. Nowadays, pH paper is available with 4 strips on it. The different strips have different colors at the same pH. The pH in the range of 1 to 14 can be determined with an accuracy of approximately 0.5 using pH paper. Here you can see the figure 7.11. For greater accuracy, pH meters are used. pH meter is a device that measures the pH dependent electrical potential of the test solution within 0.001 precision. pH meter of the size of a writing pen are now available in the market. The pH of some very common substances are given in table 7.5. See here the table 7.5. The pH of some common substances I am reading because this is important, and name of the fluid and the pH, right? Saturated solution of NaOH approximate 15, 0.1 m NaOH solution that is 13, lime water 10.5, milk of magnesia that is 10, egg white seawater that is 7.8, human blood 7.4, milk 6.8, human saliva 6.4, black coffee 5, tomato juice approximate 4.2, soft drinks and vinegar approximate 3, lemon juice approximate 2.2, gastric juice approximate 1.2, and 1 m HCl solution that is approximate 0, and concentrated HCl that is approximate minus 1.0. 7.11.3 Ionization constants of weak acids. Consider a weak acid HX that is partially ionized in the aqueous solution. The equilibrium can be expressed by HX plus H2O gives out H3O positive plus X negative. So here you can see all the calculation, and here the C is the initial concentration of the undissociated acid. HX at time t is equals to 0 and alpha is extent up to which HX is ionized into ions. Using these notations, we can derive the equilibrium constant for the above discussed acid dissociation equilibrium. Ka is equals to C square alpha square upon C 1 minus alpha, and that is equals to C alpha square upon 1 minus alpha. Ka is called the dissociation or ionization constant of acid HX. It can be represented alternatively in terms of molar concentration as follows. Ka is equals to H ion S into X negative upon HX. At a given temperature T, Ka is a measure of the strength of the acid HX, that is larger the value of Ka, the stronger is the acid. Ka is dimensionless quantity with the understanding that standard state concentration of all species is 1 m. The values of the ionization constants of some selected weak acids are given in table 7.6. Here I am reading, this is also important because, so here it is hydrofluoric acid 3.5 into 10 to the power minus 4. One side it is acid and another side it is ionization constant Ka, right? Nitrous acid 4.5 into 10 to the power minus 4, formic acid 1.8 into 10 to the power minus 4, niacin C5H4NCOOH 1.5 into 10 to the power minus 5, acetic acid 1.74 into 10 to the power minus 5, benzoic acid C6H5COOH 6.5 into 10 to the power minus 5, hypochlorous acid HClO that is 3 into 10 to the power minus 8, hydrocyanic acid HCN that is 4.9 into 10 to the power minus 10, and phenol is having 1.3 into 10 to the power minus 10. The pH scale for the hydrogen ion concentration has been so useful that besides pKw it has been extended to other species and quantities. Thus we have, so pK is equals to minus log Ka. Knowing the ionization constant Ka of an acid and its initial concentration C, it is possible to calculate the equilibrium concentration of all species and also the degree of ionization of the acid and the pH of the solution. A general stepwise approach can be adopted to evaluate the pH of the weak electrolyte as follows. Step 1. The species present before dissociation are identified as Bronsted-Lowry acids or bases. Step 2. Balanced equations for all possible reaction, that is with the base species acting both as acid as well as base, are written. Step 3. The reaction with the higher Ka is identified as the primary reaction whilst the other is a subsidiary reaction. Step 4. Enlist in a tabular form the following values for each of the species in the primary reaction. A. Initial concentration. C. B. Change in concentration on proceeding to equilibrium in terms of alpha, degree of ionization. C. Equilibrium concentration. Step 5. Substitute equilibrium concentrations into equilibrium constant equation for principal reaction and solve for alpha. Step 6. Calculate the concentration of species in principal reaction. Step 7. Calculate pH, that is equals to minus log H3O positive ion. The above mentioned methodology has been elucidated in the following examples. 7.11.4 Ionization of weak bases. The ionization of weak base MOH can be represented by equation. MOH gives out M plus OH negative, and in a weak base there is a partial ionization of MOH into M positive and OH negative. The case is similar to that of acid dissociation equilibrium. The equilibrium constant for base ionization is called base ionization constant and is represented by Kb. It can be expressed in terms of concentration and molarity of various species in equilibrium by the following equation. Kb is equals to M positive into OH negative upon MOH. Alternatively, if C is equals to initial concentration of base and alpha is degree of this ionization of base, that is the extent to which the base ionizes, when equilibrium is reached, the equilibrium constant can be written as Kb is equals to C alpha square upon C into 1 minus alpha is equals to C alpha square upon 1 minus alpha. The value of the ionization constants of some selected weak bases Kb are given in table 7.7. Here you can see the dimethylamine, that is the base, and its Kb value is 5.4 into 10 to the power minus 4. Triethylamine, its value is having 6.45 into 10 to the power minus 5. Ammonia 1.787 into 10 to the power minus 5. Quinine is a plant product and it is having 1.10 into 10 to the power minus 6. Pyridine C5H5N, it is having the value of Kb 1.77 into 10 to the power minus 9. Aniline C6H5NH2, that value is 4.27 into 10 to the power minus 10. And urea 1.3 into 10 to the power minus 14. Many organic compounds like amines are weak bases. Amines are derivatives of ammonia in which one or more hydrogen atoms are replaced by another group. For example, methylamine, codeine, quinine and nicotine all behaves as very weak bases due to their very small Kb. Ammonia produces OH ion in aqueous solution, NH3 plus H2O reversible and H4 ion plus OH ion. The pH scale for the hydrogen ion concentration has been extended to get pKb is equals to minus log Kb. Now 7.11.5 relation between Ka and Kb. As seen earlier in this chapter, Ka and Kb represent the strength of an acid and a base respectively. In case of a conjugate acid-base pair, they are related in a simpler manner so that if one is known, the other can be deduced. Considering the example of NH4 ion and NH3 we see here, you can see this complete calculation. And here the Ka represents the strength of an H4 ion as an acid and Kb represents the strength of an H3 as a base. It can be seen from the net reaction that the equilibrium constant is equal to the product of equilibrium constant Ka and Kb for the reactions added. Thus Ka into Kb is equals to the final value we will get here, that is 1 into 10 to the power minus 14 m. This can be extended to make a generalization. The equilibrium constant for a net reaction obtained after adding two or more reactions equal the product of the equilibrium constant for individual reactions. So K net is equals to K1 into K2 into so and so on. Similarly, in case of a conjugate acid and base pair, Ka into Kb is equals to Kw. Knowing one the other can be obtained, it should be noted that a strong acid will have a weak conjugate base and vice versa. Alternatively, the above expression Kw is equals to Ka into Kb can also be obtained by considering the base dissociation equilibrium reaction. Here you can see this reaction and the value of Kb is BH positive into OH negative upon B. As the concentration of water remains constant, it has been omitted from the denominator and incorporated within the dissociation constant. Then multiplying and dividing the above expression by H ion, we get Kb is equals to BH positive, OH negative, H positive upon B into H positive. And that is the final value Kw upon Ka. So Ka into Kb is equals to Kw. It may be noted that if we take negative logarithm of both sides of the equation, then pK values of the conjugate acid and base are related to each other by this equation. pKa plus pKb is equals to pKw is equals to 14 and at 298 Kelvin. 7.11.6 di and polybasic acid and di and polyacidic bases. Some of the acids like oxalic acid, sulfuric acid and phosphoric acids have more than one ionizable proton per molecule of the acid. Such acids are known as polybasic or polyprotic acids. The ionization reaction, for example, for a dibasic acid H2X are represented by the equation H2X gives out H ion plus HX negative and HS negative is giving H ion plus X2 negative. And the corresponding equilibrium constant are given below. Ka1 is equals to H ion into Hx negative upon H2x. And the next Ka2 value is the H positive into X2 negative upon Hx negative. Here Ka1 and Ka2 are called the first and second ionization constant respectively of the acid H2X. Similarly, for the tribasic acid H3PO4, we have three ionization constants. The values of the ionization constants for some common polyprotic acids are given in table 7.8. Here you can see. It can be seen that higher order ionization constant are smaller than the lower order ionization constant of a polyprotic acid. The reason for this is that it is more difficult to remove a positively charged proton from a negative ion due to electrostatic forces. This can be seen in the case of removing a proton from the uncharged H2CO3 as compared from a negatively charged HCO3 negative. Similarly, it is more difficult to remove a proton from a doubly charged HPO42 negative ion as compared to H2PO4 negative. Polyprotic acid solutions contain a mixture of acids like H2A, HA negative and A2 negative in case of a diprotic acid. H2A being a strong acid, the primary reaction involves the dissociation of H2A and H3O positive in the solution comes mainly from the first dissociation step. 7.11.7 Factors affecting the acid strengths. Having discussed quantitatively the strengths of acid and bases, we come to a stage where we can calculate the pH of a given acid solution. But the curiosity rises about why should some acids be stronger than others? What factors are responsible for making them stronger? The answer lies in its being a complex phenomena. But broadly speaking, we can say that the extent of dissociation of an acid depends on the strength and polarity of HA bond. In general, when the strength of HA bond decreases, that is the energy required to break the bond decreases, HA becomes a stronger acid. Also, when the HA bond becomes more polar, that is the electronegativity difference between the atoms H and A increases and there is a marked charges separation, cleavage of the bond becomes easier, thereby increasing the acidity. But it should be noted that while comparing elements in the same group of the periodic table, HA bond strength is a more important factor in determining acidity than its polar nature. As the size of A increases down the group, HA bond strength decreases and so the acid strength increases. For example, Size increases. HF is very less than HCl, is very less than HBr, is very less than HI. Acid strength, it means it is increasing as the size is increasing. Similarly, H2S is a stronger acid than H2O. But when we discuss elements in the same row of the periodic table, HA bond polarity becomes the deciding factor for determining the acid strength. As the electronegativity of A increases, the strength of the acid is also increases. For example, electronegativity of A increases, CH4 is less than NH3 is less than H2O is less than HF. That means electronegativity is increasing as the acid strength increases. 7.11.8 Common ion effect in the ionization of acid and bases. Consider an example of acetic acid dissociation equilibrium represented as CH3COH gives out H ion plus CH3CO negative. Here you can see the value of Ka, H ion into acetate ion, that is AC negative upon HAC. Addition of acetate ions to an acetic acid solution results in decreasing the concentration of hydrogen ions. Also, if H ions are added from an external source, then the equilibrium moves in the direction of undissociated acetic acid, that is, in a direction of reducing the concentration of hydrogen ions. This phenomena is an example of common ion effect. It can be defined as a shift in equilibrium on adding a substance that provides more of an ionic species is already present in the dissociation equilibrium. Thus, we can say that common ion effect is a phenomena based on the Le-Chatelier's principle discussed in section 7.8. In order to evaluate the pH of the solution resulting on addition of 0.05 m acetate ion to a 0.05 m acetic acid solution, we shall consider the acetic acid dissociation equilibrium once again. Here you can see the complete calculation. 7.11.9 Hydrolysis of salts and the pH of their solution. Salts formed by the reaction between acids and bases in definite proportions undergo ionization in water. The cations and anions formed on ionization of salts either exist as hydrated ions in aqueous solutions or interact with water to reform corresponding acid or bases depending upon the nature of salts. The later process of interaction between water and cation anions or both of the salt is called hydrolysis. The pH of the solution gets affected by the interaction. The cations, that is example sodium ion, potassium ion, calcium ion, barium ion, etc., of strong bases and anions like chloride, bromide, NO3 negative, ClO4 negative, etc., of strong acids simply get hydrated but do not hydrolyze, and therefore the solution of salts formed from strong acids and bases are neutral, that is their pH is 7. However, the other category of salts do undergo hydrolysis. We now consider the hydrolysis of the salts of the following types. Number 1, salts of weak acid and strong base, example CH3COONA. Number 2, salts of strong acid and weak base, that is NH4Cl. And number 3, salts of weak acid and weak base, that is CH3CONH4. In the first case, CH3COONA being a salt of weak acid and CH3COOH and a strong base, NaOH gets completely ionized in aqueous solution. Here you can see the reaction. Acetate ion thus formed undergoes hydrolysis in water to give acetic acid and OH ions. You can see this reaction. Acetic acid being a weak acid, that Ka is equals to 1.8 into 10 to the power minus 5, remains mainly unionized in solution. This results in increase of OH ion concentration in solution, making it alkaline. The pH of such a solution is more than 7. Similarly, NH4Cl formed from weak base NH4OH and strong acid, HCl in water dissociates completely. NH4Cl gives out NH4 ion plus Cl negative. Ammonium ions undergo hydrolysis with water to form NH4OH and H ion. And here you can see this reaction. Ammonium hydroxide is a weak base. Kb is equals to 1.77 into 10 to the power minus 5 and therefore remains almost unionized in solution. This results in increased of H ion concentration in solution, making the solution acidic. Thus, the pH of NH4Cl solution in water is less than 7. Consider the hydrolysis of CH3COONH4 salt formed from weak acid and weak base. The ions formed undergo hydrolysis as follow. CH3CO negative plus NH4 ion plus H2O, reversible reaction it is, and it is forming CH3COOH plus NH4OH. And here you can see CH3COH and NH4OH also remain into partially dissociated form, and you can see all the dissociated form. Without going into detailed calculation, it can be said that degree of hydrolysis is independent of concentration of solution, and pH of solution is determined by their pK values. pH is equals to 7 plus 1 by 2 pKa minus pKb. The pH solution can be greater than 7 if the difference is positive, and it will be less than 7 if the difference is negative. 7.12 Buffer solutions. Many body fluids, example blood or urine, have definite pH, and any deviation in their pH indicates malfunctioning of the body. The control of pH is also very important in many chemical and biochemical processes. Many medical and cosmetic formulations require that these be kept and administered at a particular pH. The solutions which resist change in pH on dilution or with the addition of small amounts of acid or alkali are called buffer solutions. Buffer solution of known pH can be prepared from the knowledge of pKa of the acid or pKb of base, and by controlling the ratio of the salt and acid or salt and base. A mixture of acetic acid and sodium acetate acts as buffer solution around pH 4.75, and a mixture of ammonium chloride and ammonium hydroxide acts as a buffer around pH 9.25. You will learn more about buffer solution in higher classes. 7.12.1 Designing buffer solutions. Knowledge of pKa, pKb and equilibrium constant help us to prepare the buffer solution of known pH. Let us see how we can do this. Preparation of acidic buffer. To prepare a buffer of acidic pH, we use weak acid and its salt formed with a strong base. We develop the equation relating the pH, the equilibrium constant Ka of weak acid, and ratio of concentration of weak acid and its conjugate base. For the general case where the weak acid Ha ionizes in water, you can see this calculation here. The expression 7.40 is known as Henderson-Hasselbalch equation, and the quantity A negative upon Ha is the ratio of concentration of conjugate base anion, that is of the acid, and the acid present in the mixture. Since acid is a weak acid, it ionizes to a very little extent, and concentration of Ha is negligibly different from concentration of acid taken to form buffer. Also, most of the conjugate base A negative comes from the ionization of salt of the acid. Therefore, the concentration of conjugate base will be negligibly different from the concentration of salt. Thus, equation 7.40 takes from the pH is equals to pKa plus log salt upon acid. In the equation 7.39, if the concentration of A negative is equal to the concentration of Ha, then pH is equals to pKa, because value of log 1 is 0. Thus, if we take molar concentration of acid and salt same, the pH of the buffer solution will be equal to the pKa of the acid. So, for preparing the buffer solution of the required pH, we select that acid whose pKa is close to the required pH. For acetic acid, pKa value is 4.76. Therefore, pH of the buffer solution formed by acetic acid and sodium acetate taken in equal molar concentration will be around 4.76. A similar analysis of a buffer made with a weak base and its conjugate acid leads to the result POH is equals to pKb plus log conjugate acid BH positive, that is, and base upon base B. And pH of a buffer solution can be calculated by using the equation pH plus POH is equals to 14. We know that pH plus POH is equals to pKw and pKa plus pKb is equals to pKw. On putting these values in the equation, it takes the form as follows. Here we will get this equation pH is equals to pKa plus log conjugate acid BH positive upon base B. If molar concentration of base and its conjugate acid cation is same, then pH of the buffer solution will be same as pKa for the base. pKa value for ammonia is 9.25. Therefore, a buffer of a pH close to 9.25 can be obtained by taking ammonia solution and ammonium chloride solution of same molar concentration. For a buffer solution formed by ammonium chloride and ammonium hydroxide, equation becomes pH is equals to 9.25 plus log conjugate acid upon base, and that is BH positive upon B. pH of a buffer solution is not affected by dilution because ratio under the logarithmic term remains unchanged. 7.13 Solubility Equilibria of sparingly soluble salt. We have already known that the solubility of ionic solids in water varies a great deal. Some of these, like calcium chloride, are so soluble that they are hygroscopic in nature and even absorb water vapor from atmosphere. Others, such as lithium fluoride, have so little solubility that they are commonly termed as insoluble. The solubility depends on a number of factors, important amongst which are the lattice enthalpy of the salt and the solvation enthalpy of the ions in a solution. For a salt to dissolve in a solvent, the strong forces of attraction between its ion lattice enthalpy must be overcome by the non-ion solvent interaction. The solvation enthalpy of ions is referred to in terms of solvation, which is always negative, that is, energy is released in the process of solvation. The amount of solvation enthalpy depends on the nature of the solvent. In case of a nonpolar covalent solvent, solvation enthalpy is small and hence not sufficient to overcome lattice enthalpy of the salt. Consequently, the salt does not dissolve in nonpolar solvent. As a general rule, for a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy, so that later may be overcome by former. Each salt has its characteristic solubility, which depends on temperature. We classify salts on the basis of their solubility in the following three categories: Category 1, Category 2, Category 3, and soluble, slightly soluble, and sparingly soluble. And here in the case of soluble, the solubility is greater than 0.1 m. In slightly soluble, that is the 0.01 m is less than solubility is less than 0.1 m. And in the sparingly soluble, that is the solubility is less than 0.01 m. We shall now consider the equilibrium between the sparingly soluble ionic salt and its saturated aqueous solution. 7.13.1 Solubility Product Constant. Let us now have a solid like barium sulfate in contact with its saturated aqueous solution. The equilibrium between the undissolved solid and the ions in a saturated solution can be represented by the equation. BaSO4 gives out Ba2 positive plus SO4 2 negative, and the equilibrium constant is given by the equation K is equals to Ba2 positive SO4 2 negative upon BaSO4. For a pure solid substance, the concentration remains constant, and we can write Ksp is equals to KBaSO4 is equals to Ba2 positive BaSO4 2 negative. We call Ksp the solubility product constant or simply solubility product. The experimental value of Ksp is above equation at 298 K is 1.1 into 10 to the power minus 10. This means that for solid barium sulfate in equilibrium, when its saturated solution, the product of the concentrations of barium and sulfate ion is equal to its solubility product constant. The concentration of the two ions will be equal the molar solubility of the barium sulfate. If molar solubility is S, then 1.1 into 10 to the power minus 10, and S is equals to S square, and the value of S is then 1.05 into 10 to the power minus 5. Thus, molar solubility of a barium sulfate will be equal to 1.05 into 10 to the power minus 5. A salt may given on dissociation two or more than two anions and cations carrying different charges. For example, consider a salt like zirconium phosphate of molecular formula Zr 4 positive the whole 3 and PO4 3 negative the whole 4. It dissociates into 3 zirconium cations of charge plus 4 and 4 phosphate ions of charge minus 3. If the molar solubility of zirconium phosphate is S, then it can be seen from the stoichiometry of the compound that here you can see the calculation. A solid salt of the general formula MXP positive XYQ negative with molar solubility S in equilibrium with its saturated solution may be represented by the equation MX XY is the reversible reaction XMP positive plus YXQ negative, and its solubility product constant is given by, here you can see this. The term Ksp in equation is given by Qsp when the concentration of one or more species is not concentration under equilibrium. Obviously, under equilibrium conditions, Ksp is equals to Qsp, but otherwise it gives the direction of the process of precipitation or dissolution. The solubility product constants of a number of common salts at 298 K are given in table 7.9. Here you can see the table 7.9, the solubility product constants, Ksp of some common ionic salts at 298 K. 7.13.2 common ion effect on solubility of ionic salts. It is expected from Le Chatelier's principle that if we increase the concentration of any one of the ions, it should be combined with the ion of its opposite charge and some of the salt will be precipitated till once again Ksp is equals to Qsp. Similarly, if the concentration of one of the ions is decreased, more salt will dissolve to increase the concentration of both the ions till once again Ksp is equals to Qsp. This is applicable even to soluble salts like sodium chloride, except that due to higher concentration of the ions, we use their activities instead of their molarities in the expression for Qsp. Thus, if we take a saturated solution of sodium chloride and pass HCl gas through it, then sodium chloride is precipitated due to increased concentration of chloride ion available from the dissociation of HCl. Sodium chloride thus obtained is very high purity and we can get rid of impurities like sodium and magnesium sulfates. The common ion effect is also used for almost complete precipitation of a particular ion, as it's a sparingly soluble salt with very low value of solubility product for gravimetric estimation. Thus, we can precipitate silver ion as silver chloride, ferric ion as its hydroxide or hydrated ferric oxide, and barium ion as its sulfate for quantitative estimations. The solubility of salts of weak acids like phosphates increase at lower pH. This is because at lower pH, the concentration of the anion decreases due to its protonation. This in turn increases the solubility of the salt as that Ksp is equals to Qsp. We have to satisfy two equilibria simultaneously. You can see this complete calculation here. Thus, solubility S increases with increase in H ion or decrease in pH. Summary. When the number of molecules leaving the liquid to vapor equals the number of molecules returning to the liquid from vapor, equilibrium is said to be attained and is dynamic in nature. Equilibrium can be established for both physical and chemical processes, and this stage rate of forward and reverse reaction are equal. Equilibrium constant Kc is expressed as the concentration of products divided by reactants, each term raised to the stoichiometric coefficient. For reaction AA plus BB reversible CC plus DD, Kc is equals to C to the power C D to the power D upon A to the power A and B to the power B. Equilibrium constant has constant value at a fixed temperature, and this stage all the macroscopic properties such as concentration, pressure, etc. become constant. For a gaseous reaction, equilibrium constant is expressed as Kp and is written by replacing concentration terms by partial pressure in Kc expression. The direction of reaction can be predicted by reaction quotient Qc, which is equal to Kc at equilibrium. Le-Chatelier's principle states that the change in any factor such as temperature, pressure, concentration, etc. will cause the equilibrium to shift in such a direction so as to reduce or counteract the effect of the change. It can be used to study the effect of various factors such as temperature, concentration, pressure, catalyst and inert gases on the direction of equilibrium, and to control the yield of products by controlling these factors. Catalyst does not affect the equilibrium composition of reaction mixture but increases the rate of chemical reaction by making available a new lower energy pathway for conversion of reactants to products and vice versa. All substances that conduct electricity in aqueous solution are called electrolytes. Acid, bases and salts are electrolytes, and the conduction of electricity by their aqueous solution is due to anions and cations produced by the dissociation or ionization of electrolytes in aqueous solution. The strong electrolytes are completely dissociated. In weak electrolyte, there is equilibrium between the ions and the unionized electrolyte molecules. According to the Arrhenius acid give hydrogen ions, while base produces hydroxyl ion in their aqueous solution. Bronsted-Lowry, on other hand, defined an acid as a proton donor and a base as a proton acceptor. When a Bronsted-Lowry acid reacts with a base, it produces its conjugate base and a conjugate acid corresponding to the base with which it reacts. Thus, a conjugate pair of acid-base differs only by one proton. Lewis further generalized the definition of an acid as an electron pair acceptor and a base as an electron pair donor. The expressions of ionization constant of weak acid and weak bases are developed using Arrhenius definition. The degree of ionization and its dependence on concentration and common ion are discussed. The pH scale for the hydrogen ion concentration has been introduced and extended to other quantities. pK is equals to minus log Ka, pKb is equals to minus log Kb, and pKw is equals to minus log Kw, etc. The ionization of water has been considered, and we note that equation pH plus pOH is equals to pKw is always satisfied. The salts of strong acid and weak base, weak acid and a strong base, and weak acid and weak base undergo hydrolysis in aqueous solution. The definition of buffer solutions and their importance are discussed briefly. The solubility equilibrium of sparingly soluble salts is discussed, and the equilibrium constant is introduced as solubility product constant, that is KSP. Its relationship with solubility of the salt is established. The conditions of precipitation of the salt from their solutions or their dissolution in water are worked out. The role of common ion and the solubility of sparingly soluble salts is also discussed. Chapter done. So students, if these audiobooks are helping you, then press the like button. And if you are new in my channel, then please subscribe and share with your friends also, so that they will also get the benefit of these audiobooks. So take care everyone. See you soon in my next video. Till then, just stay tuned with me. Bye bye.